Hello, and welcome to Python for Informatics. Right now we're going to cover Chapter 1. I'm Charles Severance from the University of Michigan, and I'm the author, and I'll be your lecturer for this online lecture of the first chapter of the book. This lecture and my slides and the book, as a matter of fact, are all open content, open materials. They're copyright Creative Commons attribution, and this video recording is also copyright Creative Commons attribution. It's important to be explicit about copyright, and so I say it right at the beginning. So computers basically want to be helpful. They are programmed. Matter of fact, this is a microprocessor. This is really just an electrical part. It's got wires and circuits inside of it, and somebody spent a lot of engineering time to make it so that these pins in the back take instructions from us, from operating systems, from the hard drive, from the memory. Instructions come into here and then results come out. It's really sort of a very programmable hand calculator, and it's our job to put instructions in. This thing, in a sense, is wired to be curious about what's next, right? It's like tell me what you want to do next. What do you want to do next? What do you want to do next? And after that, what do you want to do next? And it just happens to do that a billion or so times a second. And so that's sort of the low-level piece. But you can also think, if you have like a PDA, something like this, all of the buttons on here are some kind of, what's next, right? Each of those is sort of something begging for my attention. Some application developer who's built a really cool application and says, please use me, please click me. I am sort of nothing without you. We humans are the things that sort of cause computers to start doing something. And this will sit here happily until I've caused it to do something. Now, whoa, hope it's still okay. Yeah, seems to be fine. Seems to be fine. Takes a lick in and keeps on ticking. So these anyone can use, right? They say even animals can use a Macintosh smartphone. And so you don't have to be a programmer. But to get this to do what you want, you need to learn a different language. And we need to learn the language of the instructions to tell it what to do. So that's what we're going to do. We're going to learn how to talk to this. Yo! Because it's asking us a question, we have to give the answer. So what's a programmer? A programmer is somebody who writes a program, which is a script or a set of instructions that tell one of these kinds of things what it is that they're supposed to do. And sometimes you're running a program like Moodle, an open source learning management system, or Sakai, another open source learning management system. And sometimes you'll even get paid to do that, right? Sometimes you do it for free, sometimes you get paid. Sometimes you write things for yourself. But if you think about it, all these applications on my iPhone, somebody's making some money off of these. They may not be able to quit their job, but a surprising number have been able to quit their job or start small companies. Maybe not gigantic companies, but small companies. So these people that can put applications inside of our computers are programmers because they understand the way that we talk to these computers. And part of what I'm going to try to do is to get you to move from the mindset of the end user who thinks of this as something just to click on to the mindset of the programmer who's kind of on the inside trying to get out to you. So that's, as we sort of move from user to programmer, we move from outside to inside, and we think of the world out there. It's like, what are they going to push? What button are they going to push? So here's kind of a picture of that. So on the outside, we're users. We click on buttons. We click on websites. We click on buttons on our phones, etc., etc. But what's really going on inside of all that is there's a computer with a bunch of hardware inside of that. And it has inside of it data, networks, other information, and software is what makes all that make sense. And so part of what I want you to do is I want you to stop thinking about how to use these things from the outside, and we move to becoming a programmer. We're someone on the inside. We're with the CPU. We're with the memory. We are with the network connection. We are doing things on behalf of the user and presenting them back up to the user. So why be a programmer? Now, this class is specifically not trying to turn you into a professional programmer, even though I'd be very proud if after 5, 10 more classes you were a professional programmer, but that's not the purpose of this class. Sometimes you just want to get something done. You got an Excel spreadsheet at work and the data's not right. You got the data from somebody else and it's got like extra spaces where it shouldn't have it, or the missing fields or something. You got to do something to it that Excel can't do, and you're stuck like saying, "Oh, I want to mess with this data and put it in Excel so I can do my job, but it's a pain in the neck and I have to sit and bring it into a text editor like Microsoft Word and go line by line and make all kinds of mistakes and clean the data up." You can write a program to do that. And that's the kind of programs we're going to do. Programs that serve our needs inside the computer, but to serve our needs. Professional programmers tend to build things for other people to use, right? They tend to build things that everyone else does. But we're going to build stuff primarily for ourselves. So, what is code? What is software? We use these words pretty much independently. A program. It's really a sequence of stored instructions. We learn the language that this talks, and then we will feed the instructions in one at a time. It takes them one at a time. It gives us back a result. We give it a next one. Give it back, in, out, in, out. So it's really a sequence of stored instructions, but it's kind of more than that. It's sort of like our creativity. And if you've been using some of my software, like my MOOC software, I spent about a month writing all that stuff, and it's like, it's me. I mean, it's my vision of how cool stuff ought to work, right? And so it's more than just getting something done. It's also a sense of pride and a sense of accomplishment, especially if you're giving something that other people can make use of. It's really, I think it's very creative. And it's what attracted me to being a programmer in the first place, is that I could leverage the capabilities inside of here, and I could do things, the cool things, on behalf of the user. So, code, software, a program. So let's get a non-technical example of this. So I'll have you link out to the YouTube for this. This is the Macarena. The Macarena is a song that has with it a well-known dance that everyone seems to know or either get taught very quickly. So I'll stop and let you watch the Macarena and then come back. So welcome back. I hope you enjoyed that. In a sense, what we've got there is a program for human beings. And maybe you learned that at a club or something and they told you what to do next. Well, I can teach you how to do the Macarena by writing a simple program right now. So here's my Macarena. While the music plays, means you do it over and over and over again, to the beat. That's kind of like computers. They do things in a beat. They happen to have 3 billion beats a second, but as it were. So we're going to do this multiple times. So we have this whole group of instructions that we're going to do, right? Left hand out and up, right hand out and up, flip left hand, flip right hand to right shoulder, right hand to left shoulder, etc., etc. Now, this particular little program has a mistake in it. Actually, several. I want you to look and see if you can find the mistakes in the program. Okay, so here are the places that have the mistake, right? The mistake is right hand to the back of the head and left hand to right hit, not hip. Now, if you're in a bar and you take a ham and you hit somebody in the back of the head, that's not very nice when you're dancing to this song. These are what's called bugs. Now, a human reading this would say, oh, I think they meant to say hand here. But a computer is much more literal than people. We'll see a couple of exercises where we'll see that people can correct little mistakes like this, but computers, they cannot, right? So we have to fix these bugs, and we have to say right hand, and we have to say hip when we mean hip. So we have to be explicit. Computers do exactly what we say. They don't do what we mean to do. So let's clear that. Here's another example. Okay, see how this comes out. You're supposed to count the number of times the word the appears in this sentence. Count it. And the word the, how many times? Okay, your turn. Now here, this is not something humans are good at. I moved it around, I played a little music, I confused you, I put a picture of a clown car in the upper left-hand corner, etc., etc., etc. Now it turns out that computers, once we tell them what to do, are very good at concentration. It can easily go through 30 words and find the most common word, or 3 million words and find the most common word, and it'll never make a mistake. But we first have to give it a set of instructions. So I don't want you to learn this right now, but this is a Python program. Let's say that I wanted to let you count words in files. Okay? I say, hey, I know how to program Python. I'll send you an email and I'll send you this program. Just stick it into Python and it'll count words for you. Right? You got 1 million words, 1 million lines in a file. You want to find the most common word. And so here we go. So I will send you this file called words.py. I spend a little time. It's a friendly gift to you. And this is what I type in. Now I'll give you kind of an outline of what this is going to do. The first thing it's going to do is open a file and read it. Then it's going to split the lines and files into words based on the spaces. Then it's going to run through and accumulate numbers. Like, you know, this word is 1, this word is 1. Oh, I saw that one again, so I turn that to 2. That's what this does. It's a loop. It goes round and round and round, one for each word. Then what we're going to do is we're going to write another loop that's going to figure out which is the most common word by looking through all those little histograms that we built up. And then it's going to print those things out at the very end. And this can certainly do Python words.py and read clown.txt and tell us that the word the occurs 7 times. But, you know, it can find out that a different thing has the word to and occurs 16 times. And it's just as fast. And it's so yeah, you have to learn a language and you have to tell it what to do. But once you do, it'll do it for 1 million or 1 billion words and be happily. And so you don't have to do menial work once you understand the way to instruct the computer to do menial work. So we always start all programming classes with hardware architecture. I don't think it's essential, so don't get too excited about it. It's a good use of terminology so we can have some words. I can say like CPU and you don't freak out, or memory, or RAM, or a disk drive, and you don't freak out. I don't want to turn you into a hardware nut. I just want you to kind of have a few words so we can talk about what's going on inside, because in a sense we're going to be writing programs to do stuff, both data, instructions, etc. So here's some hardware that I just bought a couple of weeks ago and I'm really in love with, and that is the Raspberry Pi. This is a single board computer. It's got storage on an SD card right there. That's the operating system and the data. And it's got the both a microprocessor and the memory is in here as well. And it hooks up with USB and HDMI and various things. And if you want, in this course, you probably can do all of the homework using a Raspberry Pi if you so desire. So this is what hardware really looks like. It's kind of the inside of something. Normally it's in some kind of case and you don't get to see it. And that's what it looks like. It's kind of got this green and little silver and gold. I think they're very beautiful. They're very pretty. A lot of engineering goes into making these things. And so we kind of have a block diagram of what's going on in here. And there's just some terminology. The brains of it all, well, we draw this block diagram partly because, and here's parts are coming off of this. I don't know what that was. It's okay. It's broken anyways. And if you have a desktop computer, this is more like what it looks like inside. This part is called a motherboard, and it's kind of like the thing that connects and brings everything together. It's got a bunch of wires. Each one of those little lines here is wire. It's covered with sort of a lacquer. And then there are things that penetrate the board and then connect to various chips. And this whole thing is what this picture is, but it really is connecting a number of different components. The central processing unit that I've spoken of before, put that back down, central processing unit is the closest thing a computer has to a brain, but it's barely a brain. It's really just a super fast programmable calculator. We make it flexible by our creativity when we write programs. We make it seem intelligent. It's people that make it intelligent by taking our own knowledge and putting it in, this is not itself intelligent. There's nothing to fear from this. It's just not that smart. So this is the thing that's programmed to ask the question, what's next? And then we have to have a set of instructions that feed this thing really fast, billions of times a second. And that's what this is. This is the random access memory. And we have memory chips, and they're connected together through the motherboard. So we have the main memory, and we have the central processing unit. And this is where our high-speed instructions come from. This is where our high-speed data is stored. And this is the thing that asks what next, and it reads its instructions from here. And you'll see they're kind of like, they're not quite connected together, but eventually they're kind of connected together. Don't feel too bad about this hardware. It's all old, and it's all broken, and it can't be hurt. So the next thing we got is input-output devices. I'll go back to my Raspberry Pi. So the Raspberry Pi has a USB that you can connect a mouse or a keyboard. It has a HDMI that you can connect a monitor to. It has an Ethernet connector. So these are all examples of input-output devices. And then the last thing on the screen is the secondary memory. So this RAM, on the Raspberry Pi, the CPU, the central processing unit, and the RAM are all in this one chip in the middle. It's called SoC, or System on a Chip, where they put more parts there. So in a sense, they've collapsed this, and a lot of this all down in the Raspberry Pi to one little guy. But it's still architecturally the same thing. There's a central processing unit, there's main memory, there's graphics cards, etc. So input-output devices. Oh, and this guy has input-output devices too, like USB and keyboard and monitor, etc. So they're very similar. It's just this is new and this is old. Everything gets smaller when it gets newer. Okay. Okay. So the last thing we got to talk about is the secondary memory. Oh. When the power goes off, these things sort of go away. The data in this RAM goes away. It's just designed to be really fast, but not permanent. So we need a place that's permanent. That's what secondary storage is. That's what this secondary storage is for. This is permanent. This is fast, and it cha-cha-cha-cha-cha really fast. And but this is permanent, and this is slower. Okay? So the secondary memory, I've got two kinds of secondary memory. Oh, dropped it on the floor. Two kinds of secondary memory. I'll start with the Raspberry Pi. The secondary memory of the Raspberry Pi is this SD card. It's like a disk drive. It still is permanent, does not require power to maintain its data. The data stays permanent. So in the future we will see more of these flash style drives and SD style drives. So the Raspberry Pi is kind of alluding to the future. There's a disk drive in here. It's not really a disk, it's also flash memory. But in the old days, in the good old days, back when I was a kid, our secondary memory was a disk drive, and it had platters, and it spun, and it made a satisfying noise, and it would move in and out to read data. And I'll show you a video of this just in a bit. And so these would record the data on the magnetic platters, and then when the power's taken off, the data would still be magnetized. And then it would go and move to the right spot, spin it around, and read the data. And again, this is kind of messed up in a pretty bad way. So, there we go. Central processing unit, brains of the operation. Main memory, fast, but goes away when we power off. Input-output devices, keyboards, etc. And then storage that maintains its data across power cycles. Okay, and I just said all that. Okay, so then the question is, where do you belong in this? Where do programs live? Where do we write? And the answer is, we kind of live in the memory, right? What we do is we put our programs into the memory, and then the CPU pulls the programs out of the memory. So we have to write our programs and put them into the memory. When we start them and run them, we're really loading them into the memory so they can be fed rapidly to the CPU. Now, the computers don't really execute Python, like if x less than 3 print, but that's what we tend to want to write, because what the computers really execute is a thing called machine languages, which is a series of zeros and ones that pretty much translate directly to what's on these pins. There's voltages that go up and down. That's called machine language. Source code, like Python, is written in a way that's most convenient, well, at least more convenient. Machine language is what's most convenient for the hardware. So we have to translate from source code to machine language, and that's what the Python program does for us. We write in Python, and Python translates to machine language for us. So I got a couple of videos that give you a sense of how this all works. We'll start with CPU. And what this is going to do is this is going to show you the intensity of how much electricity. The thing that gets hot inside your computer is this little guy right here. And we're going to see in this video just how hot it can get. Okay, so welcome back. So the next thing I'm going to show you, I showed you a hard disk that sort of didn't work, but we're actually going to show you a real short video on how a hard disk works, that someone took the cover off and actually applied power to it. You don't want to do this yourself if you have a hard drive. I've read, and some people say that you can do it for a few minutes and then the drive kind of destroys itself if you run it with the cover off. So let's take a look at this. Okay, so that's sentences. Now, paragraphs. Let's talk about paragraphs. Paragraphs are the combination of sentences to make sort of a thought together. Multiple sentences, multiple lines. So the interactive Python that I just showed you is fine for running 1, 2, or 5 or 6 commands. But ultimately, we're going to write much longer bits of Python. And so we write what's called a Python script or a Python program, and we put these in a file. And if you went through the prerequisite, you will have seen me edit in a text editor, save the file, and then run from the Python file. Okay? And so we call these files, put .py on the end of them, py on the end of them, and we're giving Python a script to execute. So, interactive, you're typing directly into Python, and it's doing it right as you're talking. You're still doing it in an order, and the order does matter. In a script, you type it all into a file once and say, Python, do it all. Now, when you write one of these things, there are patterns for combining these. There are things that we do to these lines that sort of treat them differently. It's like a recipe, a set of instructions. Start at the beginning, but it's a little more complex than that. Some steps are just sequential. Some steps might be skipped. Some steps we do multiple times. And other times we have kind of like a set of steps we do over and over again. So here's some pictures. And here's 4 lines of Python, a little simple paragraph. And it's got a sentence that says x equals 2, print x equals x plus 2, which says go grab the old value of x, add 2 to it, stick it back in x, and print x. So the output of this program is 2, then 4. Because x was 2, we printed it, then we added 2 to it, and then we printed it again, so it was 4. Now, these flowcharts, don't worry, I'm not going to make you draw these. I just draw these in case cognitively it makes it easier for you to understand what's going on. So, x equals 1 is the first step. Sequentially, it just continues on. It runs the print. X equals x plus 1 runs the print. So this is just straight through. It'll make more sense when we see a little more convoluted things. So this program just starts naturally. Python starts at the beginning and works its way down through the end. That's sequential stuff. That's the normal order of business. Now, a conditional is a step that may or may not get executed. If all we did was sequential steps, programs would be kind of dull, right? They would just be like, blah, 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 stop. So there's things like, oh, what if you do this or what if you do that? And so we do things like, if you have more than 40 hours, I'm going to pay you a different rate than if I have under 40 hours. Those kinds of things are if, the word if. So in Python, the way we express this is we use the keyword if. So we say x equals 5, and then we say, if x is less than 10, this is a question that's being asked. Is x less than 10 or not? Yes or no? If it is, we execute the indented bit. If it's not, we skip it. In this case, since x is 5, we execute it. And then we come back here, and we're going to do another one. if x is greater than 20, well, this turns out to be false. So we skip that. So bigger does not run. That line never runs. So the output is smaller, fini. Now, here we can take a look at it sort of in the picture diagram. We run x equals 5. We ask a question. This doesn't hurt x to ask the question. Is x less than 10? The answer is yes, so we kind of drive down this little path. We print smaller, and then we rejoin the freeway. Is x less than 20? No, so we skip and we continue. So this never gets executed. So you can think of it either way. You can think of it either sort of like Gestalt, say, if this is true, do what's indented. Or you can imagine sort of a little car driving down a highway, making turn choices as it goes. They're equivalent. Over time, it's probably, you'll just start seeing this and start thinking this way, but sometimes it helps to think about it this way for a little while. Okay. Now, the next thing I want to show you is repeated steps, steps that happen over and over and over again. Okay? And that again, when I said, oh, computers are good at handling a billion words, well, that means it has to have a loop or a repeated section, one for each word. It's going to do something for each word. And so, here we go. And in Python, let's pick a different festive color. Let's pick purple as a festive color. So here's our program. Starts at the beginning, sets the variable n to 5, and then a keyword, reserved word while. While n greater than 0, again, this is asking a question. This is asking a question. Is n greater than 0? That's a question. If yes, we're going to do this. If no, we're going to do that. Over here, if it's true, we're going to execute the indented part and then come back and do it again. If it's false, we're going to skip down. So it's kind of like an if, except it keeps doing it over and over and over again. So it comes in, sets n to 5. Is n greater than 0? Yeah, sure. So we print n, out comes 5. Then it says n equals n minus 1, so n becomes 4. We can change colors. Then it goes back up. Goes back up and asks the question again. N is 4. It's still greater than 0, so it comes through. Prints out 4, subtracts 1, so n is now 3. Goes back up. Is n 0? Is n greater than 0? Yes, it is. Print out 3. Subtract 1. Now it's 2. So out come 3 and 2. Then it goes back up. Still greater than 0? Yes, it is. Print out 2. Or wait. Now it's 1. Now we subtract 1. It becomes 0. Is it greater than 0? No. And we finally leave. And we finally drop down. And so the last thing that comes out is the print of blast off. So this is a loop. The notion that we're going to run this little bit of code 5 times. Excuse me. We're going to run this little bit of code 5 times. And loops have these things we call iteration variables. And that is this n. It's a variable that specifically is changing each time it goes through the loop. And that way we can sort of control the loop. We can decide when it starts and when it stops. We can tell if we're at the beginning or the end, or the first one or the last one. We'll do a lot of stuff with loops. This is an iteration variable because we repeatedly iterate through the loop. Okay? Any questions? Can't do questions. Okay. So now, if we go back to the little story that you got several chapters to understand. Don't worry. You actually got like through chapter 9. So don't try to understand this program right now. I'm just trying to give you a sense of what the picture is going to be, right? So here are some sequential statements because they aren't indented. Those 5 lines are sequential. They just go one after the other. Then we have 4, and it's indented. This is a loop. This is going to run a bunch of times. Then we're done with that. We do some more sequential stuff. Now we have a for loop, and that's going to run a bunch of times. And then we have an if, which may or may not run. So this little block of code is conditionally executed based on something, and here's the question that we're asking. So that's the question. And then at the end we do a print. Now again, don't try to make too much sense of this. I'm just trying to show you sequential, repeated, repeated, conditional. Okay? Just those concepts show up in pretty much every program that we build. So, let's do a couple more little exercises that get you sort of in the mindset of being a programmer and how programmers tend to have to think about problems a little bit differently. So here we go. I call this an animated short story. And your job, I'm going to give you several sets of numbers, and I want you to find the largest number in the list of numbers. Now, it's not so important to know what the large number is, but also to think about how your mind attacks the problem. What your eyes are doing, what your mind is doing, how you break a bigger problem down into smaller problems, how a human solves this problem. And then we'll focus on how a computer might have to look at the problem differently. Okay? So don't just like get the answer. That's not so important. Think about how you get the answer. So don't just like scroll ahead in your YouTube and cheat and go get the answer. Think about actually solving the problem and then monitor what your brain is thinking as it goes. So here we go. So I'm going to give you a list of numbers, and you are to tell me what the largest number is. Ready, set, go. I didn't make it easy. You're looking for the largest number. Did you get it? Did you get it? Did you have to go back a couple of times? Actually, I don't care what the answer is. The question is, how was your brain solving? Okay, you probably want to know what it is. The answer is 198. That was the largest number. Of course, what I was doing is I was moving it to make it difficult. But here's the thing. How do humans look at this? Like, do humans did you look at 25, then you looked at 1, then you looked at 114, and did you just look at them slowly one at a time, like this? Or no? I doubt it. If you are, maybe you're a computer. Maybe I'm talking to computers. Maybe you're all computers. I'm certainly not a computer. Maybe you're all computers. Okay, enough of that. No, that's probably not how you did it. What you probably did was you had your eyes move around the whole thing very rapidly, and the first thing that you figured out is that there were one-digit blobs. There were small, medium, and large blobs of purple. And the first thing you knew right away was there was no point at looking at any of the small blobs. Your brain just threw the blobs away really quick. Then you say, okay, given that there's no 4-digit numbers, they're 3-digit numbers. Then what you probably did is you started looking for the first digit. You say, look, there's some 1s. Is there any 2s? Quickly you decided there are no 2s. So you knew that you had to look for the big blobs, and the second digit was probably the thing that mattered. Then you start getting to the 9. You say, okay, there's some 9s. So that means it's 19 something. Then that was the part that you probably had to go check to find the, oh, where the heck was the 190? Oh, 198 right there. Yeah, I color-coded. I couldn't even see it. Okay? But the point is humans are great at eliminating sort of bad solutions really fast. And you probably looked at how much purple was on the screen, eliminating the areas that were less purple because you knew that your brain quickly and instinctively knew that the more purple meant a larger number. Computers don't do any of that. They don't do any of that. So, in order to make you feel a little more like a computer, I have another test. And again, the goal is not just to find the largest number, but to monitor as you go what your brain is thinking while you're doing this. Okay? You get it? How are you attacking the problem? What is your feeling as you're attacking the problem? Are you a computer or not? Here we go. I'm only going to give you a few seconds. So, what did you get? My guess is that most of you just said, I don't care. This is such a hard problem. It's a stupid problem, or I'll try and turn my head upside down, or something. It's a really hard problem. The other one was kind of easy. Not that you might not have got it, but you had this natural instinct that allowed you to approach the problem. Okay, I'll show you what the right answer is. The right answer is right there. It is 197. Yay. Right? You can't even if I tell you, it's, there you are. What is this? Is this 500 or 200? Actually, the only way I can do this is I flip it to find it. I mean, it's just not what humans are good at. This is a little bit more like how computers see the world. But the fact that the data is frontwards or backwards should sort of make no difference, right? Computers need a strategy. We need to give them a strategy. Okay. So here we go. One last experiment. Now, I'm going to show you numbers one at a time. And at the end, I want you to tell me what the largest number that you saw was. Ready? Here we go. First number. What was the largest number? As a matter of fact, how did you solve that problem? You solved that problem most likely because you couldn't look at all the numbers at the same time, so you probably created a variable in your head without even knowing it. And you put into that variable, you called the variable the largest number I've seen so far. And you hadn't seen any, so let's say the largest number you've seen so far is -1. Then I showed you 3. And you said to yourself, well, -1 is no longer the largest number I've seen, so I'm going to keep that one. I'll keep 3. That's the largest I've seen so far. And now I see 41. 41 is larger than 3, so I will keep that. And now I see 12. Now 12 is crap because it's nowhere near as good as 41, so I'm keeping 41. 74, 9. 9, not nearly as good as 41, so I'm going to throw that one away. 74, better, keep it. Keep that one. So I'll keep 74. And the last number is 15. Don't even know it's the last number, but we don't want to keep that one. And so now we're done. And so we know that at the end, what was during the loop the largest so far is the actual largest of all the numbers. And we don't remember exactly how many numbers there were. So that's kind of like thinking like a program. You have this kind of sliding window. It didn't matter if I gave you 1 billion numbers or 5 numbers. I think there were 5 numbers, actually. This notion of the largest so far is a powerful notion. As a matter of fact, it's central to the program I've been showing you. Now, I don't want you to try to understand this, but this part in the purple, is really saying, I'm going to loop through the counts of all the words. So it's got a word like the is 15 times and clown is 4 times, and it's going to look through all the pairs of word value combinations. And it's going to basically say, I'm going to go through the counts that I have, and I'm going to check to see if the count I'm looking at is bigger than the biggest count I've seen so far, and if it is, I'm going to remember it. Now, don't worry about this. We haven't even covered any of this stuff. That's what chapter 2, 3, 4, 5, 6. But this is an algorithm, a paragraph, a pattern that allows you to find the largest number. And we'll look at this again in great detail in upcoming chapters. So this is kind of thinking like a computer, having a sliding window across a long list of numbers and coming up with something that is the answer that you need. Okay, so that's the end of this lecture. Read chapter 1, write your Hello World program. Make sure if you haven't, get Python installed. As you read this chapter, and even as you install Python, and even as you write the first program, don't get too stuck on the details. I was confused for like 8 weeks, or probably 6 weeks in my first programming class. You'll be confused too. Just sort of wander through with me. Keep at it. It will start making sense at some point that's up to you. I can't tell you when it's going to make sense. So don't sort of stare at everything until you get it. Just kind of keep digging in and keep understanding and keep playing. And sooner or later, this will make a lot of sense to you. I promise you. See you next lecture. Hello, and welcome to Chapter 2. Hope you enjoyed Chapter 1. It was one of the longer lectures, trying to motivate you a little bit. And now we're going to kind of go back to the basics. The Chapter 1 covered sort of the first 4 to 5 chapters of the book. So, as always, this video, these slides are copyright Creative Commons attribution, as well as the audio. And so, now we're going to talk about sort of the really low-level things that make up the Python language. Constants. So, and some of this is terminology just so I can say the word constant and you won't freak out. Constant is, as contrasted with something that changes, is variable. We'll talk about variables in the next slide, but for now, constants. Constants are in things that are sort of natural and instinctive, things like numbers, 123, 98.6, or hello world. And so in what I'm doing here is we're using the Python interpreter, and that's how you can tell the chevron prompt. And I'm saying print 123, and then Python responds with 123, print 98.6, Python responds with 98.6, and print single quote hello world single quote. So the constants are the 123, 98.6, and quote hello world quote. So these are things we can use either single quotes or double quotes to make strings. And so programs kind of work with numbers and work with strings, and we have these non-varying values that we call constants. So the other side of the picture is the variable. And the way I like to characterize a variable is it's a place in the memory of the computer. We give it a name as a programmer. We pick the variable name. In this I'm saying x equals 12.2 and y equals 14. I am choosing the name and I'm choosing what to put in there. This is a statement called an assignment statement. And the way to think of the assignment statement is that it sort of has a direction. We're saying, dear Python, go find some memory. I will use the label x later to refer to that memory, and take the number 12.2 and stick it into x. Then, this is sequential code. Then the next thing I want you to do is I'd like you to go find some more memory, call it y. I will call it y later. And stick 14 in there. Okay, and so that ends up sort of with two little areas of memory. You know, one labeled x, and here's a little cell in which we'd like a drawer or something, and one labeled y, and we have 12.2 after these lines run. We have 12.2 in one and 14 in the other. Then, for example, if there's another line that's down here, so there's this third line after this has happened, x equals 100. Remember, this has kind of got a direction to it. Say, oh, remember that x that I had? You know, I would like now to put 100 in that. So as I'm thinking this through, I think of that as sort of removing the 12.2 or overwriting the 12.2 and putting 100 in its place. And so at the end here, x is left with 100 and y is left with 14. So these variables can kind of have one value in them, and we can look at them and we can reuse them and put different values in if we want. There's some rules for naming your variables. Again, you get to pick the variable names. Often we pick variables that make some sense. We'll talk about that in a second. In Python, variables can start with an underscore. We tend not to, as normal programmers, use those. We let libraries use those. It has to have letters, numbers, and underscores, and start with a letter or an underscore. Case matters. So spam is good, eggs is good, spam 23 is good because the number is not the first character. Underscore speed, that's also perfectly fine because it starts with an underscore or a letter. 23 spam starts with a letter, starts with a number, so that's bad. This starts with something other than a letter or a underscore, and you can't use dot in the variable name. It turns out the dot has meaning to Python that would confuse it. And wouldn't understand what we really mean there, and so that would be a syntax error. Because case is sensitive, that means that things like all lowercase spam is different than uppercase S and all uppercase. These are three distinct variables that are unique. Most people don't choose variables that might be so confusing. So this, to you as you write it, and as to anybody that might read it, would find three variables named as very confusing. So it's a bad idea. Don't do it. But I'm just showing you as an example that case can make a variable name distinct. And again, this variable is a place in memory that we are going to store and retrieve information, whether that be numbers or strings or whatever. These are things that we control. Now, Python also has a set of reserved words, and what it really means is you can't use these for variables. These words have very special meaning, and, for, is, raise, if. So you can't make a variable named if. It'll be like, oh no, that is if. I know what if is. And so these are words that Python has as its core vocabulary and forbids you to use them for other purposes like variable names or later function names. So that's kind of the vocabulary: constants, variables, and reserved words. Now, we take these and we start assembling them into sort of sentences, statements, Python statements that do something. So we've already talked about an assignment statement. It has kind of an arrow here. It says, hey, Python, go find me a place called X. Take the number 2 and stick it in there for later. Then continue on. Now, because there's an arrow, the right side of this is done first. And so it said, so this right side, you can kind of ignore for the moment the left-hand side, and it calculates the right-hand side by looking at the current value for X, which happens to be 2. Then it adds these two things together and then gets 4. And then at the point where it knows 4, that this number is 4, it will then store that back into X. And so then later we print X and we will get the 4. And so again, this is a sequence of steps, and the variable X changes as these steps continue. And when we're saying print X, that really means print the current value for X. So we can do a number of different operators in assignment statements. We calculate this right-hand side. This is sort of all calculated, whatever this is, based on the current value for X, does this calculation, and then when it knows what the answer is, it assigns that into the variable that's on the left-hand side of the assignment statement. Again, calculate the right-hand side completely and then move it to the left-hand side. Some early languages actually didn't use the equal sign for the assignment operator, this assignment operator, and in a way it kind of, get a good color here. Some languages, an early language, actually used an arrow. Arrows aren't really on people's keyboards. Another language used colon equals as this assignment operator, but we use equals. Now, if you're familiar with math, this can be a little confusing, like x equals 1 and then x equals 2. That, as mathematics, would be bad math, because in a proof or a problem, x can only have one value. But in programming, if this was two statements, that means just x had a value and then the value for x changed later. Okay, so just kind of go through this. Because it's working from the right-hand side to the left-hand side on assignment statements, it is pulling out these x values. So x may have 0.6. It pulls the values out before it's sort of ignoring this part right here, and it's just going to try to resolve this expression. And it has multiplication in parentheses and things like that. So it basically pulls the 0.6 into the calculation, does the 1 minus x, which gives you 0.4. Then it multiplies these three things together, giving 0.93. And then when it is all done with all of that, it takes that 0.93 and then puts it back into x. And so this is just sort of emphasizing how the right-hand side is computed to produce a value, then it is moved into the variable, and that is why you can have sort of x on both sides, because this is like the old and this is the new. This is the old x participates in the calculation, and then when the calculation is done, it becomes the new x. Hope that makes sense. So this on the right hand side here is a numeric expression. So we have a number of different operators. Some of them are instinctive, intuitive, the plus and the minus. The reason some of these are so weird is in the really old days we didn't have too many things on the keyboard, and a lot of programs were very mathematical. And so they figured out what was on the keyboard of the computer equipment of the day, and then they had to fake certain things. So it turns out that plus and minus were on the keyboard, and so plus and minus are addition and subtraction respectively. There was no kind of times operator for multiplication, and dot was used for decimal points, so they used asterisk for multiplication. So in computers, languages, nearly all of them, they basically use times for multiplication. Slash is used for division, so we say like 8/2, which is 8 divided by 2. Raising something to the power, like 4 squared, that is double asterisk. And then remainder is if you do a division that gives you the remainder rather than the divisor. So 8/2 is 4, remainder 0. So the remainder is what you get with this particular operator. There's a few cool things that we can do with remainder that we won't talk about right away, but it's there. And so here's just a couple of sample expressions. Let's give me green. Okay. So again, I'm using the Python interpreter, so you can kind of this is just the prompt. These chevrons are the prompt. Create the variable xx and assign it to 2. Retrieve the old value in an addition, then print it out, put it back into xx, so xx has 4. Yy, this is a multiplication. 440 times 12 is 5,280. Yy over 1,000. Now this is a little counterintuitive. This, because yy is an integer, it then does it in a truncated division, and so 5,280 divided by 1,000 is 5. Now, if so that's an integer division. We'll see in a second about floating point division. Now we take the variable jj and we set it to 23, and now we're going to use the modulo or remainder operator to say what is jj, what is the remainder when we divide this jj by 5. And so if you think about this, we take old long division, 23 divided by 5, you end up with 4, and then remainder 3. The modulo operator, or the percent, or the remainder operator, gives us back this number, and so that's why kk is 3. It is the remainder of 23 when divided by 5, or the remainder of the division of 5 into 23. And the raising to the power, 4 cubed, no, that's not so nice, 4 cubed is 4 star 3, and so that ends up being 64. So that's just operations. Now, just like in algebra and mathematics, we have rules about when to which operations happen first. In general, things like the power happens before the multiplication and division, and then the addition and subtraction happen. And so there are some rules that when you're looking at an expression and trying to calculate what its value is, if you don't have parentheses, it follows these rules. And so the rule that sort of trumps all the rules is that parentheses are always respected. So a lot of us just write these with parentheses in place, even sometimes though you don't need it. Then after parentheses have been handled, then it does exponentiation, then it does multiplication, division, and remainder, and then it does addition and subtraction, and then when all else being equal, it just works left to right. So let's look through an example. So here is a calculation that is, 1 plus 2 times 3 divided by 4 over 5, and the question is, what order does this happen? Okay, and so let's sort of take a look at this. And so we start with, are there any parentheses? And the answer is no, there are no parentheses. So let's go next. Power. And so the power says, okay, let's look across and find those things that are raised to a power, and the 2 cubed, or 2 to the third power, is the power. So we're going to do that one. Okay, and then we can, the way I do it when I'm sort of doing these slowly is I rewrite it. So the 2 to the third power becomes 8, so it's 1 plus 8 over 4 times 5. And then now we can say, oh, power, that's taken care of. Now we're going to do multiplication and division, and we go across. Now we have both a division and a multiplication. Okay, and multiplication and division are done at the same time. So that means we do left to right, which means we do the first one that we encounter first. And so that will be 8 over 4 because of the left to right rule. And so we find that one, and that's the one that gets computed next. And that turns into 2. And again, I like to rewrite these expressions just to keep my brain really, really clear. After a while, you just do it in your head. But I rewrite them when I was first learning it. At least I rewrote it all the time. And so next, looking at this, there's a multiplication. We're not done with multiplication yet. So the 2 over 5 is the next thing. And then we do that calculation, and that becomes 10. And again, we rewrite it. And now we've done the multiplication. And we're going to do addition next, and that's just 1 over 10. And that becomes 11. And so basically, this big long thing, through a series of successive steps, becomes 11. And indeed, when we print it out, that's what we get. Okay? So there's the rules that are parentheses, power, multiplication, addition, and then left to right. But smart people usually just put parentheses in. You know, so here's an exam. Oop, go back. Here's an exam question. Now, I wouldn't write this code, right? I wouldn't write this code this way. I would put a parenthesis here and a parenthesis there. It's the same thing, because that's exactly, the 2 times 3 is going to happen, and the 4 over 5 is going to happen, and then the plus and the minus will happen left to right. But why not make it easier on your readers and just put the parentheses in? Because they're redundant, they're not necessary, but away you go. Now, if you don't want it to happen in that order, of course, then you have to put parentheses. If you want the addition to happen before the multiplication, then you have to put parentheses in, which you can. But we tend to recommend that you use more parentheses rather than less parentheses. Now, Python integer division in Python 2, which we are using Python 2 for this class. There's a new Python 3 that the world is slowly transitioning to, and a lot of people are using it and teaching, but it's not as common sort of in the real world with libraries and utilities. And so we'll stick with Python 2 for a few more years until Python 3 really kind of turns the corner. It's nice to have it there, but there's so much Python, and it's so popular, Python 2, that it's just kind of hard to get everybody up to Python 3. So in Python 2, integer division truncates, and you saw that before, where I did the 5,280 by 1,000, and I got 5 as it. But we can look at a couple of examples that make this really quite clear. So 10 divided by 2 is 5, as you would expect. 9 divided by 2 is 4. Not exactly what you'd expect. You kind of expect that to be 4.5 instead of 4. But in Python 3, it will be 4.5. But for now, in Python 2, 9 over 2 is 4. And 99 over 100 is 0. Now that seems rather counterintuitive, but it is a truncating division. It's not a rounding division. It's a truncating division. Now, interestingly, if you make either of these numbers have a decimal, make them what we call floating point numbers, then the division is done in floating point. So 10.0 over 2.0 is 5.0. Now, these are different. This is an integer number, and this is a floating point number. It's 5.0. And then 99.0 over 100.0 is exactly as you would expect, and it's a floating point number. So now you can also mix integers and floating point numbers as you go. So here we have 99 over 100. Those are both integers, integer, integer. And that comes out with 0 because it's truncating. Now if we have an integer and a floating point number, 99 over 100.0, then that comes out as 0.99. And either one, if we have 99 over 100, that's a floating point and that's an integer, we still end up with a floating point. So this is a floating point, floating point. And even in complex expressions, as it evaluates, when it sees an integer, so the first thing it would evaluate is this would become a 6. So it would be 1 plus 6 over 4.0 minus 5. Then it would be doing this 6 over 4.0, and that would be 1.5. 1 plus 1.5 minus 5. And so this is an integer, and that's a floating point, and the result becomes a floating point. And then the rest of the calculation is done floating point to the point where the ultimate is a floating point negative 2.5. So you can throw a floating point into a calculation, and as soon as the calculation touches the floating point, the remainder of the calculation is done in floating point. Kind of converts it to floating point, but it doesn't want to convert it back because it considers floating point sort of the more general of the representations. Here we are talking about integers and floating points. These are a concept in programming languages and in Python called type. Variables and constants have a type. We can see that if you say 1 versus 1.0, they have different, it works different, it functions differently. And so Python keeps track of both variables and literals/constants and having them have a type. And we've seen this, right? Now the interesting thing is Python is very aware of the type and can use the same syntax to accomplish different things. So if we look at this line here where we say dd equals 1.4, well, it looks at the 1 and looks at the 4 and says, oh, those are two integers. I will add those together and give you a 5. So it gives you an integer, and an integer comes back. Okay? And then EE equals hello plus there. Well, these are two strings, hello and there. And it says, this must be a concatenation. Right? So I'm going to concatenate those together because those are strings, and I know how to concatenate strings, and that's kind of like string addition, right? And so we see hello there as a result. Now the interesting thing is, where did this space come from? Let me change colors here. Where did that space come from? Well, the plus does not add the space. There's a space right there, and that's the space. So I concatenated hello space plus there, and that's how I got hello there. But the key thing is this plus operator, clear. This plus operator looks to either side and says, oh, they're strings. I think you mean concatenation. Here, it looks either side and says, oh, those are integers. I think you mean addition. So Python is very aware of type, and type informs Python what you really mean. And so it looks like those are kind of the same, but they're quite different operations. So the type can get you in trouble. Remember, Python is looking at the type. So here we have a little problem. Our first traceback. First of many tracebacks. So here we have EE, which is hello there, which is exactly what we did. This is a string and this is a string, so EE should be a string. And then we try to add 1 to it. And again, Python is saying, oh, I see a plus sign here. So I'm going to look over here, yeah, that's a string, and we'll look over here and that's an integer. It's like, ah! And this is a traceback. Now, here's a good time to talk about tracebacks. Tracebacks, I color them red because you might think that Python dislikes you or thinks that you're, unworthy of its brilliance. And certainly the way these things are worded, it sounds like, you're being scolded. It's like, hey, type error, you cannot concatenate stir and int objects, right? I'm scolding you. You're bad programmer. And it does feel a bit like you're scolded. But if you go back to Lecture 1, this is also the moment where really we shouldn't think of this as like scolding. We should think of this as Python sort of asking for help. It's like, wow, you gave me this line, and I, Python, have no idea. In all your greatness, could you give me some possible clue as to what you really mean for me to do, because I'm so lost, and given that I'm Python and I'm lost and you are the only purpose for my existence, I must stop until you give me better guidance. So don't look at tracebacks as scolding. They sound like scolding. I'll stop coloring them red after a while. So if Python is so obsessed with the type of things, you should be able to ask Python what the type of something is. And so there's a built-in function called type. This is part of the Python language. Type parenthesis, and you can put a variable in here. What's the type of the variable EE? And it says, oh yeah, I know what that is. That would be a string. And then you can also put a constant in here and say, what's the type of quote, hello quote? And that's a string too. And what's the type of the number 1? Well, that would be an integer. So it's picky about the type, but it'll also share with you what it believes the type is. And there's several types of numbers. As I've already mentioned, there are integers, which are the whole numbers. They can be positive and negative and 0. And then there are the decimal numbers, the floating point numbers, like 98.6 or negative 2.5 or 14.0. Python knows these as well because it does division different if it's presented with 2 integers, or an integer and a float, or a float and a float. And so here we have x is 1, and we say, what is it? It's an integer. And we say it's 98.6, and we say, well, what's that? It's a float. And you can ask for both variables and constants. So what's the type of 1? It's an integer. And what's the type of 1.0? And it's a float. You can also convert types. It has a bunch of type conversion functions built into it. So there's implicit conversion going on when you're sort of saying, divide an integer by a floating point. It says, okay, I look to the sides and I will make the conversion for you. But you can also be explicit. So in this case, we're going to say, take this 99 and convert it to a floating point version of itself, which is 99.0, and then do the division. So Python looks out here and goes, oh, after that's a float, and that's an integer if I look over here, and then that means that the result is a float, and the division is done as a float. So we are force converting the 99 integer into a 99.0 float. And we can even do this and just stick it in a variable. So we can put 42 in I, and that is an integer. Then we can say, hey, convert float that I into a float and stick it into the variable f. And so we can print it. And now it's 42.0 instead of 42. Right? They're not the same. They're both kind of 42, but one is a floating point 42 and the other is an integer 42. And we can ask, and that is a float. And you can also do the same thing in the middle of a calculation where you have 1 plus 2 times float of 3. This float is done quickly. So the first thing that happens, this is 1 plus 2 times 3.0, 0.0 over 4 minus 5. So the first thing that happens is these floats are done because they're parentheses, so they matter. So this is a built-in function called float that takes as its argument a non-floating point number and gives you back a floating point number. We'll talk more about functions in chapter 4. You can also convert between strings and numbers. And if you recall, we did the example where we took a string. In this case, I'm being a little confusing because I'm making a string with the characters 1, 2, 3. Now this is not the same as 123. This is a 3-character string with 1, 2, 3 in it. And I can ask what kind of thing is in there, and it says, oh, there's a string in there. I know about that. And then I can try to add 1 to it. And it seems intuitive that, quote, 1, 2, 3 plus 1 would be somehow 124. But it's not. Python takes a look at the plus and says, oh, there's a string on that side and an integer on that side. I am going to freak out and tell you that you cannot concatenate a string and an integer. Okay? But there is an int function that converts various things, including strings, to an integer. So we can give as its parameter, its input, the string value, then it converts it to an integer, and then we'll put the result in the variable ival. We can ask what the type of that is. It's a integer, and now we can use it in an expression, print ival plus 1, and so now Python looks to both sides, sees an integer, and gets 124. Voila. Now, if I make a new variable and I stick hello Bob in it, and I say, hey, let's convert hello Bob to an integer, as you might expect, it blows up. And it says invalid literal for int. These tracebacks, again, once you kind of get used to the kind of harsh wording of them, because they're not saying sorry, comma, they're trying to tell you what's going on. So cannot concatenate string and integer, and invalid literal for int. It's trying to be as helpful as it possibly can be to give you a clue as to what to fix. So again, not scolding. Okay, so that's variables and types and type conversion. Now we'll talk a little bit about user input. And there's a function that's built into Python called raw input. And what happens when raw input runs is it has as one of its parameters a prompt, which is something that shows up on the screen. Who are you? And then it waits, sits and waits. It says, what next? And then you type a string, and then you hit the enter key, and then whatever you typed here goes into a variable. And it is a string, and then you can use it. So I'm going to print the string welcome, comma, so that means I'm printing two things now. The comma adds a space between welcome and then nam. And so welcome is a literal, and then Chuck is coming from this nam variable. So this is a two-line program. And I think this is one of your assignments, actually, to, well, it's one of the exercises in the book, to prompt for a user's name and then welcome them. Okay? So raw input is a function that issues a prompt, waits, and then takes whatever string that's entered and then returns it and then puts it into that variable. So now we're going to create kind of the first useful program. It's not a powerful program. It is an interesting problem of the fact that for some reason there's a difference in the numbering scheme of United States elevators and European elevators. European elevators, the floor that you walk out on is the 0 floor. The floor above that is the 1 floor, and the floor below that, the basement, is the -1 floor. And so you walk in and you can either go up the elevator or down the elevator. Of course, in the United States, the floor that you walk in is the 1, and then there's the 2 floor above that, and then there's like the basement. So this is the imagination that the Americans have as to how to number floors. Right? The Europeans go 0, 1, -1. So children who go to hotels learn instantly the notion of 0 and the notion of positive and negative numbers and the symmetry between positive and negative numbers. I mean, I just wish the United States hotels would switch to this to teach young people 0 immediately and negative numbers. So we somehow think that numbers all in the United States start at 1, and then there are no negative numbers. There's the basement. I wonder why that is. But whatever. For people who travel a lot, they may be confused by this. They need a way to convert back and forth between the US and European numbering system. So this is a simple program that demonstrates a real classic pattern of input, processing, and output. It's just 3 lines, but it has the essential things that all programs that are useful, they generally read some data, do some work with the data, and then produce some kind of results. And so the first line is a raw input that effectively puts out a prompt, and then it waits. It says, please enter your Europe floor. It sits there. We type a 0. Then 0 goes into imp, but it is a string. It's not a number. It is a string. So we can't add to it. But we can take and convert it to an integer with the int function. Int of imp. That's a string being converted to an integer. So now it's a real numeric 0. And we can add 1 to that. And we sum that together. And we put it in to the variable USF. And then we print US floor, comma, and then whatever the variable for USF is. And out comes US floor 1. So we've written a very simple elevator floor conversion from a European floor to a United States floor. Don't ask about negative numbers. It's not really good at that. But from 0 and positive numbers, it works great. So another thing to think about in any programming language is comments. Comments are like commentary, and basically it's a way for us to add notations for ourselves or for other humans interspersed in the code. And so in Python, anything after a pound sign is ignored. You can have a pound sign at the beginning of the line and then the whole line is ignored. There are 2 or 3 reasons why you can do this. One is sort of like paragraph headings, where you can say what's going to happen in English or your language. And you can write documentation that says this code was written by Charles Severance, December 2010. And you can also just hide a line of code to test and turn it on and off without actually deleting the line of code. It's a real common thing in debugging. So for example, here is the program that we've been playing with. This is our word counting program that we've been talking about from the beginning. And here is an example of 4 comments. 1, 2, 3, 4. 4 comments that basically tell us what these paragraphs are going to do. Now, they don't have any effect on the program whatsoever. But this one says, get the name of the file and open it. Kind of helpful, right? Count the word frequency. That's what this little bit does. Find the most common word. That's what this little bit does. And all done, print this out. So it's really can be very helpful just to add a little tiny bit of stuff. You don't want to overuse comments. You don't want to say like x equals 12. Take 12 and put it into x. Sometimes people teach you and try to say, oh, you need one comment every 3 lines. I don't believe in any of those rules. I basically say, if it's useful to describe it, then describe it. So that's comments. So some operators apply to strings. We've already talked about plus. It's kind of silly, although useful in places. You can actually multiply strings, where this is the asterisk looks and says I got a string and an integer, and it prints out the string 5 times. Not a lot of use for that. Now, let's talk a little bit about choosing variable names. This is something that is really confusing. So I said like x equals 1, x equals x plus 1. What does x mean? And the answer is, it doesn't mean anything. I chose it. I wanted to make a variable, and so I picked x. We pick x a lot, probably because we learned in algebra in 6th grade that x was a variable. So, and it's short, and so why not call it x? But as your programs get larger, this gets kind of frustrating to have all your variables like x and y and z. And so the notion of mnemonic, it means memory aid. We choose our variable names wisely so they remind us of what the variable's going to do internally. And so as I go through this lecture, in the beginning, if I choose a variable that's too clever, you're going to think that it's part of the language. And so I sort of switch back and forth between well-chosen variable names and stupid variable names to kind of re-emphasize the notion that I can choose. Mnemonic is a good practice. Okay? So here we go. Let's take a look at a bit of code. So the question is, what is this code doing? What will it even print out? Is it syntactically correct? Now you could probably cut and paste this into Python and figure out that it is syntactically correct. There are 3 variables. This one here and this one here match. This one here and that one there match. And these 2 match. So it's taking these 2 numbers and multiplying together and then printing out the product of the 2 numbers. If you're real careful and like look at every character. Now, this would be called non-mnemonic variables. They're really messy. Now Python, it's happy because all it wants is to say, oh, here's the name that I, the programmer, decided I wanted to call this piece of memory, and I'll refer to it down here. Okay? And so Python's happy. Now, if you hand this to another human being, they're going to be really unhappy because they're going to be like, what are you doing? So one better way to write it would be to make the variables very simple. And then cognitively, we humans can figure out which is which. Because again, it's still only about matching. The A has to match the A, the B matches the B, and the C's match. It's actually the exact same program. A equals 35, B equals 12.5, C equals A times B, and print C. It is these, Python sees these as the same program. It doesn't care what we name them. Now a human will be much appreciative If you say, here, you can either have this one or this one will make them a lot happier. Woo. Okay? So that is certainly cognitively easier, but it's not really giving you any sense of what's going on here. Right? So an even better way to write this exact same program to do the exact same thing would be to choose variables named hours, rate, and pay, if indeed that is what you're doing. Now you can look at this and you go, oh, well, shoot, 35 is the number of hours and 12 and a half is the rate and the pay is the number of hours times the rate. And then we're going to print out the pay. That makes a lot of sense. So this is really a awesome and wonderful characterization. And this, if that's what you're doing, and if those are hours, rate, and pay, it's a great thing to name your variables. But this is where beginning students get confused. And so sometimes I'll write it this way, and sometimes I'll write it this way. Because you look at this until you get a little more sophisticated, a little more skilled, and you say, like, does Python know something about payroll? Is hours a reserved word? Is rate a reserved word and pay a reserved word? Are these things that Python knows about? And the answer is no. Python sees these three programs as exactly the same name. It's just this person really made a very bad choice of a variable name. This person made a less bad choice of a variable name. And this person made a really awesome choice of a variable name. So the only difference between those two things is style. They are the exact same program. And Python is equivalently happy with these. But humans are most happy when the variables are easy to remember and they are somewhat descriptive of what their expected contents will be. That's mnemonic, to help you remember what you were meaning to do when you write the program. This is still a bit cryptic. Having these really short one-character variable names is still a bit cryptic. So, you have a couple of assignments at the end of the chapter. One of the assignments is to write a program to prompt the user for hours and rate per hour and compute pay. So I won't do this here, but just a couple of sort of things. You're going to be using raw input, but remember that hands a string in, so you're going to have to use float, the function to convert it to a floating point number so you can actually do a calculation. And then you're going to have to use multiplication and print. So multiplication and then print. So it's some combination of raw input, float, multiplication, and print, constructed to make your program do exactly this. So this is the end of chapter 2. We talked about types, reserved words, variables, the mnemonic, how you choose variable names. We'll hit this a couple more times because choosing variable names is always problematic. Operators, operator precedence, which just means like does multiplication happen before plus, parentheses. Integer division is a little weird because it truncates, right? 9 over 10, 9 over 10 equals 0. That's the integer division truncating. Conversion, this is like the int, float, and then user input, which is raw input, and then comments, which are ways for you to add human readable text to your program. Okay? See you next lecture. Hello, and welcome to Chapter 3 of Python for Informatics. Chapter 1, Chapter 2, now we're going to get to something kind of programming. I mean, assignment statements and reserved words, that's just kind of gurgling. Now we're going to start seeing composition. We're going to start seeing the conditional execution gets us started sort of seeing the power of computers where you're starting to make decisions. So as always, this lecture and audio, video, and slides are also available. Are copyright Creative Commons attribution. So conditional steps are steps that may or may not be executed. So here's a bit of code. So and I draw these pictures. I won't draw too many of these pictures on the left-hand side. If you've taken a programming class, you may have seen these. They're sometimes called flowcharts. Sometimes people really think these are important. I don't think they're all that important for understanding. The Python code is here on the right-hand side, and this picture's on the left-hand side. And the reality is that this may initially make more sense cognitively to you than this. But this part on the right-hand side is what's important. I like to call these like road maps, so you can sort of trace where the code is going by driving down a little road. That's kind of something that you do once or twice, and then pretty soon you just start reading the code. So I'm going to start on the right-hand side here and just walk through the code. Remember, code operates in sequence. Well, there is a if, which is a special reserved word. It's one of those things that you can't name a variable if. And it is our indication that to Python that the next statement that we're going to do may or may not be executed, if. And the thing that comes on the same line as the if, up to including the little colon, is a question. This is a question. You're asking a question. So an assignment statement is moving a value into a variable, and a if statement is asking a question. In this case, we're asking a question about a variable. So always think when you're sort of here that this is a question to be asked. And you'll notice when I'm doing the same thing over here, I put a question mark there. Is x less than 10? Yes or no? It's a question that has a yes or no. And so the way this works is this statement that's indented after the if is either executed or not executed based on the result of that question. So the way to sort of read this in English is set x to 5. If x is less than 10, which it is because x is 5, then we're going to execute this. So print smaller comes out, and then we come back out and we continue and say, oh, okay, now I have another if statement, and then a block of indented code. If x is less than 20, that's the question. The answer to that is no, and so it does not run that line, and so it runs fini. So the printout of this program is smaller, followed by fini. What happens is this line never executes because the answer to this question is false. Okay? So let's go through that a little faster. Set x to 5. If x is less than 10, print smaller. Then if x is greater than 20, which it's not, skip that, and then print fini. That's the short version of it. Okay? Conditional steps. This step is conditional. This step is conditional. They may or may not be executed based on the result of the question. Now, if we're thinking of this as like a GPS roadmap or something, we can look at this right-hand side. So the CPU comes roaring down here, x equals 5. Okay, I'll run that. Then it's faced with a choice. Is x less than 10? Yes or no? If it is yes, and it is, I will go this way. If it was no, I would go that way. So if it's yes, I go here and I run this little thing and print smaller. Great. And I follow the little road. And now the road takes me to here. And it's asking another question. Is x greater than 20? This time the answer is no. So I'd come down here. Right? And so this bit of code is never executed. Now, this is a very simple example, but you get the basic idea. Okay? So that's conditional execution. Now there's a number of conditional operators that we want to use, just like we had multiplication, division. Some of them are pretty intuitive, and the others you just kind of have to memorize. Like less than and greater than make a lot of sense. The one that probably the easy, like less than or equal to or greater than or equal to, those kind of make sense too. They're less than or equal to, just because we don't have a less than or equal to sign on a symbol or a greater than or equal sign, which we would use in mathematics. Equality, asking the question of whether something is equal to something else or not, is double equal. And that's because we're already using single equals as assignment. So when we say x equals 3, that is an assignment and sticks a value into x. This is the question. Is x equal to? If I was building a language, I would make it be equal question mark or something like that. It'd be like, huh? Is it equal? Kind of a question mark. But that's not what we do. I didn't invent this, so double equals is the question, is something equal to another. A single equals changes something. X equals 5 changes x. Okay, and then not equal, exclamation is commonly used to mean not in computer context. So if something is not equal to something, it is exclamation equal. Here are some examples. Just kind of running through them. They all turn out to be true because I set x to 5. If x equals 5, print equals 5. Come out here. If x is greater than 4, which is true, print greater than 4. If x greater than or equal to 5, yeah. If x less than 6, print less than 6. Now there are two sort of syntaxes to the if statement. One is where the if statement is down here on a separate line and it's indented, and the other is where there's a single line and it's right on the same line. If x less than 6, print less than 6. So this is true, so this whole thing executes. Then it continues down. If x less than or equal to 5, yep, print less than or equal to 5. If x is not equal to 6, which is true because it's 5, then not equal to 6. So all those will turn out to be true, and all those will execute. And so the tricky bit here is, just seeing this syntax for an if statement where it's all one line, and this syntax where you end the first line with a colon and then indent the second line. This you can only do one line. We will soon see that you can put more than one line in an indented block. Okay. Here we have more than one line in the indented block. These are called one-way decisions. And so we say x equals 5. We print out before 5, so that prints out. If x equals 5, remember the double equals is the question mark version of equality. Single equals assignment. It says yes. So we indent, and the convention is to indent 4 spaces, although it doesn't really matter as long as you're consistent. Then it's going to run all 3 of those. Is 5, still 5, third 5. These lines all come out. And then it comes out and prints. And the de-indenting, the fact that this print has been moved to line up with the if, that's what indicates that this little block of conditional executed code is finished. So then it prints out afterwards 5, some more, before 6. Then it asks another question. If x is equal to 6, again, that's the question mark version of it. And if this is false now, because x happens to be 5, so the answer to this expression, the logical expression, is false. Then it skips all of the indented bits, so none of this executes. So since it's false, it skips all of the indented bit, but then this print lines up, and so then it picks back up with afterwards 6. So we call this a one-way decision where you have the question, and then you have a couple of things that you're going to do on this true thing. Or if it turns out that you're false, you're going to skip all those things. So Python is actually one of the few languages that uses indentation as syntactically significant. We like to indent code for ifs, and in a moment we'll see you learn about loops. We like to indent code as a way to make sense of stuff. It makes it easier to read. If this thing's inside, and so it's really quite nice. And then we sort of use it as a matching to help us cognitively understand what's inside of a program. But in Python, it's really, really important, and it's you have to think of like when you are moving in, you mean something, and when you move back out, you mean something. So you can increase the indent, which you do after like an if statement or any other statement that ends in a colon. You increase the indent, and then when you're done, you decrease the indent. You maintain the indent sort of for sequential code. Now, blank lines and comments are ignored. So you can have a blank line and the indentation just goes right past it, and the comments don't affect it. And so while we're here, we'll interrupt us for a recommendation. In your text editor, Notepad Plus or TextEdit or Text Wrangler or whatever you're using, it may be set when you hit the Tab key to move in 4 spaces. Sometimes you also might move in 4 spaces by hitting spacebar 4 times. Python will see that as different, and it is possible in all of these word processors to say, hey, don't actually put tabs in my document. When I hit the tab, put in 4 spaces. Then whether you're hitting the spacebar or hitting the tab, at least you are putting the same thing into your document and not freaking Python out. If you don't, you may get indentation errors. Indentation errors are syntax errors to Python. And what's really frustrating is if it looks good to you in your text editor, you have an if and the block goes in and it comes back out, but one of them is 4 spaces and one of them is a tab, then Python will yell at you. And this is really frustrating when Python yells at you about that. So what I'd like you to do is go into your text editor, whatever it is, into the properties or the settings, and here is, yours may be different, but here is where you set this. Auto expand tabs, that is on the Mac in Text Wrangler, And then in Notepad++, there is replace tabs with spaces, and that's underneath preferences. So you have to find it. Stop right now and go set this so you're not going to make yourself crazy. Okay, so this is kind of a busy slide, but it gives you this sense that you have to explicitly think about indenting and de-indenting. Okay, and so I'm just going to walk through this. So when you have two lines lining up, that means they're going to run sequentially. If you see an if, or later here we'll see a for, we haven't talked about for yet, but it's like if. So the fact that we go from this second line to this third line and move the indent in, we're actually creating a block that has to do with this if. And you can also kind of tell the if and the for end in a colon character. Now, we could pull this print back out, but we want it to be part of the if, so we maintain the indent. And then we're done with the if by pulling out. So we line the P with the I, and that means this is outside of the if. This for, which we haven't learned about for yet, for is another statement that ends in colon, and afterwards you have to indent. Then you maintain the indent. Here's an if. But now we have an if, and we're already in, but that ends in a colon, so we go in farther. And now this is the block. Now, we come back out, and we line up with that if right there. Okay? And now at the end of this indent, this X here, comes all the way back out, so it lines up. The rest of these are kind of weird in that comments don't matter, blank lines don't matter, and so it just is sort of, you have to mentally get used to the notion that these don't count. They can really cognitively mess you up, so these don't count. And now if I look through it with the comments hidden, it starts in column 1, ignore, ignore, goes in, stays in, ignore, 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 comes out. So it all makes sense. Those comments and blank lines are just kind of confusion. So, increasing and decreasing indent has meaning in Python. We'll learn more about this in a bit. Our programs won't get this complex right away, but it's important to think these indents aren't just pretty, they actually are communicating something to Python. And what they're communicating is basically what's in a block. And it shouldn't take you very long when you start looking at Python to sort of visualize these blocks. So here's a big block, this block here that's got these three things. And then this is a block as well, and you can kind of say, well, here's an if statement, and then these are the two statements that are part of that if statement. So mentally, you kind of make these block pictures. So here's another block. This is that for loop. This part's the indented part, but then there's a block inside of the block. So you got to kind of start seeing that as well. So this is a block that has to do, this green block is the one that has to do with the if. And then there's a block here, and then this is a great big block because this is where it finally de-indents. So don't worry about it yet, but at some point you're going to start seeing this indenting and de-indenting as defining blocks of code for various purposes. Now we don't have all the purposes yet, but we'll get there. Hello, and welcome to Chapter 4, Functions, in my book Python for Informatics. As always, these slides and this audio and this video are copyright Creative Commons attribution. Now we are to the point, Chapter 4, we're sort of well into the class, so I figure I should introduce myself a little bit, let you know a little bit. As I said before, I think in the beginning, I'm taping this in a wonderful building at the University of Michigan called North Quad. It's a relatively new building. It's got some residential sections and some academic sections and some classrooms. And one of the classrooms that I typically teach in is actually 2255 North Quad. It's a really beautiful room with great ways for people to interact. And so sometimes I'm teaching, little tiny Dr. Chuck down here with a smile on the face. And sometimes my students are taking my classes on campus, and sometimes students are watching me through lecture. And so this building is really beautiful, and if you ever get a chance to come to Ann Arbor and take a look at it, maybe walk through it, it's really quite nice. One of the things I like about it is that I think it's really highly inspired by Harry Potter. the kind of course, Oxford and Cambridge are the real inspiration for Harry Potter, but our cafeteria, for example, it kind of looks like the four tables in Hogwarts, and you can kind of imagine a snowy owl flying around and sorting hat at the front sorting people. And so the nickname for the place is Quadwarts, because it's North Quadwarts. That's like Hogwarts and North Quad kind of jammed together. And of course, given that we sort of think of ourselves a little bit as Harry Potter, people, when they first come in the September, often sort of decide to sort themselves. And a few years back, when we first started the building, the students decided that I did not get to be in Gryffindor. As a matter of fact, it's probably time for me to show you who I am and who I've been sorted to be. So the students decided that I couldn't be in Gryffindor, that I had to be in Slytherin. And that's because of my name, Charles Severance, and Severus Snape. What's even cooler, of course, is given that I teach Python, Slytherin's house is a snake, right? So makes a lot of sense. I even have this really fancy Slytherin teacup that I use to drink tea during lectures. Sometimes I drink coffee, sometimes I drink tea. Oh, wow, this thing itches. So let me just get rid of it. If I had any hair, that would mess my hair up. So let me get rid of this for the rest of the lecture. So there I am. Okay. Enough of that. Back to Dr. Chuck. So, with that sort of brief interlude, the actual topic of this lecture is functions. And so, storing and reusing is basically an idea that we will often have a series of steps that we will want to use over and over in a program, increasingly complex. The things we'll use in this lecture are kind of silly because I have to keep them short so the slides don't get too long. But a good example of the kind of work is maybe I'm going to use Google's geocoding service, and I'm going to send some unstructured data back and get a GPS coordinate back, and that's a service that I want to call, and it would maybe be about this many lines of code, and I'm going to want to do that all over the place. So do I want to put this many lines of code 40 places in my program, or do I want to put it one place and then call it in the various places that I need it? And so that's why I call it the store and the reuse function. So if we take a look at the simple syntax here, these things are called functions, and some languages are called subprograms, but we call them functions in Python. And the keyword that we're really going to focus on is def, which stands for define. And what happens here is that when Python sees this def keyword, it actually doesn't run the code. It says, oh, you're going to make a function, and you're going to kind of turn on a recorder and start recording this code. So it has a colon at the end of it, so it has an indented block afterwards. And so the indented block becomes recorded. So instead of running the code, like if we just put print hello and print fun, it would run it. But instead it says, hey, don't run it right now. Name it hello. We give it a name. It's kind of like a variable. We choose the name. We've chosen hello as the name of this. Define it as hello. Have it have these 2 lines of Python in it, and we'll use it later. Okay? And so that's the function definition. That's the store phase. That is, it's sort of like, it doesn't really run those lines. It sort of makes a variable called hello that actually contains Python code rather than containing like 12 or a string or something like that we've worked with before. So this is the store part, and then the reuse part is we then have extended Python. We now can call our bit of code. So we say hello. The hello name is what we came up with, parenthesis, and then that says, remember that code that I put in there under the name hello? Run it now. And so if I start looking at that, and then it just continues. So let me kind of clear this and start over again. And so if I watch what Python does from the beginning, is it reads here and goes, oh, you're defining a function named hello. Great. I will sort of remember. I got that remembered for you. Let's continue on. Oh, hello. you want me to run that stuff that you just got done storing under the name hello. So then it kind of goes and runs it, and out comes hello fun. Then after that, it runs to this print, and then out comes print zip. Then we say, you know what, I want to reuse that again. I stored it once, I can reuse it as many times as I want, and now hello, and then these 2 lines of code run a second time. So we stored them once, gave them a name, and then ran them twice in the context of wherever it is we wanted. Now, this is not sort of a profound reason to use it in this. I'm just trying to give you the notion that there is a way to store and name code that then you can retrieve later. That's really what's going on here. So there's 2 kind of functions inside of Python, and we've actually been using them almost from the very first lecture. And that is, there are built-in functions that Python provides to us, like float, raw input, int, those kinds of functions. Those are just part of Python, but we call them as functions. The difference is we don't write them. And then there's user-defined functions, functions that we write, functions that create functionality that we want to make use of, like encapsulating the ability to compute pay for time and a half for overtime. And so we name these things and we treat them as new reserved words that we've created. They're kind of an extension to the language, as it were. So when we're coming along, we define a function with the def keyword, right? The def keyword is a reserved word. It's one of the many reserved words back in chapter 1 that we talked about, and it indicates to Python the beginning of a function. We define it, and then when we call it, it's called invoking. It's like we're building it, and then we're invoking it. And you can build it once and then invoke it many, many times. So, for example, here is a built-in function called max that finds the largest character, the sort of lexicographically largest character in a string. And so it's like, okay, tell me the maximum character. And so max is not some code that we've written, but we are invoking a function here. And we're passing in an argument to that. So the argument is this stuff in between the parentheses. So the max function can find the maximum of many different things. At this moment, we want it to find the maximum of that particular string, the highest character in that particular string. So this is a right-hand side of an assignment statement too, so that has to be evaluated to a value. So it goes into the function, does whatever things the function wants to do, and then the function gives us back a value that becomes the value for max parenthesis hello world. And that value in this case is the letter W. Okay, because the letter W is decided to be the highest letter, and that's what max gives us back. And then when we're done with that, then that W ends up being assigned, the assignment statement completes. And so you can think of the function evaluation as happening as part of the right-hand side expression calculation. There could be a plus here and other stuff, and it's just at some point a big expression. In this one, it's a simple expression with just one function call. Now if we look at this, there's some code somewhere. Somebody wrote some code. It's part of Python. You didn't write it. There's a max function somewhere, and you can think of a function as having some input. It's kind of like a program. That's why some languages call these things sub-programs, because they have an input, they do some kind of useful works, whatever that useful work happens to be, and then it produces some kind of an output, right? So hello world is the input, the string, the arguments, the thing we're passing in. Hello world is what's being passed into the function. The function is running, and then something comes back and is sent back. So it has input, processing, and output. Input, processing, and output. So that's how a function, some stored code, whether we wrote it or not, they work the same when we call functions. Right? So you could think of this as somewhere inside of the Python library is some code that maybe has a little def in there, and they name the function max, and it takes a single parameter, and it does some blah 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 loopy blah 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 stuff, whatever max wants to do, whatever we need max to do based on the specifications that max is supposed to support. But somewhere there is code inside of Python that actually represents the function definition. It's a built-in function because it comes with Python and we didn't have to do anything to add it. So some common built-in functions that we have been using all along. Go good examples are the float, which takes as input anything and returns you a floating point number version of that. Type, which takes a parameter of a variable or a constant and says, what is the type of this? Float, again converting. Type, again, and float. So these are all things that we've been calling functions all along. And it passes the input value into the function runs, and then gives us back a return value, which then participates in the rest of the expression on the right-hand side. You can think of it pausing the calculation on the right-hand side, calling the function, getting the result of the function back, and then continuing the evaluation of the right-hand side, then coming up with whatever value, and then printing that value out. Okay? Another thing that we've done is we've done string conversions, right? So we've converted, in this case, a string to an integer, and asked what type it is. We've converted a string to an integer, so int converts its argument, whatever that happens to be, into an integer. So that's just some of the built-in functions that we have talked about so far. Now, this becomes more interesting when we can make our own functions. Oops, there goes my tea bag right in the middle of the thing. Here, let me take the tea bag out. I think it's, whoa, hang on, be right back. Tea bag. Okay, there's my tea. So we want to make a new function. Like I said in the other example, we use the def keyword. The def keyword here, and then we have some indented bit. We create a name for it and then have some parentheses. These parentheses will later tell the inputs that we're going to pass in, but this function has no input, so we just go parenthesis, parenthesis, and then the all-important colon character, which indicates the beginning of an indented block of Python that then is the text of the function. So it's important to remember that while this is executing, when Python first looks at this, it doesn't run these lines of code. It just remembers them and names them print lyrics. So it doesn't cause any printout. It just causes Python to remember it. I've probably said that a few too many times. So here is a difficult problem, and I'll let you think about it for a while. I want you to kind of mentally go through and execute this code and ask yourself what the output of this program would produce. How many lines? How many lines of output would this program produce? So, how many of you said 3? How many of you said 5? Well, the right answer is actually 3. You see 5 print statements, 2, 3, 4, 5. But 2 of the print statements are sitting inside of this. And we never invoked the function down here. Okay? So this one, let's clear this. This one prints, these 2 get skipped, this one prints, and this one prints. So that's why there are 3 statements that print. There is stored, but we never used, a function called print lyrics. And it's got 2 statements in it, but we never used it. So the output of this is hello, yo, 7. And that's because we never actually invoked it. We had to say print lyrics, parenthesis, or whatever, to cause it to call this. Okay, that's just to emphasize that as it looks at it, it does not execute these lines. So once we defined a function, once we have given it a name, given it code that is a part of it, then we can invoke it or call it as many times as we like. So now our little example works a little better if we actually call our function. Python really doesn't care if you don't call your function. It's like, you told me to make one, I made one, you didn't use it, there you go. But if you look at this one now, so here we go. X equals 5, print hello, out comes hello. Define, nothing happens here, nothing happens here, it's just remembering. Okay, then it says print yo. Then it calls the function print lyrics, which sort of stops us here, runs these 2 lines of code, So out comes that and that. Then it sort of finishes this and it comes back, x equals x plus 2. Then it prints x. That must mean x is 7. And so out that comes. And so again, it's on the first time through. Oh, go back. On the first time through, it doesn't print. But then when it hits this, it prints. You could say print lyrics several more times, and it would run this as many times as it did, and that it needed to, as many times as you want, and it would make output for you. So you can invoke. This is the definition. Let's clear this. This is the definition. This is the call or invoke. So we're invoking the function, we're calling the function, we're causing the function to execute. Here we are just causing the function to be looked at and defined, but not actually executed. Hope that's clear. Now, when we pass data into a function, and functions that don't take data are not as useful as they could be. There's plenty of things that do. Times that you build a function that doesn't take data, but the most interesting functions are the ones that you can hand them something to work on and they can do their work and then come back with whatever. So this max function is a good example of this, one that's taking an argument. We call the things in between the parentheses when we're invoking the function. We call the things in between the parentheses arguments. Okay, so that's passing into the function, feeding data into the function. So we put arguments in between them. So for example, here we have a little program that it's a function named greet, and now we are going to define this function, and we're going to say, you know what? I would like to take a parameter. Let's take a parameter. Let's have one parameter come in, and we need kind of a placeholder for that parameter. So within the function, we're going to use lang. Now this isn't actually a real variable. It's kind of like it's a placeholder variable. So this first parameter, whatever it is, when it's called, is going to be lang. And so if that first parameter is equal to es, we're going to print hola. And if it's equal to fr, we'll print bonjour. And otherwise, we'll print hello. So there's apparently 3 languages in the world, Spanish, French, and English. And if it's not Spanish or French, then it must be English. But I have to keep this kind of small so my screen doesn't get too big. So this is, again, just the definition. And if you type this into the interactive thing, it gives you this ... prompt. And so we now have this thing called greet. And now we've extended Python to add our own function to Python. And now we can say greet en. And so it runs this code, except that en is lang. And so that comes, and then it prints hello. So out comes hello. Now later we can say, oh, I would like to do a greeting, but this time I'm going to pass es in as it. So lang becomes, for this execution, es. And then it prints out hola. And then the next execution, lang is fr. So it executes this 3 times, but lang is different each time because we've passed in different parameters each time. So that's how we can kind of write general purpose code inside the function and then reuse that general purpose code in different ways. Okay? It's a real powerful mechanism that makes functions far more useful. Now, functions don't necessarily just have to do stuff. A real powerful mechanism in a function is what we call a return value. So a function can take its arguments, do some work, we've seen that, and then it can return a value. And the key to the return value is when we call the function, like we were calling max, it gives us back some value, like the little w. Okay? So here we're going to make a function called greet that takes no parameters. Doesn't take parameters, but it has another keyword. It's another reserved word in Python, and whatever we put on this return statement shows up as the replacement in this expression. So whatever greet is, it runs greet, and then the return is kind of a residual value. So if we say print greet comma Glenn, it says hello Glenn because the return value for the greet function is the string hello. And if we say greet Sally, it says hello Sally. And so and it's run the code twice, and the return value has been put in here instead. And so the hello came there and the hello came there, so we get the 2 lines. So return is a statement that both terminates the execution of the function and defines the value of what will be replaced when the function call comes back in the line that the function was called from. So here is a little smarter version of our greet function. It's very similar. It's called greet still. Takes lang as a parameter. And if the language is ES, then it returns the string hola. If the language is French, it returns bonjour. Otherwise, it returns hello. So we're not actually doing the print. If you go back on the other slides, we were printing. But now we're just returning a string. Okay? And so now I can call print, greet, and pass en in. So then that runs the code once with lang equal to en. And I get back hello and then comma Glenn. Then I call it again and I pass es in. And then that time it returns, the return value here becomes hola, a string hola, hola Sally. And then Michael, I pass in one more time. Lang now is fr, the string fr, and so it returns bonjour. And so the residual that is here is bonjour, and so out comes bonjour Michael. So there's a lot to this, right? You're passing stuff in, you have this kind of placeholder variable, and you have this return that sort of appears where it was called from. It goes in, does its work, it comes back, and there's sort of this residual value that sits here. You don't have to have a return in a function, but if you want to do something with a value, then you have to have a return in the function. We call the functions that produce values fruitful, and the other ones are called void. So that's a good name for them. So to review sort of this arguments, parameters, and results, if we look at max, the original thing where it's looking for the largest lexicographically largest letter, it looks hello world is the argument that's passed in. We have this sort of formal parameter here called imp, which is not really a variable. It just happens to refer to whatever is the first argument when in any particular call. And then it does its little thing and runs loops and does all these things. And at some point, it returns w, so that the thing that comes out when the function quits, that becomes the replacement value here, is a lowercase w string. And then that is the w that goes over into big. So the return is what defines what comes back here. Because you think of this as, it's looking at this, it suspends for the moment, it runs this code, it's holding itself here, it's running this code, and then it comes back to here. Okay? And the return value is what defines coming back. So, of course, you can have more than one parameter, and they are in order. So here we have an A and a B. The name of these things doesn't really matter. They're just relevant inside of the function definition. So we are going to add two numbers together by taking A plus B and then returning the sum. The added variable is just kind of local to this function. And now we can say, add to 3 comma 5, and then this will come back as 8, and then 8 will get assigned into x, and so that'll print out 8. And so you can have as many of these as you want, and the order matters, and there's a one-to-one correspondence. 3 goes to A and 5 goes to B when the thing is called, and then the return value, again, comes back. Okay? So that's sort of arguments. And like I said, not all functions have to return values. We call them void functions when they don't return anything. It's totally fine for that to be the case. So at this point you might be thinking to yourself, okay, great. Well, I still don't quite get why to use functions. And in reality, in the first 10, 11 chapters of this book, other than using lots of functions, we're not really going to spend a lot of time making functions, because most of our programs are going to kind of be that long, and we're not going to do a lot of reuse in the program. And there'll be a time when your programs become complex enough that you'll be like, oh, thank heaven for functions. I think it's premature to say you must use functions, even though there are some exercises that just say, hey, do this with a function, just so you kind of get the understanding of a function. You will find soon enough, as your programs grow, you'll go like, oh, I keep doing the same thing over and over again. Let me pull that up into a function and pass a parameter in, have a return value, and away you go. Or you might find that you're moving from one program to another and you have this common thing that you want to do, so you make yourself a library that you drag along. And we will do lots of libraries. The book in the second half does lots and lots of library stuff doing things like parsing XML and this, that, and the other thing. So don't feel like you need to use functions on every assignment, because they're a natural thing when a program gets big enough. So just kind of understand them on a mechanical level, but it'll come to you at the right time when it's time to start building your own functions. So in this class, we kind of, talked about functions, just got you started, talked about parameters, talked about built-in functions, talking about return values, the store and reuse pattern. So the problems at the end of the chapter for this particular chapter are relatively straightforward in that, like I said, we don't have a real strong need to do functions yet in this class because the programs aren't large enough. But I just said, okay, take one of your previous assignments and refactor the code so that at the top there's a def, compute pay, and you put like the if and whatever in here, and then later on you do your code and then you call compute pay. So you took code that you already had, you move it up into a function and make a function. And I've also online got sort of a sample of this because it's a little complex, and so you should be able to find on Python Learn or on the course site. You should be able to find a good example because I really want you to sort of get this. Like I said, there will come a time when functions will make the most sense to you. But coming up next, of course, is Chapter 5, and that's loops. And loops are going to rock the house. And so that's our fourth major pattern is loops, and I'm looking forward to it. And so we'll see you at the next lecture. Hello, and welcome to Chapter 5, Loops and Iteration. As always, this lecture is copyright Creative Commons attribution, including the audio and the video and the slides and the book even. So now we're getting to our fourth basic pattern. We've talked about sequential, where steps happen one after another. We've talked about conditional, where steps may or may not happen. In Chapter 4, we talked about the store and retrieve pattern, and now we're going to talk about the looping pattern. And the looping pattern is the last of our really foundational ones, and it potentially is the most important one because it's the thing that allows us to get computers to do lots of things that, say, humans might get tired of, but computers don't tire of. And so after this, we'll start sort of becoming a little more skilled in the basic language capabilities. We'll talk about strings and then start talking about files and start doing some real work after we get done with this. So bear with us. It's going to be a while, but we'll get there. We'll get there. So welcome to Repeated Steps. This is the example that I had in the first lecture, Chapter 1. And the basic idea, just to review, is that you have this while keyword. The while keyword sort of functions like an if in that it implicitly has a decision that it's going to make. And it's either going to do the code in the indented block or not do it, or skip it, basically. All right, so you either do it or you skip it. The difference between the while and the if is that it's going to do it many times as long as this question that we have remains true. Okay, and so in this case, n is 5. While n greater than 0, it functions like an if, so yes, it's going to run it. Prints out 5, subtracts 1, so it's 4. Goes back up, and asks the question again. Is n still greater than 0? Well, since it's 4, yes, we'll continue on. Out comes 4, then n gets subtracted. 3, 2, 3, 2, and then we come through, we print 1, we subtract n to 0, we go up, we go back up, n is now not greater than 0, so we come up and we execute outside the loop, we leave the loop, and that really means in the Python code we skip to whatever's lined up with the while statement, the same indent level as the while statement. And so that's how it works, and I just print n at the end here to remind ourselves that n ended up at 0, not at 1. The last thing we printed out in the loop, was the 1, but n ended up at 0 because this loop was going to run as long as n was greater than 0, so n had to sort of be not greater than 0 to get out of the loop. Okay, so that's basically a review of what we've done. Now, oh, wait, something else. Iteration variables. Okay, so the key to this is these loops can't run forever. We don't want them to run forever. We want them to run as long as we want them to run. They may run a very long time, but not forever. There's got to be a way to get out of them. Otherwise, we call them infinite loops, which we'll talk about in the next slide. And so the iteration variable is generally some variable that is changing each time through the loop, and we are changing it by subtracting 1 from it. And so this thing is going to keep running, and we can pretty much see that, oh, this is going to exit, right? Whatever n is, it could be a large number, but eventually it's going to get to 0, right? So the iteration variable controls how many times the loop runs, and it also allows us to do something different inside the loop. And of course, this is like a trivial loop where we're just printing the iteration variable, but it just means that this loop is going to run 5 times, and it's going to do something potentially different each time. If you just ran the loop that did the same thing over and over and over again with no data changing, that's kind of dull and pointless. So just because you have an iteration variable doesn't mean that you've properly constructed your loop. It's a common problem, or something we want to avoid, is an infinite loop. And here is a carefully constructed loop. We start n at 5 at the beginning. We have a good question at the end, while n greater than 0. It's going to run this as long as n is greater than 0. But the problem is we don't change in the little block. We don't change the n, which means it's going to come back and n is going to be 5. And then it's going to run this, and then it's going to be 5. And then it's going to run this, and it's going to be 5. And so this is an infinite loop, which means this loop will never exit. It will never get out. It's just going to run forever in here because n's not changing. Neither of these statements change n. So part of the iteration variable is there needs to be something that changes so that the loop will ultimately make progress to accomplish what it is and know when to stop. So this is an infinite loop. And of course, lather, rinse, repeat is commonly put on shampoo and conditioner. And so you can, next time you're in the shower, take a look at your shampoo and conditioner and find the infinite loop that's on most bottles of shampoo and conditioner. Now, here's another loop, just to emphasize that it's possible to structure these loops in a way that they never run. So this function is as an if. The while functions as an if. And so when n is set to 0 and we ask the question, it is literally going to make the decision based on n greater than 0. Well, it is not greater than 0, so it's going to go right by it. Over here, it's going to come in here and go right to there and never run these lines of code. And we call this a zero-trip loop. And that's okay. I mean, this is a silly one, of course. It just shows that the test, the question that's being asked, is above the lines that make up the body of the loop. And if it's false, the loop never runs. So it's possible that these loops have 0 trips. Okay? So that's a loop. Now, there are more than one way to sort of control the flow of a loop. The basic flow of the loop is when it gets to the bottom, it goes back up to the while and does the check. This is a different way of getting out of a loop or controlling the execution of a loop. There is a keyword or a part of the Python language called, what color did I got? Oh, green's over here, called break. If you looked back at reserved words, break was one of the reserved words. Break says, hey, if I'm in a loop, stop the loop, right? Get out of this loop. I'm done with this loop. And so here's this loop. Now the interesting thing we've done is I just got done talking to you about infinite loops. We have just constructed an infinite loop because the question is right there and the answer is yes, true, true. And that's a way to construct an infinite loop. We've done this because we have a different way of getting out of the loop. So we've constructed a loop that just on the face of it, just looking at that line, looks like an infinite loop. So what this loop does is it reads a line of input, checks to see if it's the string that we've entered is done, and if it is, we're going to skip out with his break and get out of the loop. Otherwise, we're going to print it. So at a high level, what this loop is going to do is prompt for strings of characters until we enter done. And that's exactly what it does. It prompts, we say hello there, it prints that out. We say finished, it prints that out. We say done, and it's done. So when we say done, it comes out and finishes the loop, and that's the end of the program. Okay, so to look at this in some more detail, the first time it comes in, does the raw input, because true is true, so it's going to run it, and then we enter hello there. It checks to see if what we'd entered is equal to the string done. It is not, so it skips, and it does the print. And we do this one more time, and we type finished, and then the line is not done. That's variable line does not have the value done in it. So we print that. We come in one more time, but this time this is true, and so it goes in and executes the break, and then it escapes the loop. And so you can think of, right, here is the body of this loop, because that's where the indentation starts and ends. The break says, break me out of the current loop that I'm in and get to that next line that has the same indent as the while. So whatever it is, break says we are done with this loop. When that statement executes, we are done with the loop. We're finished with the loop. It'll run until that executes because we've got this set to be while true. Okay, so there's a simpler, this is sort of a simple way to draw this. Break is sort of a jump to the statement immediately following the loop. If you really want to picture this, I think of this as kind of like a Star Trek transporter, where you kind of come into break and then your molecules are sent to the four corners of the universe and you reassemble outside of the loop. And so if we look at this sort of in my little roadmap version of these things, right, where while loop is going to run for a while, yada yada, there can actually be more than one break as long as they only get this. But the moment that somehow some if or whatever hits the break, then it gets out completely, and so it escapes the loop. And so it's sort of like you're zoom, 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 zoom. You come in here, and then you're rematerialized outside the loop. That's what the break does. Okay, so break is one way to control the execution of loops. Now, another way to control the execution of loops that doesn't actually exit the loop is called continue. Continue basically says, hey, I'm done with this iteration of the loop. Now, each time through the loop is we call that an iteration. Continue says, I don't want to stop the loop, but I want to stop this iteration and advance to the next iteration. And so what we have here is we have the same basic loop, a while true, which kind of makes us an infinite loop. We're going to read a line prompting with a less than sign. And if it's done, we're going to break. That code is down here, and we're going to print it if we fall through. So normally we'll be reading and printing, and if the line is done, we're going to break out. That's what we just got done doing. But the new part is right here. And this is, we'll learn this in the next chapter. If line sub 0, if the first character of the line is a pound sign, we're going to continue. And what continue says is it doesn't actually get us out of the loop. It jumps back up to the top of the loop, which means that it ignores, for that iteration, the rest of the loop, right? So if execution comes in here, let me clear that. If execution comes in here and hits this line, it goes back up to the while, okay? Which means whatever this is, it's not coming out of this if. It's going back up to the while, okay? So continue ends the current iteration and jumps to the top of the loop and starts the next iteration. And so if we look at how the code runs, hello there prints. Pound sign with the first character doesn't print, so there is no printout right here. Print this is not done, and we enter done, and then the loop ends. Now another way to sort of draw this is that continue jumps to the top of the loop. It does run the question, right? It does check the question. And so here's another way to draw that picture. And so here again we have a loop, and it's happily running, and there can be breaks in there, and there could be continues in there. And as long as we don't hit a break or continue, the loop just sort of runs and goes up to the top. And at some point, some if, we hit the continue, and like a transporter, instead of going out of the loop, we go to the top of the loop. But it's important that we go and we check the question, right? So the continue is not likely to exit the loop unless the question has become false. So the continue is likely to come up here, run some more, then we hit the continue, it comes up here. Oops, I did that backwards. Run some more, clear this out. So the continue could run many times, right? So we have the loop runs a bunch of times. Then finally we hit the continue goes up to the top. If it's still true, we'll run the loop some more. Then you might hit the continue, then you might go up to the top, come down, round and round and round and round, hit the continue again, go up to the top, yada yada. Now in this particular loop, this break eventually is down here, and that's how we get out. Okay, so the continue goes back up to the top of the loop. So these loops that we construct with the while keyword are what we call indefinite loops. Looking at the ones that we've written, which are 2 lines or 6 lines, we can kind of inspect them and understand when they're going to stop. And we're going to know that they're possible to stop them. A loop that won't stop is an infinite loop. Sometimes these loops can be rather complex, and you may not actually be able to look at them because there are many lines, and so we don't know. And so it's real careful. You have to be real careful when you construct these to make sure that they stop as things get more complicated. Now, the cousin to indefinite loops are definite loops. And definite loops is something where we have a list of things or a set of things that are a kind of a known set of things, a finite set of things. And we're going to write a loop that's going to go through that set of things and do something to each thing in that set of things. And the keyword that we'll use for this is the for. So we use the Python for keyword that says we're going to write a loop, but instead of it just running until some condition becomes true or false or we hit a break, we're actually going to know how many times this is going to run. Now you can actually use break and continue in for loops. We call these definite loops because how long they're going to run is kind of well known, basically. So here's a simple definite loop. And it's kind of like that while loop that we just got done looking at, where it's counting down and then saying blast off. And so the way we construct this loop is we have the for keyword, which is part of the Python language, the in keyword, and then we have an iteration variable. I've chosen I as my iteration variable. And basically what we're saying is, dear Python, run this indented block, and there's only one line in the indented block. Run it once for each of the values in this little list. This is a Python list. Square brackets make Python lists, comma separated values. So it says, I would like I to be 5, then run this code. Then I would like I to be 4, then run this code. Then I would like I to be 3, then run this code. I should be 2, then run this code. And I should be 1, then run this code. And so this is a pretty clear, and I like this word in. It says, doop, 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 and then run this each time. And so out of that comes 5, 4, 3, 2, 1, and then the loop is done. Python is doing all the tricky bits here. Python's figuring all these things out for us and handling all this, and then we're done. And so you look at it, we have an iteration variable, but we didn't have to increment it. We didn't have to do anything. Python took care of a lot of things for us. And so when we're looping through known list of things, or later when we read a file, we're going to loop through the lines in the file. And so the for loop is a really nice, powerful, and it's syntactically cleaner. It's really quite nice. Now, it's important to realize that you don't have to just loop through numbers. I did that one with a set of descending numbers, so that it was equivalent to the while loop that I started at the beginning. But this is a loop where what it's going to loop through is a list. Close square brackets are a list in Python. This is a list of 3 strings, Joseph, Glenn, and Sally. They're string constants, and then commas are how we make lists. And so friends is a mnemonic variable. Python doesn't know anything about friends in particular, but I've chosen this variable name to be friends. And it's a list of 3 people, Joseph, Glenn, and Sally. And so I have an iteration variable called friend, and I'm going to loop through the set of friends. Now, Python doesn't know anything about singular. Python doesn't know anything about plural. I'm just choosing these variable names because it makes a lot of sense. This is a set of friends, because it has 3 of them in it, and this is a single friend. What it's really going to do is friend is going to take on the successive values, Joseph, Glenn, and Sally, and this little block of code is going to run once for each of those 3 items in the set, and the variable friend is going to take on the successive values of that set. So out of this comes 3 lines of printout. Happy New Year, Joseph. Happy New Year, Glenn. Happy New Year, Sally. Of course, this is the I bit right over here. But we just made it so, hey, Python, look, however many friends there are, run this code one time for each one, change this variable friend to be each of the successive ones in order. And then we print that we're done. Okay. So the for loop, sort of, we go and try to make a picture of the for loop. The for loop is kind of a powerful thing. It does 2 things. It decides if we're done or not. How do we keep going in the loop? Or, well, I mean, and as long as we keep going, we're going to advance the I value, the iteration variable. It takes care of it, the responsibility of changing the iteration variable. We do not have to add lines of code in that change the iteration variable. Okay? And so if we take a look, we come in, are we done? We're not done. Set I to the right thing, then print it. Out comes 5. advance I, print it, advance it, print it, advance it, print it. Oh, now we're done, right? I was not the thing that decided when we were done. The for loop just keeps track internally as I moves through these things, and it goes like, oh, I'm all done. I'll take care of that. You finished. So it doesn't. There's no if in here. It's not like if I equals 1, stop. No, no, no. It just says you told me to do 5 things. I'm going to do 5 things, and then we're going to stop. And so again, the for loop here is got sort of 2 functions. Decides how long the loop's going to run and changes the iteration variable based on what you've told it to in this in clause. Okay? So I think in is a real elegant construct. It's just a keyword, but it's sort of, if you think about math, if you're familiar with sets, it's like something inside of a set of something. I think it's a real pretty way to think about it. And you can kind of think of it a little more abstractly, that you say, well, here's a little indented block of code, right? And I want it to run some number of times for each of the I values in the set 5, 4, 3, 2, 1. That's how I kind of think of it. So I think this is a real pretty syntax. Different languages have different looping syntax. I think this is really a very expressive, very pretty one. Yeah. So another way to one way to think about this picture is that, you know, the for loop causes sort of repeated execution, and we're driving in the circle and then we stop, right? The other way to think about this is to think about it a little more abstractly, right? To say, you know, at the end of the day, all I'm really telling Python is I want to execute this block of code 5 times, and I want the variable I to change to these 3 values. So in a way, you could think of this as expanded as the for loop sets it to 5, then runs your code. The for loop then sets it to 4, runs your code. The for loop sets it to 3, runs your code. For loop sets it to 2, runs your code. Sets it to 1, runs your code. These 2 ways of looking at it are the same from your perspective, because you're just asking Python to do something. Whether it does it this way or whether it does it this way, you hardly can tell the difference. It's probably going to do it this way, but logically it's not that different. It's not different from doing it this way. You're saying, run this block of code, change I in the following way. Cool. It's like we don't have to worry. I mean, we can use mentally either model of what's going on inside, because it doesn't matter, because they're the same. Okay, so these definite loops are really cool. Starting in a couple of chapters, we'll mostly use definite loops to go through lists or dictionaries or tuples or files. And so it's a finite set of things. It can be a large set of things, but it's a finite set of things. Loop idioms are how we construct loops. And we're going to, the loops kind of have some kind of a goal in mind. Finding the largest, we played with that. Finding the smallest, counting the number of things, looking for lines that start with £, something like that. They have a kind of a high-level view of what they're supposed to do, and then we have to kind of build a loop to accomplish that. And this goes back to how we have to think like a computer, right? We have to say, hey, computer, do this over and over and over again, and then I'll get what I want once you've done that over and over again. You have to do something a million times. I'm not going to sit here and wait. At the end, I get what I want. So I call these kind of smart loops, or how to kind of build intelligence into loops. So for example, we want the largest number, right? But we have to construct a loop that will get us the largest number, thinking like a computer. Okay, thinking computationally, thinking like a computer. So the idea is that we have some kind of a loop, and we're going to go through this list, some list of things, and this is going to run a bunch of times. But the way we're going to do it is we're going to set something up before the loop starts. We're going to do something to each of the things that's being looked at, and then at the end we're going to get the result we're looking for. Okay, and so in the middle it's kind of like working. It's in the middle working, da 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 da, and then here is the payoff. The payoff is at the end when we get the information that we're interested in. So I will sort of use in the next few examples this simple loop. And right now it doesn't do much. It does a print before, and it has this variable thing that goes through the successive values of these numbers, and it prints it out, right? So that middle part says run this 6 times, once for each of those values, and then after. Okay, and so we will add some intelligence at the beginning, we'll add some intelligence in the middle, and we'll add some intelligence at the end, and then the whole thing will accomplish what we want. Right now this is kind of not that intelligent. So now what I want to do is I want to review the thing we did, and I want you to remember what the largest number is, and I'm going to show you a sequence of numbers in order. Ready? I'll do it kind of quickly because you've seen this before. So I'm only showing you one number at a time, so you want to tell me what the largest number is. So here we go. The first number is 9. The second number is 41. The third number is 12. The fourth number is 3. The fifth number is 74. And the sixth number is 15. So what was the largest number? Did you have to go back? Or did you remember how to do it? Okay, well, I will give you a clue. It was 74. Okay? That's because I know. Okay, now if you did that, and you had to do that for 20 or 30 numbers, you'd have to create a mental algorithm in your head to approach it and stay concentrated, focused. So, you would have created a variable in your head called largest so far. I would show you the first number, which would be 9, and you would go, well, 9 is larger than -1, so I will keep that. That's the new largest I've seen so far. That's pretty awesome, because it's way better than -1. 41, I thought 9 was good, but 41, that is a lot better, so I'm going to keep that one. That's the best. It's the largest we've seen so far. We've only seen 2 numbers, but the best we've seen so far is 41. So 12, that's not larger. Who cares about that? It's not as big as 41, so we'll just go right on to the next. On to the next. 3. That's lame when we're looking for large numbers. So we skip. Whoa, 74. 74. That's a rockingly large number. So we're gonna. That's actually the largest we've seen so far, because it's bigger than 41, and 41 was the former champion largest we've seen so far. And there's 74. So we keep that one. I don't know how many letters of these things we're going to see, right? We could see lots of them. But the next one we see 15. Well, that's no good. We got 74 already. 74 is like totally awesome, right? So now, oh, we're done. So, hey, we're done. And so 74 is the champion. That is the largest. It's not even the largest so far anymore. It's actually the largest. It's the largest. So again, we had this thing at the top. We had this loop in the middle, and at the bottom is where you kind of get the payoff. And the payoff is not in the middle. While we were largest so far, but at the end, it turned out, once you've looked at all the values, the largest so far is indeed the largest. Okay, so here's the algorithm for this. And I have some variables, and remember that underscores are valid characters in variables. Now, I'm being a little over explicit in this, so I have a variable called largest so far. Then what I do is I set it to -1. Then I print before so we can see that largest so far is -1. Then we have a for loop, and my iteration variable is the_num. So that's going to take on the successive values 9, 41, 12, 3, 74, 15, and run this indented loop of code. Okay? And so the num will be 9 first time through. If the num, 9, is greater than largest so far, then grab the num and assign it into largest so far. Then print at the end of each loop largest so far and the num. So in effect, the num is 9. We compare it to -1, and -1, 9 is higher, so we make largest so far be 9. Next time through the loop, num is 41, so we compare largest so far with 41, and we like it, so we store it. So we like it, we run it, and we print out 41 is the largest we've seen so far. Then we run again, we come in, the num now points to 12. The num, 12, is not greater than 41, and so we skip. So the largest so far stays 41, and we see 12. Similarly, the num advances to 3. We skip, so we saw 3, but the largest so far is still 41. Continuing, the num is now 74. It runs. 74 is greater than 41. And so we run this code. And so we say 74 is stuck in largest so far, and indeed then we print it out, and largest so far is now 74. We continue on, we go up one more time, the num points to 15, but 15 is not larger than 74, and so we skip, we print out 15 and 74, and then we come out, and at the end we get the largest so far. The name no longer, I mean, it's kind of largest so far at the end is the largest, but the variable name. Okay? Got it? That's one idiom. So let's just switch to another idiom. Now counting. How many things are we going to, how many times is the loop going to execute? How many things are we going to find in the loop? It's all kind of the same notion. And the pattern is really simple. We start some variable Zork. A better name for this would be count, but I want to call it Zork. And then we have a loop, and then in the loop we just add 1 to Zork. And at the end, Zork, and that should be light blue right there, Zork should be the total count. Now, of course, we can look at it and say it's going to be 6, but assume this loop is looping through a million lines in a file or something like that. So it's cheating to kind of look at it and say, ooh, it's 6, because we want to actually compute it. So it's really simple. You know, Zork starts at 0. It's going to run Zork is 1 now, and 2, 3, 4, 5, 6, and then we've run out of stuff, and then we print out 6. Okay, so that's kind of the idiom, right? Before, during, and after. Right? We do something before, we do something during, and in a sense, this Zork here is the number we've seen so far, and at the end, it becomes kind of the total number. Summing in a loop, very similar. Again, you have to think of this as there's a whole bunch of variables here. We start a variable at 0. Each time through the loop, we add whatever it is that we're seeing. Instead of adding 1, we're adding 9, 41, 12, 3, 74, 15. And Zork would be best thought of as running total. So Zork is the running total, and so if we look at the numbers 9 as it comes, running total is 9, running total is 50, running total is 62, 65, 139, 154, and then we skip out, and at the end, the running total becomes the total. Okay? So that's another of these patterns that sort of we do something at the beginning, we do something in the middle, and we have something very nice for ourselves at the end. Finding the average of a sequence of values is the combination of the two previous patterns. This time I'm going to use more mnemonic variables. I have a variable called count. Everyone calls this count. Sum, now the total would maybe be a better word for this, the running total. And then, so the count and the sum start out at 0, and then each time through the loop, count equals count plus 1, so we're adding 1 to count. Sum equals sum plus value, so we're adding 1 to sum. adding the value. Value, of course, being 9, 41, 12, 3, 74, 15. And then at the very end, we can print out the number. We have 6 things with a total of 154, and then we calculate the average. Of course, these are integer numbers, and so this is a truncating division. So 154 over 6 equals 25, and not 25 point something. If we were in Python 3000, Python 3, it'd be better. But so the average, the integer average is, of the numbers we just looked at, is 25. So sometimes we're searching, like for a needle in a haystack, looking for something. And again, you have to think of like you're handed some amount of data and you got to hunt for something. And there might be a million things and you might only want 5 of them. And you can either look by hand or you can write a loop that's got an if statement that says, found it. Maybe I found it at line 7 or found it wherever. So this is filtering or finding or searching, looking for a needle in a haystack in a loop. And so the idea basically is that we have this loop. It's going to go through all the values, 9, 41, 12, 3, 74, but we put in the loop, we embed an if statement. If the value we're looking at is greater than 20, print I found it. So when value is 9, this is going to do nothing and just go and make value be 41. And then value 41, oh, yep, there we go, print large number, so out this comes. Then value becomes 12, nothing happens, value becomes 3, nothing happens, value becomes 74. Oops, this time it's going to happen, so out comes large number 74. Then value becomes 15, nothing happens, and then value is all done, and so it comes and finishes. So this is the searching or filtering or catching or whatever. Okay? We can also sort of, if we don't just want to print everything out, we want to say, is something in there? Go look through this million things and tell me if blah exists. And in this, we're going to introduce the notion of Boolean variable. Boolean is a true-false. It only has 2 values, and we've already used it in the while true. So that capital true, that is a constant. It's just like 7 or 42 or 99 or Sam. And so we're going to make this variable called found. Now found is a mnemonic variable. It's just a name I picked. So found equals false. This is going to be false until we find what we're looking for, and then it's going to switch to true. So it starts out and it's false. Then we're going to run this bit of code 3 times. And if the value that we are looking at is 3, then we're going to set found to be true. And we'll print found value each time through. So value is going to take on 9, 41, 12, 3, 74. So we get a line of output for each one. And the first time through, it's not yet found because we're looking at a 9. The second time, it's not yet found. We looked at 41. Still false. So it could stay false for a long time. Oh, we found it true. And then that means that this code's going to run once. And so you can kind of think of this found variable as sticky. It's going to stay false, and then the rest of the loop is going to stay true, and at the end, it is true. Now, the way we usually do these kinds of things is we don't bother with this print statement, so we wouldn't see all this stuff. All we would see is before false, after true. And after would just tell us that, yeah, we found it. There was a 3 somewhere in that long list of numbers. Okay, I'm just adding this print statement so we can kind of trace it. But basically, this loop, sort of from here to here, is asking the question, is there the number 3 in the list that we're about to go through? Okay? Now, I'll just give you a second and ask you a quick question. You can pause if you want. How could you improve this loop using the break? Where might you put a break to make this loop smarter? It's okay if it doesn't jump out at you. So if you think about it, once you hit true, there's really little point in looking at the rest of them. There just is no point. So we could put a break right here inside this block. You say, look, I'm looking for a 3. All I care is whether I found it or not. If I find it, I mark it to true that I found it, and I get out of the loop. Why bother? Why do all these things? Right? Just get out. Okay? So don't worry about it. I'm just pointing that out. That's one of the places where break could be used. The loop functions either way. It just looks through all the rest of them as well. Here's this largest value one that I've used before, and away we go. We have largest so far. We check to see if the one we're looking at is better, and if it is, we keep it, and then away we go, and we find that the largest is 17. What would you have to change in this code to make this search for the smallest of all the values? Like point where in the screen. What would you have to change to make this look for the smallest in a list of values? What is the nature of what's making this about being largest? What would you have to change? Okay. Pause if you like. So here is some things that you might do to make it work about smallest. So hey, one thing we would do, let's change the name of the variable. We had a variable named largest so far, and now we'll change it to be called smallest so far. Changing the variable name doesn't change the program at all. But it makes the program easier to read if the program works. So it's like smallest so far. Okay, but that didn't make it about being small. The thing that made it about being small is change this greater than to a less than. Because we're kind of thinking when we're doing largest so far, if the number we're looking at is bigger than the largest so far, we keep it. If the number we're looking at in the smallest is smaller than the smallest so far, then we want to keep it. So this is like keep. This line here is the keeping line, And this is the win line, win to keep. We'll keep it if it's smaller. Okay? So that's the key. And so I name it smallest so far, whoop-de-doo. That's good, but the real thing that had this being about largeness and smallness was whether this is less than and greater than, and this was the repeated code that got rechecked over and over again. So, but this still has a bug in it. So let's run this visually. Okay, so now we've got a variable called smallest so far. We are going to check to see if a series of numbers that I'm about to show you are smaller than the smallest so far. So the first number is 9. Is that smaller than -1? No, it's not. -1 is smaller. The second number is 41. Is that smaller than -1? No, it is not. The next number is 12. Is that smaller than -1? No. -1 is smaller than 12. 3? No, not smaller. 74? No, not smaller. 15? Not smaller. So we're all done. Yay! And the smallest number we saw on the list is -1. -1 wasn't even in the list. So that's not a very good program. So let's take a look at what went wrong with this program. So we fixed it. We fixed it as best we could. All right, we made it. We changed the words largest to smallest. Yay, that'll fix. Just makes it more readable. Doesn't actually change the program. And we made this less than. So now what happens is it comes in. If 3 is less than -1, smallest so far, of course, is -1. This just never runs. This never runs. And so as we print, smallest so far stays -1, and oops, that should be -1 right there. Sorry, I forgot to fix that. Here, let me magically fix that. Boom. So let's take a look at what went wrong with this. So here we have the code. Smallest so far is -1. We have it fixed so that we're looking for smaller numbers rather than larger numbers by turning this to less than. But the first time through, smallest so far is -1, and the num is 3. 3 is not less than -1, so we skip through. And the printout at the first line is -1, 3. And it doesn't take long to realize it's just going to keep doing this. Smallest so far is going to stay -1 no matter what we look at on this side. And then we're going to come out the end, and we end up with -1 as the answer. Not very good. So the question is, what should we make this value be? -1, it barely worked in the largest because we were working with positive numbers. And so starting with -1 as the largest so far was a reasonable assumption as long as the numbers were all positive. But what would be a good number to choose here? Think about that for a sec. Pause if you have to. Let me clear it. Let me make it real clear. What's the right thing to put here? Okay. So, what? 1,000,000? That might work. Or 1,000,000 might work. But what if this number, was, what if all these numbers were larger than 1,000,000? Okay, then that wouldn't work. So the problem is there's no real good value unless you could make this be somehow infinity. Okay, you could make this be infinity. But there's a way to do this in Python, and it's a really kind of cool technique. It's sort of a way we signal ourselves, and that is we're going to use a special value. Not -1, it's not a number, and the special value we're going to use is none. It's a different type. It's not a number, it's itself its own type. So what we're going to do is we're going to mark smallest as none. And sort of at a high level, what we're really saying is we haven't seen anything so far. The smallest we've seen so far is none. We've not seen anything so far. Now we have to change our loop, our little if inside the loop. This is this intelligence in the middle. First we say if smallest is none. Is an operator, part of the Python language. If smallest is none, exactly the same as none, then the smallest we've seen so far is the value. Now this is going to happen the first time, because smallest starts out none, and then as soon as we set smallest to the value, it's going to be that first number. So it's going to be 9. Okay, so smallest is quickly going to become 9. Then we print out the smallest is 9 after we've seen the 9. Then we go up to the top and we say, is smallest none? And the answer is no, it is not, because smallest is now 9. Then this else if is going to ask, is the value we're looking at, which is 41, is the value less than smallest? Well, no, it is not. 9 is smaller than 41. And so in a sense, after the first time that's executed, after the first time the statement is executed, this is going to always be false, right? Because smallest is no longer none. And this is going to be the thing that really is operating. And then it's going to work. And when we, smallest will become 9. The smallest so far is 9, but then we see the 3 finally, and the value, the 3 is less than 9, and so then we take 3 and we stick it into smallest, and we end up with this, and then the loop runs some more times, and when we're all done, we have 3. So the trick here is we put this none in, and we have a little more if code to check to see if we haven't seen anything so far. This is what you can think of this as a way to trigger on the first iteration. Special code that's really gonna, it looks at it on each iteration, but it's never true after the first iteration. Okay? So that's just a technique. So this is and the is not operator, I think, is a real elegant thing. Don't start overusing it. It's at a low level, its real meaning is exactly the same as in type and value. There's an is and there's an is not. But don't say if. Don't do things like saying if I equal. Oops. I won't even let myself type the bad code. If I is 4. Don't say that. Okay. Don't say that. Don't do if I is 4. It may work in certain situations. It's really best used in very limited situations where you're checking for some of these special values like none and false. Okay. The problem is if you use equality here, it tries to kind of convert values, and it may end up giving you a false yes. And so is a stronger equality than simple equals. Equals is same value, same numeric value, whereas is exactly the same thing. But don't overuse is. Use double equals 95% of the time, and use is when you're checking if it's one of these special constants like true or false. Okay? Okay, so this is iterations. I mean, our loops are going to get more sophisticated and we have more interesting things to do, but we talked about some indefinite loops, definite loops, iteration variables, some patterns like maximum, minimum, summing, averaging. We introduced the concept of none, and so we're getting there. We've got a couple more chapters before we really start hitting the data analysis. So see you in the next lecture. Hello, and welcome to Chapter 6. This chapter we're going to talk about strings, and stuff is going to start to get real now. So, as always, this material, this video, these slides, and copyright Creative Commons attribution. I want you to use these materials. I want you to, somebody else, I want to make more teachers so everyone can teach this stuff. Use it however you like. Okay, so we've been playing with strings from the beginning. I mean, literally, if we didn't work with strings, we could have never printed Hello World. And Lord knows we need to print Hello World in a programming language. And so we've been using them, especially constants. Now in this chapter, we're going to dig in. So a string is a sequence of characters. You can either use single quotes or double quotes in Python to delimit a string. And so here's two string constants, hello and there, and stuck into the variables stir1 and stir2. We can concatenate them together with a plus sign. Python is smart enough to look and say, oh, those are strings. I know what to do with those. And you'll notice that the plus doesn't add any space here because when we print Bob out, hello and there are right next to one another. If, for example, we've done some conversions, so when we're like reading pay and rate and hours and stuff, we've done some conversions. So this is an example of a string 123, not 123, but the string quote 123 quote, and we can't add 1 to this. We get a trace back, kind of at this point as we expected, and we would convert that to an integer using the int function that's built in. See how much Python you already know? I mean, this is awesome, right? I can just say, oh, you call the int function, and you know what that is. That's Sorry, I'm just awesomed out. So you convert this to an integer, and then you add 1 to it, and then we get 124. So there you go. We've been doing strings all along. Had to. I mean, literally, strings and numeric data are the two things that programs deal with. So we've been reading and converting. Again, this is sort of a pattern from some of the earlier programs where we do a raw input, and the raw input just takes a string and puts it in a variable. So if I take Chuck, then the variable contains the string CHUCK. Even if we type numbers, that is a string. We can't, just because I put 100 in, I still can't subtract 10. We get a happy little traceback. Oh, happy little sad face traceback. But of course, if we convert it int or float or something like that, if we convert int or float, we can do that and subtract 10, and we can do that. So we've been doing this for a while. We've been doing strings and manipulating strings and converting strings all along. So the thing we're going to start doing now is we're going to dive into strings. We realize that strings are addressable at a character by character basis, and we can do all kind of cool things with that. And so a string is a sequence of characters, and we can look inside them using what we call the index operator, the square brackets. And we've seen square brackets in lists, and you'll see that there's sort of similarities between lists of numbers, and in effect a string is a special kind of list of characters. So if we take the string banana, the string banana starts, the first character starts at 0, so we call this operator sub. So letter equals fruit sub 1, and that is the second character. Now, this may seem a little weird that the first character is a 0 and the second character is a 1. It actually is kind of similar to the old elevator thing, where in Europe they're called, the first floor is 0 and then -1, and the second floor is 1. Right? It's kind of the same thing. Actually, it turns out that internally 0 is a better way to start than 1. You'll get used to it, and then after a while there's some little cool advantages to it. But for now, beginning is 0. Just beginning is 0. It is the rule. Just remember it. Okay, so the 0 is B, the 1 is A, the 2 is N, etc., etc. And we call this syntax fruit sub 1, okay? So that is the sub 1 character of fruit, and then that is an A. So that fruit sub 1 says, look up in banana, find the 1 position, and give me what's in that 1 position. That's what the sub. And what's inside these brackets can be an expression. So if we set n to 3, n minus 1, well, that'll compute to 2. And then fruit sub 2 is the letter n, right? So that's fruit sub 2. Okay, it's the third character, fruit sub 2. So the index starts at 0. We read the brackets as sub, fruit sub 1, fruit sub 2. Now, Python will complain to you if you use this sub operator too far down the string. Here is a character with 3, which is 0, 1, and 2. If we go to sub 5, it blows up. Now, by now I hope that you're not freaking out about traceback errors. Remember, traceback errors are just Python trying to inform you. And if we just stop looking at that as mean Python face and instead look at that as, oh, index error, string index out of range. Oh yeah, I stuck a 5 in there and there's only 3. My bad. Thank you, Python. Appreciate it. Thanks for the help. So think of this as like, it's not a smiley face, but it's kind of like a quizzical face, right? It's like, I don't know. So Python's confused, and it's trying to tell you what it's confused, okay? So don't look at these as sad faces. Python doesn't hate you. Python loves you. Python loves me too. So strings have individual characters that we can address with the index operator. They also have length. And there is a built-in function called len that we can call and pass in as a parameter the variable or a constant, and it will tell us how many characters. Now this banana has 6 characters in it that are 0 through 5. So don't get a little confused. The last character is the 5th, is sub 5, but it's also the sixth character. So the length is really the length. It's not length minus 1. Okay? So len is like a built-in function. It's not a function we have to write. As we talked about in the functions chapter, there are things that are part of Python that are just sitting there. And so we are passing banana, the variable fruit, into function. We're passing it into function. And then into the len function. Then len does magic stuff. And then out comes the answer. And that 6 replaces this. And then the 6 goes into the variable x. And so x is 6. I sure made that a messy looking slide. And so think of inside the len function, there's a def. Len takes a parameter, does some loopy things, and it does its thing. So it's a function that we might write, except we don't have to because it's already written and built into Python. Okay, so that's the length of the string. That's getting at individual characters. We can also loop through strings. Obviously, if we can use the index operator and we can put a variable in there, we can write a loop. This is an indefinite loop. So we have this variable fruit, has the string banana in it. We set the variable index to 0. We make a little while loop. And we ask, as long as index is less than the length of fruit, now remember the length of fruit is going to be 6, but we don't want to make that less than or equal to because then we would crash because the last character is 5. We can say letter is equal to fruit sub index, so that's going to start out being index is going to be 0, so that's fruit sub 0. Then we print index and letter, so that means the first time through the loop we're going to see 0b. Then we increment our iteration operator. Then we go up. And then we come out with 1a, and index advances until index is 6, but has printed out each of the letters. Now, we're not doing this just to print them out. We will do something a little more valuable inside that loop. But this gives us the sense that we can work through a loop just like we can work through a string just like we work through a list of numbers. Okay? Now, so that was how you do it with an indefinite loop. In a definite loop, it's just far more awesome. Okay? Just like we did with the list of numbers, Python understands strings and allows us to write for loops using for and in that go through the strings. So basically, for letter and fruit, now remember I'm using letter as a mnemonic variable here. It's just a wise choice of a variable name. So that says run this little block of text once for each letter in the variable fruit, which means that letter is going to take on the successive B, A, N, A, N, A. When I look at that, I always worry that I misspelled it. I think I got these right. If I rewrite this book, I'm not going to use banana as the example because I'm terrified that I misspelled banana because I don't know how many N's banana has in it. But be that as it may, we are abstracting, we are letting Python say run this little block of text once in order for each of the letters in the variable fruit, which is B, A, and A, and so it prints out each of the letters. So this is a much prettier version of the looping. So using the definite, the for keyword instead of the while keyword. And so we can just kind of compare these two things. They kind of do the exact same thing, and it also is kind of gives you a sense of what the for is doing for us, right? The for is setting up this index, the for is looking up inside of fruit, and the for is advancing the index. So the for is doing a bunch of work for us, and I've characterized that sort of in the previous lecture, how the for is sort of doing a bunch of things for us, and it allows our code to be more expressive and instead of, so this is a lot of this just kind of bookkeeping crap that we don't really need, and so the for loop helps us by doing some of the bookkeeping for us. Okay, so we can do all those loop idioms. We can find the largest letter, the smallest letter, the how many times. So I think how many N's are in this or how many A's are in this. And so this is a simple counting pattern and a looking pattern. And so our word is banana, our count is 0. For the letter and word, again, boop, 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 that comes out like that. So it's going to run this little block. If the letter is A, add 1 to the count. So this is going to basically print out at the end the number of A's in banana. it would probably be more useful for me to print out the number of N's in banana, because I never know how many N's are in banana. But it looks like there's supposed to be 2, or otherwise I have a typo on this slide. So the in, again, I love the in. I just absolutely love this in. I love this syntax. This for each letter in the word banana. To me, it reads very smoothly. Cognitively, it fits in my mind what's going on. For each letter in banana, run this little indented block of text. Again, very pretty. I love in. It's one of my favorite little pieces of Python. So again, with the for, it takes care of all the iteration variables for us, and it goes through the sequence. And so here's an animation, right? Remember that the for is going to do all this work for us, right? Letter is going to advance through the successive letters in banana. So letter is being moved for us by the for statement. Okay? So that's looping through. Now, it turns out there's a lot of common things that we want to do that are already built into Python for us. Clear the old screen there. We call these slicing. So the index operator looks up various things in a string, but we can also pull substrings out using the colon in addition to the square brackets. Again, this is called slicing. So the colon operator basically takes a starting position and then an ending position, but the ending position is up to but not including the second one. So it's up to but not including, up to but not including. Just like the 0, you get used to it pretty quick, but the first time you see it, it's a little bit wonky. So if we're going 0 through 4, that's how I read this. Print S sub 0 through 4, or better said, S 0 up to but not including 4. That is, print me out the chunk that is up to but not including 4. So it doesn't include 4, and so out comes mont. Right? So the next one is 6 up to but not including 7, so it starts at 6, up to but not including 7, so out comes the P. And even though you might expect that it would trace back on this, Python is a little forgiving. So here's a moment where Python is a little forgiving, saying, you know, I'll give you a break here. If you go 6 but up to but not including 20, I'll just stop at the end of the string, so 6 to the end. So you can over-reference here, and you won't get yourself in trouble, so that comes out Python. So again, the second character is up to but not including, and that's the kind of the weird thing there. Of course, once you remember that the first character is 0, 0 up through but not including. Nice. If we leave off the first or the last number, leaving off the first number, the last number, and both of them, they mean the beginning and end of the string respectively. And so up to but not including 2 is MO. 8 colon means starting at 8 to the end of the string. So that's thon. And then that means the beginning of the end, and so it's just the whole string, Monty Python. Now we've already played with string concatenation. Just a thing to emphasize here is the concatenation operator does not add a space. Does not add a space. If you want a space, you explicitly add it. So here there's no space in between the O and the T, but here there is a space between the O and the T because we explicitly added it. So you can concatenate more than one thing, and you add your spaces as you want. Okay? Another thing you can do is you can ask questions about a string, sort of like doing a string lookup using the in operator. This is a little different than how we use it inside of a for loop. This is a logical operation asking a question like less than or greater than or whatever. So here is an expression. So fruit is banana as always. Is N in fruit? And the answer is yes, it is. True. So this is a logical operation. It's a question. It's a true or false. Is M in fruit? No, false. And this can be a string, not just a single character. Is NaN in fruit? The answer is true. And you can put sort of, if parts of ifs, etc., etc., etc. So this is a logical expression that can be on an if. You can have a while, etc., etc., etc. So it's a logical expression and it returns true or false. You can also do comparisons. Now the comparison operations Equals makes a lot of sense. Less than and greater than depend on the language that you're using Python. And so if you're using like a Latin character set, then alphabetical matters. The way the Latin character set would do. But if you're in a different character set, Python is aware of multiple character sets and will sort strings based on the sorting algorithm of the particular character set. So you can do comparisons like equality, less than, and greater than. And we've seen some of these things in previous lectures, actually. We've had to use them. So in addition to these sort of fundamental operations that we can do on strings, there's a extensive library of built-in capabilities in Python. And so the way we see these built-in capabilities are they're actually sort of built into strings. So let's go real slow here. Here we have a variable called greet, and we're sticking the string hello Bob into it. Now greet is of type string as a result of this, and it contains hello Bob as its value. But we can actually access capabilities inside of this value. So we can say greet dot lower parenthesis. This is calling something that's part of greet itself. It's a part of all strings. The fact that greet contains a string means that we can ask for, hey, give me greet, which just gives you back what you're looking for. Like here, print greet is hello Bob. Or you can say, give me greet lower. So this is giving me a lowercase copy. It doesn't convert it to lowercase. It gives me a lowercase copy of hello Bob. So zap is hello Bob, all lowercase. Now it didn't change greet, right? And you can even put this dot lower on the end of constants. So why you do this, I don't know, but hi there with H and T capitalized, dot lower comes out as hi there. So this bit is part of all strings. Both variables and constants have these string functions built into them. And every instance of a string, whether it be a variable or constant, has these capabilities. They don't modify it. They just give you back a copy. Now, it turns out there is a command inside Python called dir to ask questions like, hey, well, here's, stuff is got hello world. We can say, let me redo this. Come here. Stuff has a string. We can ask, hey, what are you? I'm a string. Dir is another built-in Python that asks the question, hey, what are all the things that are built into this that I can make use of? And here they are. That's kind of a raw dump of them. You can also go look at the online documentation for Python and see at the Python website, you can see a whole bunch of these things, and they have the calling sequence, what the parameters are, etc. So when you're looking these things up, you can go read about them. Here's just a few that I pulled out. Capitalize, which uppercase is the first characters. Center ends with find. There's stripping. So I'll look through a couple of these, just the kind of things to be looking for. Be a good idea to take a look and read through some of the things. Here's a couple that we'll probably be using early on. The find function, it's similar to in, but it tells you where it finds the particular thing that it's looking for. And so we'll put fruit is banana. And I'm going to say pos, which is going to be an integer variable, equals fruit.findNA. So what it's saying is, go look inside this variable fruit, hunt until you find the first occurrence of the string NA. Hunt, 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 hunt. Whoop, got it. And then return it to me. So that's going to give me back 2. 2 is where it found it, right? So where is it in the string? That's what find does. And if you don't find anything, like you're looking for a Z, no, I didn't find the Z, then it gives me back -1. So just, again, this is just one of many built-in functions in string. The ability to find a substring, okay? Or find a character or string within another string. There's a lowercase. There's also an uppercase. This might be better named shouting. Upper means give me an uppercase copy of this variable. So hello Bob becomes hello Bob. And then lower is hello Bob. Right? So these are both ways to get copies of uppercase and lowercase versions. You might think these are kind of silly, but one of the things that you tend to use lower for is if you're doing searching and you want to ignore case, you convert the whole thing to lowercase, and then you search for a lowercase string. So Depends if you want to ignore case or not. So that's one of the reasons that you have things like this. There is a replace function. Again, it doesn't change the value. Greet is going to have hello Bob, and I'm going to say greet dot replace all occurrences of Bob with Jane. That gives me back a copy in nster says hello Jane. So greet is unchanged. This replace says make a copy and then make that following edit that we've requested. Now we can also say, well, I mean, the replace is going to do all occurrences. So greet is still hello Bob. This is kind of redundant here. I'm just doing it so you remember what it is. Greet is still hello Bob. I put hello Bob back in it and replace all the occurrences of lowercase o with uppercase X. And then that happens. So this says go through the whole string, doing all those replacing. Okay? Now another common thing that we're going to have to do is we're going to have to throw away white space. Sometimes you have a string that has characters, blank characters, or other characters at the beginning and the end, non-printable characters, and we can strip them. And there's three functions that are built into to Python strings that do this for us. There is lstrip, which strips from the left. There is rstrip, which strips from the right, so throws away these white spaces. So hello Bob is gone. So it gets rid of these characters. Oops, these are the ones that are gotten rid of there. I need an eraser. And then let's use white. And then strip basically gets rid of all the white space both on the left and the right side and gets rid of that. So we're gonna be using these a lot. One of the things you tend to do in Python is cleaning up data. Sometimes if you have spaces at the beginning or the end, you just want to kind of ignore them. So you strip them off. You throw them away. When we're looking for data, we sometimes are looking for a prefix. And there is a starts with function that gives you a true or a false. We're asking here, does this variable line start with the string please? And the answer is true, because it does start with the string please. And the next we ask, does this start with the letter P? And the answer is false. It does not start with the letter P. Okay, so there's lots more of these things. And reading data and tearing it apart is one of the things that we're going to really focus on for the rest of these first few chapters of the book. Okay, because that's one thing that Python's really good at. It's tearing data into pieces and pulling the pieces that you want. So let's take a look at this line. So this line that we've got here is a line from an actual email box. This is what, if you looked at your email sort of on your hard drive, email boxes would have this kind of a format. And there's actually many lines, and then soon we'll be reading whole files full of email. But for now, let's just say we got this one line somehow. And we're looking for, we don't know how long these things are going to be. The first thing is from, then there's an email address, then there's some detail about when the mail was sent. But what we actually want is we want this part right here. And that's the domain name of the mail address, right? We want to extract this out. We're faced with this line in a variable, and we want to extract that out. So this is kind of putting all these things together. So let's walk through how we do this. So here's this line, and it's a big long string. Mostly we would have read this from a file rather than just put it in a constant, but for now we put it in a constant because files is the next chapter. And so what we're going to do is we're going to say, you know what, I'm going to look at this line and I'm going to go find the @ sign, and I want to know where the @ sign is. So I call data.find @ sign and put the result in @pose, and that gives me 21. It hunts until it finds the @ sign and then tells me where it found it. Then what I want to look at is, starting here for the rest of the string, I want to find the first space afterwards. So what I say is this sppose is my variable for the position of the space, data.find a blank starting at the @. So this is starting at 21. So it says I'll start at 21 and I'll look for the next blank. And I find that at 31. So now I know where the @ sign is and I know where the space is. And so what I'm looking at is I want the stuff one beyond the @ sign up to but not including the space. So then I can use a slicing operation. Start at the @ position, add 1 to it, so we advanced 1, that's going to be the letter U, and then a slicing operation up to but not including space. Up to, this is going to work out nicely all of a sudden, but not including. Okay? And then I'm going to take that slice, which is really this little bit of data right here, take that slice and put it in the variable host. Then we print that out and we get the piece. Okay? And so here we have some data we want to tear apart. We hunt for the @ we find it at position 21. We start at 21 and we look for the space after that, 31, and then we pull from 22 up to but not including 31. And it wouldn't matter where this thing was because these aren't all the same length when we start looking at them in files, but it would have found the @ sign and the space after the @ sign, and it would have reliably pulled out the host. Okay? So this is a basic pattern we call parsing. Parsing text. Like find this, find that other thing, grab this thing out, then look inside that thing, and so it does all these things, right? So that's kind of strings. Up next we have files. Files are going to be lots of strings, so we're going to start putting all these things together. And so the next chapter is a really, really important chapter where it starts to really start coming together. So see you soon. Welcome to Chapter 7, Python for Informatics, Exploring Information. I'm Charles Severance. I'm the author of the book and your host. And as always, this is brought to you by, it's all copyright Creative Commons attribution. The audio, the video, the slides, and even the book. So here we go. Oh, and so frankly, where we've been working all along is we have been writing code and talking to the CPU. Hang on, let me go get my CPU and stuff. Hang on, be right back. Okay, here we go. Here's all the stuff. Remember the stuff from the first lecture? There we go with that. Remember the motherboard from the first lecture? This is kind of the picture of what's on the screen. The motherboard, the CPU plugs in here, memory plugs in here. And remember how the CPU is sort of the brains, as much brains as there is for the operation. This CPU is asking what next. The instructions come in through these little pins. There's data inside, and it stores sort of semi-permanent data. Variables are all stored pretty much here in RAM. And we write our programs, and so your Python programs, they're sitting here in this RAM, and they're being fed to this CPU through those chips. Through those pins, right? The pins. I mean, it doesn't really connect like that. And so frankly, up to now, everything that we've been doing is just the Python programming language. And so the only place we've really been operating is here. We have been putting Python into the main memory, and we have been effectively feeding instructions to the CPU, the central processing unit, as it needed them. And then the program would stop. And everything we've done so far, everything, is just sort of fiddling around here. We have never escaped it. So now we are finally going to escape from the central processing unit and the memory. We'll still write programs and have variables in here, but now we are going to use the disk, the secondary storage, the permanent media, right? So if I go grab my Raspberry Pi, all right, that disk goes right there. Here's my Raspberry Pi. So here we got the Raspberry Pi, which is the small version, which of course has a CPU, memory, and graphics processor all on this little chip right here. But the secondary memory for is this little SD card that is the secondary memory for Raspberry Pi. So the structure of the Raspberry Pi is exactly the same as the structure of any other personal computer. It's just smaller and less expensive. And so in the Raspberry Pi, if you're programming the Raspberry Pi, you're sort of finally escaping. All your programs were in here, your CPU is in here, and that's pretty much how far you got to run. But now, of course, when you save your files, you save them to here. But now we're going to start looking at data on the disk drive. And so it's time to escape to the secondary memory. Okay? Time to escape to the secondary memory. There's the Raspberry Pi, you go right there. Okay? So it's time to find some data to mess with. So a lot of what we've been doing so far is just kind of the pre-work to get to the point where we can do this. And in here we're going to have data files. Now we've been making data files. You've been writing, every Python program that you write on your computer gets saved as a file. Then Python reads the file and runs it. But now we're actually going to start messing with some data. And so files are where we're going to be working with. And so one of the things about secondary memory is it's much larger. I mean, main memory of the computer is pretty large. It's just not large enough to hold everything that the computer is capable of holding. So the files that we're going to work with, now we're not talking about image files or QuickTime movies or things like that. We're going to work with text files because the theme of this course is digging through text. Sometimes we'll pull it off the internet, sometimes we'll read files, but it's digging through and using all the things that we've learned so far, looping and strings and all those things, to make sense of a sequence of information. Okay? Now, to access file information, we have to do this thing called opening the file. We can't just say, yo, the information is just omnipresent, because there are so much data that you can't have Python sort of know all the data. You literally have hundreds of thousands of files on your computer's hard drive, and which one are you going to read? So there's a step that you have to do that you call this built-in function called open, and say, oh, this is the file I want to work with, of the hundreds of thousands. And then once you do, you've kind of got this little connector into it. And the open is a built-in function inside Python. Hang on a sec, let's say goodbye to that. The open function is a built-in function in Python, and it takes two parameters. The first parameter is the name of the file, like mbox.txt, and then the second is how you're going to read it. Are you going to read it? Are you going to write it? Etc. Now, most of the time, we'll be reading our files. So we call the open function and pass it in the name of the file we want to open, and then how we want to read it. Now, you can leave this second parameter off, and it assumes that you're going to want to read the file. Now, when the open is successful, it doesn't actually read all of the data, because the memory is small compared to the hard drive. And so you have to sort of step through the data. You'll tell it when to read it. So the act of opening it isn't not actually reading all the data. It is creating kind of like a connection between the memory and the data that's on the hard drive, right? It's connecting between, let's do this. Oh, that's going to fall down. It's going to stand up that way. Oh, I should come up with a way to make that stand. So it's a connection. So your program's kind of running in here, and the file handle is just sort of it's like a phone call between your memory and your disk drive. It's not the actual data. The actual data is still sitting on the disk drive. Okay? So a graphical way to take a look at this is the file handle, the thing that comes back from the open request. The open goes and finds the file out on the disk drive, yada, yada, yada. And then the handle is something that lives in the memory that is sort of like the thing that maintains its connection to where all the data is on the disk or on the SD-RAM that's in it. So the handle is not all the data, but it is a mechanism that you can use to get at the data. So if you print it out, it doesn't have all the data from the file. It says, I am a file handle that's opened this file, and we're in read mode. So it doesn't actually have the data, even though this is the data that's in the file. And then we have operations that we do to the handle, like open it, close it, read it, write it. So we do things. So the handle, and then through the handle, it actually changes what's on the disk or reads what's on the disk. So the handle is kind of a thing that's not there. if you attempt to open a file and the name of the file. Now the way we're going to do these is these need to be in the same folder on your computer as your Python code. Now there are trickier ways to do it, but we're going to keep it simple. This is the name of a file in the same folder as the Python code that you're running. And if it's not, then we get, of course, a traceback. And we're used to reading tracebacks by now. No such file or directory, stuff.txt. Oh, of course, I forgot to save it, or I typed it wrong. So, the next thing we have to learn is the notion of the new line character. We haven't seen this so far, but there's a special character in files that is used to indicate the end of a line. Because these text files that we've been writing, including the Python programs that you have, are organized into lines. Each line is variable length, and there's a special non-printing character that you just don't see. Now you see it because you see a line, multiple lines, but you don't see the character itself. So it turns out that this character is very important because the data is just a stream of characters on disk, and then it's punctuated by new lines that tell it when it's time to end a line. So if we're building a string, constant for new line is \n. And so when we make a string that we want to have a new line in it, we'll say hello \n world. And then if you print it out one way, you actually see the \n, but then if you use the print to print it out, you see sort of like it moves back down, to the left margin and down. So sometimes you see the /n, and sometimes it's shown as movement, right? It moves it. The other thing that's important is even though we represent this as two characters, the \n is represented as two characters in a string, it's actually one character. So if we print it out, we see X, new line Y, and if we ask how many characters are in stuff, which is this string, it says 3. That's important. Okay, there is 1, 2, 3. The new line is a single character. This is just a syntax that we use to sort of encode a new line in a string. Okay? So, even though these are just a long sequence of characters punctuated by new lines, visually, text editors and operating systems show these files to us as a sequence of lines. And it doesn't take very long to just start thinking about them as a sequence of lines. As a matter of fact, maybe you wish I never told you about new lines. But when we start reading files, we're going to have to deal with these new lines. So the way that we sort of have to mentally visualize of what these text files look like is they have a new line that punctuates the end of the line. Now in reality, if we look at this R really comes right after it. Right? This is all a bunch of characters, and the new lines are punctuation. Okay, to say this is first line, second line, third line, fourth line. So you got to think that each of these things is here, sitting at the end of the line. And so the number of characters in this line include that new line. Now the new line is one character. Okay? So, how do we read these files? Well, we've already talked about doing an open X file. And this X file, again, that's just a mnemonic name that I made up. This is a handle. Remember, it's not all the data, but the handle is the way that we can read the data. We can use it as an access point. The coolest way to read a file, if it's a text file in multiple lines, is to use a determinant loop, a for loop. For cheese in X file. So this, remember we would put a list of numbers or a string here. Now we've put a file handle here. Python knows automatically that each time we're going to run this loop, it's going to go to the next line of the file. Automatically. For cheese is just a stupid name that I came up with. It probably would be better to call it line rather than cheese. But for cheese in, and then it goes each file, and then it stops when it reads the whole file. So this line will print out every line in the file. That's how you do it. These 3 lines open a file, read every line in the file. Okay? So a file handle itself is a special kind of a sequence, much like a list of numbers or a string is a sequence of characters. So one of the things we can do to combine one of our counting idioms is count the number of lines in a file. Okay, and so how we would do that is we would open the file, set a counter to 0. This time I'll use a mnemonic variable called count. For line in fhan, that says run this indented text once for each line in the file. For each line in the file, add count equals count plus 1. When the for loop is done, print the count. Pretty straightforward. Very few other languages are capable of writing that program in as quick and as dense, as succinct a way as Python is. Python does a really, really nice job of this. Okay, so that's how you count the lines. Open it, write a for loop, and then add 1. Now we can't just say, so what you can't do, and this gives you a sense, is you can't say len f hand. And that's because this isn't really the data. That's sort of, you have to like pull it and read it to get the data out of it. Although we'll see another way of reading it later. Okay, so that's counting the lines in a file. It turns out you can also read the entire file. Now if you read the entire file, it's not broken into lines. You're getting all the characters punctuated by new lines, and you get everything. Now you don't want to read this if it's too big. So it's going to all try to read it into the memory of the computer. And if the memory is not big enough, the computer's going to slow down to a crawl. But if it's a real tiny file, this works just fine. And so we have sort of we open a file and we say fhand.read. This is basically saying, hey, dear fhand, read it all and return it to me as a string. So that's a string with all the lines of the file concatenated together with new lines, which is actually exactly what's in the file. It's the raw data. That for loop sort of looks for the new line and does all the stuff automatically for us. That's quite nice. So then we can, like, because imp is a string at this point, we can just print the length of it. And we can say, oh, there's 94,626 characters that came from that file. It reads the whole thing, whole file, reads the whole file. We can also do things like, slice it now. And so this is the first 20 characters, up from 0 up to, but not including 20. So this is our file. Okay? So that's reading through the whole file. So let me go back a little bit. This is the file that we're going to play with. This file here that we're going to play with in this class is a mailbox file. And this is actual real data, and these are real people, and these are real dates having to do with an open source project that I worked on called Sakai. I actually have a tattoo of Sakai here on my shoulder. Maybe in an upcoming lecture I'll have a short sleeve shirt and show you my tattoo. But for now I can't because I've got clothes on. So, but this is real data. It's the mbox.txt file. So that's the file that we're going to use for most of the next few assignments. It'll be the same file. You'll get tired of it. And you get to know all these people, Stephen and Chen Wen and all the people in the file. Okay, so we can search for lines that have a prefix. This is kind of the find pattern from the looping lecture. So we're going to go through a list of lines in a file, and we're going to only print out the ones that match a certain thing. So again, we open the file up. We're going to write a for loop that's going to say for each line in the file, if the line, and then we can call a utility function inside of string, because line is a string. If line starts with from, print it out. So this means it's going to loop through all of the lines of the file, and it's going to print the ones that start with the string from : Okay. Again, 4 lines, complete Python program to read this file and print the lines that have a prefix of from. So if you run this program, and I suggest that you do, this is what the output's going to look like. And it's like, wait a second, I'm seeing the lines that have the froms. But then I get these blank lines. And why is that? Why are these blank lines there? If I look at the program, I'm not printing blank lines. I'm only printing lines that start with from. I'm not doing that. So why? What do you think? I'll give you a second. I've certainly done enough foreshadowing in this lecture. Well, it turns out these new lines are the problem. So it turns out that the print, we've been doing this all along, we didn't make a fuss about it. The print adds a new line at the end of everything that it prints. So these yellow new lines are coming from the print statement. But when we read the file, each line ends in a new line. So these green new lines are actually from the file. They're the ones from the file. So what's happening is we're seeing two new lines, and so that turns into a blank line. So how do we deal with that? Well, we've got a string function that conveniently solves that problem. Okay? And that is, we're going to call rstrip. If you recall, we had strip, lstrip, and rstrip to strip white space on one side, on the other side, or on both sides. So in this one, we're going to use rstrip. We're going to say, we're going to read the line, that this line is going to have a new line in it. Rstrip says pull white space, and the new lines are also counted as white space. Blanks or new lines are white space. And then we're going to replace this with no new line in it. Then we're going to ask if it starts with a from, and then we're going to print it out. And then we go and we're going to see exactly what we're looking for in this file. And there's no new lines. Now so the new line that's coming out here is the one from the print, not the one from the file, because the one from the file got wiped out by that particular line. Okay? So another general pattern of these file-based loops that we have done this is a skipping pattern. Now you can do, the non-skipping pattern is where you're saying I'm going to look for lines that start with from and do something to them. Sometimes you want to do something you want to say here's a bunch of lines I'm going to skip and then I'm going to do something. So the skipping pattern uses continue. And so the first few lines here are the same. We open a file, we read each line in the file, then we're going to strip off the white space. You're going to get tired of typing these three lines because you're going to do it a lot. Open the file, start reading the file, strip the white space for each line. And you can make it so that you can look for some fact. In this case, I'm going to say if not line starts with from, means this is true for all the lines that don't start with from, continue. And if you remember, continue goes up. So the continue says, I'm done. It finishes the iteration, and it doesn't do anything down here. Okay? And so and then we can do something. So I've kind of flipped this where I said, these are the things I'm interested in. That's lines that start with from. So I'm going to skip the lines that don't. So I'm going to use continue. Either way you can do it, depending on the complexity or how much. Often this is a good pattern when you have lots of lines of code down here that you're going to do a lot of cool stuff with. You can also use things like in to select lines, right? So I'm going to look for lines that have at uct.ac.za in them. So again, I'm going to open it up. I'm going to open these, go through each line in the file. I'm going to strip the white space out, and if not uct, if this string is not in line, then I'm going to continue. So it's a way for me to skip all of the lines that don't have this string in it. So these lines do, oops, that one has it too. And then we're going to print it out. We'll print out the ones that make it past here. Okay, so, but in is another way to do searching. Right? It starts with, etc. So one more thing that you might want to try is, so we can count, right? Now, and this is a pattern for prompting for a file name. And so here you'll get tired of sort of changing your code every time you want to open a different file, because you probably want to run the program with mbox once and mbox short, because you just so you can test it with different things of data. So here's just another pattern. We add this line to say raw input, enter the file name, and there you go. We'll type in the file name, and then the thing that we open is whatever we entered as the file name, and then the rest of it is pretty much yada yada. So here it's reading the whole file. If the line starts with subject, count equals count plus 1, and then there were 1797 subject lines in mbox.txt. There were 27 subject lines in mbox short.txt. Okay, so that's prompting for the file names. Now, the open statement fails if the file name doesn't exist. So you might want to add a try and except around that. If you're just writing code for yourself and you assume that the data is okay, then you don't have to write try except. But if you want to catch it and catch a bad file name, then you take the open, and turn it into these 4 lines. So this is the code that we think might blow up, and it's going to blow up. We know it's going to blow up if they enter a bad file name like Nana Boo Boo, right? This is going to blow up. So what do? We use try and accept. We put try around that. We're going to take out some insurance on that particular line. And then if it fails, we're going to print this message and then say exit to get out. So if you get a good file, it works, skips the accept, then runs the thing, prints out the count. That's what's happening here. If, on the other hand, you get a bad file, it comes here, open, blows up, runs the accept, prints this out, and then quits. So that's how this one works with a bad file. And now we know traceback, right? So it's kind of a short lecture. We're done with Chapter 7. We open a file, we read the file, we take out white space at the end with rstrip, we use string functions. So this is kind of putting it all together, and it's kind of short little programs now, and so it's not, and starting now, we're going to start putting these things together and start actually doing work, because now we have, from the first few chapters, we have basic capabilities of Python. Now we have some data to work with. Now going forward, we're going to do increasingly sophisticated things with that data. So I can't wait to see you in the next lecture. Hello, and welcome to Chapter 8, Python Lists. So now we're sort of going to start taking care of business. We are going to make lists and dictionaries and tuples and really start manipulating this data and doing real data analysis, laying the ground for work for real data analysis. As always, these lectures, audio, video, slides, and even book are copyright Creative Commons attribution. So lists, dictionaries, and tuples, the next real three big topics we're going to talk about are collections. And we've been doing lists already, right? We've been doing lists when we were doing for loops. A list in Python is something that has a square braces. This is a constant list. Now, when I first talked to you about variables, I sort of oversimplified things. I said if you put like x equals 2 and then put x equals 4, the 2 and the 4 overwrite each other. A collection is where you can put a bunch of things in the same variable. Now I have to have a way to find those things. But it allows us to put multiple things in more than one thing in a variable. And so here we have friends that has 3 strings, Joseph, Glenn, and Sally, and we have carry on that has socks, shirt, and perfume. So that's the basic idea. So what's not a collection? Well, simple variables. Simple variables are not collections. Just like this example, I say x equals 2, x equals 4, and print x, and the 4 is in there and the 2 is somehow gone. It was there for a moment, and then it's gone. And so that's a normal variable. They're not collections. You can't put more than one thing in it. But when you put more than one thing in it, then you have to have a way to find the things that are in there. We'll get to that. So we've been using list constants for the last couple of chapters just because we have to use list constants. So we used, in the for loop chapter, we did lists of numbers. We have done lists of strings. That's strings, red, yellow, and blue. And you don't have to necessarily, have to have things all of the same type. This is a 3-item list that has a string red, the number integer 24, and 98.6, which is a floating point number. Here's an interesting thing, just as a side note. This shows that floating point numbers are not always perfectly represented inside of the computer. It's sort of an artifact of how they work. And this is an example of 98.6 is really 98.999. So when you see something like that, don't freak out. Floating point numbers are the ones that show this behavior. So interestingly, you can always, although we won't put a lot of energy into this, you can also have an element of a list be a list itself. So this is a outer list that's got 3 elements, 1, 7, and then a list that's 5 and 6. So if you look at the length of this, there is 3 things in it. Not 4, 3, because the outer list has 1, 2, 3 things in it. And an empty list is bracket, bracket. Okay? Like I said, we have been going through lists all along. We have iteration variables for I in. This is a list. We've been using it all along. Similarly, we've been using lists in indefinite loops are a great way to go through lists for friend in friends. There we have, goes through 3 times, out come 3 lines with the variable friend advancing through the 3 successive items in the list, and away we go. So again, lists are not completely foreign to us. Now, just like in a string, we can use the index operator, the square bracket operator, and we can look up items in the list. Sub 1, friends sub 1. Not surprisingly, using the European elevator rule, the first item in a list is sub 0. The second item is sub 1, and the third one is sub 2. So here when I print friend sub 1, I get Glenn, which is the second element. Just like strings. So once you kind of know it for strings, lists and the rest of these things make a lot more sense. Just remember that we're in Europe and things start with 0. Some things in these data items that we work with are not mutable. So for example, strings. When we ask for a lowercase version of a string, we were given a copy of that string. And that's because strings are not mutable. And we can see this by doing something like saying fruit sub 0 equals lowercase b. Now you'd think that would just change this to be a lowercase b, but it doesn't. Okay, it says string object does not support item assignment, which means that you're not allowed to reassign. You can make a new string and put different things in that new string, but once the strings are made, they're not changeable. And that's why when we call fruit.lower, we get a copy of it in lowercase. And so x is a copy of the original string, but the original string, once we assign it into fruit, is unchanged. Can't be changed. Lists, on the other hand, can be changed, and we can change them in the middle. This is one of the things we like about them. So here we have a list 2, 14, 26, 41, and 63. Then we say lotto sub 2. Of course, that is going to be the third item. Lotto sub 2 is equal to 28. Then we print it, and we see the new number there. So all this is saying is that we can change them, right? Strings, no, and lists, yes. You can change lists, but you can't change strings. So, the len function, we've used it for several things. We can say, len is used for strings, and it's used for lists as well. So the same function knows that when its parameter is a string, and when its parameter is a string, it gives us the number of characters in the string, and when it is a list, it gives us the number of elements in the list. And just because one of them is a string, it's still one element from the point of view of this list. So it has 1, 2, 3, 4 items in the list. Okay? So the range function is a special function. It's probably about time to talk about the range function. The range function is a function that generates a list, that produces a list and gives it back to us. And so you give the range function a parameter, how many items you want, and the range function creates and gives us back a list that is 4 numbers starting at 0, which is 0 up to but not including 3. Sound familiar? Yeah, 0 up to but not including 4. And so the same thing is true here. So we can combine the len and the range to say, to say, okay, well, len friends, that's 3 items, and range len friends is 0, 1, 2. And it also corresponds exactly to these items. So we can actually use this to construct loops to go through a list. We already have a basic for loop, right? We basically have a for loop that is the for each friend in friends, and out comes Happy New Year, Glenn and Joseph. If we also want to know what position we're at as the loop progresses, we can rewrite the exact same loop a different way and make I be our iteration variable and say I in range len friends. That turns this into 0, 1, 2. And then I goes 0, 1, 2. And then we can, in the loop, look up the particular friend that is the particular one we're interested in using the index operator, friends sub I, and then print Happy New Year. So these two loops are equivalent. Not that one. This loop and this loop. this loop is preferred unless you happen to need this value I, which tells you where you're at, in case maybe you're going to change something. You're going to look through something and then change it. So, but for what I've written here, they're exactly equivalent. Prefer the simpler one unless you need the more complex one. They both produce the same kind of output. We can concatenate lists, much like we concatenate strings with a plus. And you can think of the Python operators looking to its right and to its left and saying, oh, those are both lists. I know what to do with lists. I'm going to put those together. And so that produces a 2 3-long list become a 6-long list with the first one followed by the second one concatenated. It didn't hurt the original, A. C is a new list, basically. We can also slice lists. Feels a lot like strings, right? Everything's kind of like strings. For loops like strings, concatenation like strings, and now slicing like strings. And it is exactly the same. So 1 up to but not including. Just remember, up to but not including. The second parameter is up to but not including. So that starts at the sub 1, which is the second one, up to but not including 3, the third one. So this is 1, 2, and 3. So that's 41, comma 2. Starting at the first one, up to but not including the third one. We can similarly eliminate the first one, so that's up to but not including the fourth one. Starting at 0, 1, 2, 3, but not including 4. So that's this one. If we go 3 to the end, and again remember that they're starting at 0, so 3 to the end is 0, 1, 2, 3 to the end. The number 3 doesn't matter. So that's 374.15. And the whole thing. That's the whole thing. So these two things are the same. So slicing works like strings. Starting and up to but not including is the second parameter. There are some methods, and you can read about these online in the Python documentation. We can use the built-in function. It doesn't have a lot of use in sort of how we run when we're running programs, but it's kind of useful. I like it when I'm typing interactively, like, what can this thing do? So I make a list. List is a unique type. And I say, with dir, I say, what can we do with it? Well, we can append, we can count, extend, index, insert, pop, remove, reverse, and sort. And then you can sort of read up on all these things. I'll show you just a couple. We can build a list with the append. So this syntax here, stuff equals list, that's called a constructor, which says give me an empty list. You could also say bracket, bracket for an empty list. Whatever, you got to make an empty list. And then you call the append. Remember that lists are mutable, so it's okay to change it. So we're saying, okay, we started with an empty list. Now append to the end of that the word book, and then append to that 99. Wait a sec. That's a mistake. That's a mistake. So I have to fix this mistake. So watch me fix the mistake. Poof! Now my thing is magically fixed. Isn't that amazing? I have magic powers when it comes to slide fixing. I just snap my fingers and the slides are fixed. So here we go. We append to 99 and we print it out, and it's got book and 99, emphasizing the fact that they don't have to be the exact same kind of thing in a list. Then later we append cookie, and then it's book 99 cookie. Okay, so this append, we won't do it in line like this so often. We'll tend to do it in a loop as we're building up a list. But that's a way you start with an empty list and then programmatically grow it. We can ask, much like we do in a string, we can ask if an item is in a list. So here's a list called sum with these numbers in it. It's got 5 numbers in it. Is 9 in sum? True. Yes, it is. Is 15 in sum? False. Is 20 not in? That's a legal syntax. That is legal syntax. Is 20 not in sum? Yes, it's not there. Okay? They don't modify the list. Don't modify the list. They're just asking questions. These are logical operations, often used in if statements or while, some kind of a logic that you might be building. Okay, so lists have order. So when we were appending them, the first thing went in first, the second thing went in second, etc., etc. And we can also tell the list to sort itself. So one of the things that we can do with a list, now we're starting to see some power here, is say sort yourself. This is a list of strings. It can sort numbers. It can sort lots of things. Friends.sort. That says, hey there, dear friends, sort yourself. This makes a change. It alters the list and puts it, in this case, in alphabetical order. Glenn, Joseph, and Sally. It is muted. It's been modified, and so friend sub 1 is now Joseph because that's the second one. Okay, so the sort method says sort yourself. Now sort yourself, and it sorts, and then it stays sorted. So you're going to be kind of ticked about this particular side because there's a whole bunch of built-in functions that help with lists, and there's max, there's min, there's len, various things. And so we could, all those loops that I told you how to do, I was just showing you that stuff because I thought it was important. This is the simplest way to go through and find the largest, smallest, and sum, etc. So here's a list of numbers. We can say how many are there. That's the count. We can say what's the largest. It's 74. What's the smallest? That'd be 3. What is the sum of the running total of them all? 154. If you remember from a few lectures ago, these are the same numbers. And what is the average, which is sum of them over the length of them. Okay? So this makes a lot more sense. And if you had a list of numbers like this, you would simply say, what's the max? You wouldn't write a max loop. I just did that to kind of demonstrate how loops work. Demonstrate how loops work. So here is a way that you can sort of change those kind of programs that we wrote. So there's two ways to write a summing program. Let's just say instead of the data being in a list, we're going to write a while loop that's going to read a set of numbers until we say done, and then compute the average of those numbers. Okay, so let's say this is our problem. Read a list of numbers, and wait till the word done comes in, and then average them. So here's a little program that does that. We create total equals 0, count equals 0, make a infinite loop with while true, and then we ask to enter a number. We get a string back from this. Remember, raw input always gives us strings back. And then if it's done, we're going to break. This is the version of the if that does not require an indent. We just put the break up there. And so that gets us out of the loop when the time is right. So when the time is right over here. And then we convert the value to float. We use float to convert the input to a floating point number. And then we do our accumulation pattern. Total equals total plus value. Count equals count plus 1. So this is going to run. These numbers are going to go up and up and up and up. And then we're going to break out of it, calculate the average, and then print the average. Because that's a floating point number, so now the average is a floating point number. So that's one way to do it, right? That would be one way to write a program that does an average, is keep a running average as you're reading the numbers. But there's another way to do it that would work exactly the same way. And this is when you can start using lists. So come in, you say I'm going to make a list of numbers, just a mnemonic name, numList, is an empty list. Then I create another infinite loop that's going to read for enter a number, and if it's done, break. That kind of gets us out of it. Convert the value to an imp, convert the value to a float, the input value to a float, and then append it to the list. So now the list is going to grow. Each time we read a number, the list is going to grow. However many times we add the numbers, how many things are going to be in the list. So in this case, when we're at this point and we type done, there will be 3 numbers in the list because we will have run append 3 times. We'll have appended 3, 9, and 5. We'll have them sitting in a list, and we will have exited the loop. So now you say, oh, add up all the numbers in that list, and then divide it by the length of the list, and print the average. So these two programs are basically equivalent. The only time that they might not be equivalent was if there was 10 million numbers. This would use up 40 megabytes of your memory, which is actually not a lot of memory on some computers, but if memory mattered, this does store all those numbers. This one actually just runs the calculation. So if there's a really large number of numbers, this would make a difference. Because the list is growing and keeping them all, summing them all at the end. This is actually storing very little data. but for reasonably sized numbers, like thousands or even hundreds of thousands of numbers, these two approaches are kind of equivalent. And then sometimes you actually want to accumulate something a little more complex than this. You want to sort them or look for the maximum and look for something else, who knows what. But the notion of make a list and then append something to the list each time through the iteration and then do something with a list at the end is a rather powerful pattern. So this is also a powerful pattern. This is the accumulator pattern where we just have the variables accumulating in the loop. This one is one where we accumulate the data in the loop and then do the computations all at the end. To certain situations, we'll make use of these different techniques. Okay, so connecting strings and lists. So there's a method, a capability of strings that is really powerful when it comes to tearing data apart. It's called the split. So here is a string with 3 words and has blanks in between here. And abc.split says parse this string, look for the blanks, break the string into pieces, and give me back a list with one item for each of the words in the list as defined by the spaces. Okay? So it breaks it into 3 pieces and gives us that back in a list. It's very powerful. Okay? So we're going to split it and we get it back a list. There are 3 words, and the first word, stuff sub-0, is with. So there's a lot of parsing going on here. We could do this with for loops and a lot of other things. There would be a lot of work in this split. Given that this is a really common task, it's really great that this has been put into Python for us. Okay? So split breaks a string into parts and produce a list of strings. We think of these as words. We can access a particular word, or we can loop through all the words. So here we have stuff again, and now we have a for loop for each of that's going to go through each of the 3 words, and then it's going to run 3 times. Now chances are good we're going to do something different other than just print them out. But you see how that you quickly can take a split followed by a for and then write a loop that's going to go through each of the words without working too hard to find the spaces. You let Python do all the hard work of finding the spaces. Okay? So let's take a look at a couple of samples. Just a couple things to teach you a little more about split. Split looks at many spaces as equal to 1 space. So if you split a lot of spaces, it still just throws away all those spaces and gives us 4 words. 1, 2, 3, 4, and throws away all the spaces because it assumes that's what we want done. So that's nice. You can also have split. You can also have split on some other character. Sometimes you'll be getting data and they'll have used a semicolon or a comma or a colon or a tab character. Who knows what they've used, and your job is to dig that data out. So you can split based on a different character. Here, if we're splitting normally, with this is a normal split, it's not going to see the semicolons. It's looking for a space, and so all we get back is 1 item in the string with the semicolons. But if we switch and we pass semicolon as a parameter to split, then it will know to split it based on semicolons and gives us first, second, and third back. Okay, and then it gives us 3 words. So you can split either on spaces or you can split on a character other than a space. Okay? So let's take a look at how we might turn this into some of our common assignments that we have in this chapter, where we're going to read some of the mailbox data. Okay? So here we go with a little program. First 3 lines, we write these a lot. Open the file, write a for loop to loop through each line in the file. Then we're going to strip off the white space at the end of the line. 1, 2, 3. Do those all the time. And we're looking for lines, if you look at the whole file, we're looking at lines that start with from followed by a space. So if the line does not start with from followed by a space, that's a space right there, continue. So that's a way to skip all the lines that don't look like this. There are thousands of lines in this file and just a few that look like this. Okay? And so we're going to look and we're going to try to find what day of the week this thing happened on. So we're throwing away all the lines with this little bit of code. Then what we do is we take the line, which is all of this text, and then we split it. And we know that the day of the week is word sub 2. So this is word sub 0, this is word sub 1, and this is word sub 2. So this is word sub 0, sub 1, and sub 2. And so all we have to do is print out the sub 2, and we throw away all the lines except the from lines. We split them and take the third word, or word sub 2, and we can quickly create something that's extracting the day of the week out of these. Okay? So it's quick, because split does the tricky work. If you go back to the strings chapter, you saw that we did a lot of work to get this to happen. So here's even another tricky pattern. So let's say we want to do what we did at the end of chapter 6, the string chapter. Let's say we wanted to get back this little bit of data. Okay? So we can look at this and say, okay, let's split this, and this will be 0, 1, and 2, and 3, and 4, 5, and 6. We're splitting it based on spaces. Then the email address is words sub 1, right? So that email address is this little bit of stuff because it's in between spaces, right? So that's what we pull out. The email address is word sub 1. We've got that. So that's sitting in this email address variable. Then we don't really want the whole thing. We just want the part after the @ sign. And we could do a lookup of the @ sign. But you can also then do a second, come back. Zoop, there we come. You can also do a second split. Okay? So we're taking this variable here, email, which is merely this little part right here. And we are splitting it again, except this time we're splitting it based on an @ sign, which means it's going to bust it right here and find us 2 pieces. So pieces now is a list where the sub 0 item is the person's name and the sub 1 item is the host that their mail address is held from. Okay? And so then all we need to know is pieces sub 1. And pieces sub 1 is this guy right here. So that's pieces sub 1, and so we pulled it out. So if you go back to how we did it before, we were doing searching, and we were searching some more, and then we're taking slices. This is a little more elegant, okay, because really we split it, and then we split it, and we knew what piece we were looking at. So this is what I call the double split pattern, where you split a string into a list, then you take a thing out, and then you split it again, depending on what data you're looking for. This is just a technique. It's not the only technique. Okay, so that's lists. We talked about the concept of a collection where lists have multiple things in it, indefinite loops. Again, we've seen these things. It looks a lot like strings, except the elements are more powerful and they're more mutable. We still use the bracket operator, and we redid the max, min, and sum, except we did it in like one line rather than a whole loop. And something we're going to play with a lot is using split to parse strings, the single split, and then the double split is a natural extension of the single split. So, see you in the next lecture. Looking forward to talking about dictionaries. Hello, and welcome to Chapter 10 of Python for Informatics, the chapter on tuples. I'm Charles Severance. I'm your lecturer, and I'm the author of the textbook. As always, this material is copyright Creative Commons Attribution, including the video lectures, the slides, and the book. So, tuples are the third kind of collection that we've talked about. We've talked about lists, we've talked about dictionaries, and in the dictionary lecture we kind of alluded to tuples. We don't have to talk too much about tuples. We're really shortening the lecture by telling you that they're a lot like lists. They're a non-changeable list. And the syntax of them is pretty much the same as a list, except that we use parentheses instead of square brackets. Okay, and so like here is a 3 tuple with 3 items in it: Glenn, Sally, and Joseph. They are numbered 0, 0, 1, and 2, so the second thing is 1. So x sub 2 is indeed Joseph. We can pass them in as sequences to things like max or min or sum. And so the maximum of 192 is 9. And we can loop through them. So here is y, it's a tuple, it's 192, and iteration is going to go through the three values, right? And so it's going to print out 192, it runs the indented code once for each of the values inside the tuple. And so in this respect, they're very much like lists. But they're also different than lists in some real valuable ways. Tuples are immutable. And so if you recall when we talked about lists, we compared them to strings because both lists and strings are a sequence of elements where the first one is 0, 1, 2, etc. But if we look at a string, for example, and we have a 3-character string ABC and we want to change the third character, y sub 2, to D, it complains and says, no, you can't do that. But you can do it on a list. So if we have a list 987 and we say x sub 2 is 6, which is the third item, then the third item changes from 7 to 6. Okay, so this is mutable. This is not mutable. And tuples are also not mutable. They are like strings. They're sort of like lists in terms of what they can store, but they're like strings in the fact that they can't be changed. So here we create a 3-tuple, a 3-item tuple, and we try to change the third thing from 3 to 0, and it says you can't do that. Not mutable. Okay, so it's kind of like lists in the kind of data that we store in them, and it's kind of like strings in that you can't change them once you create them. So this parenthesis, this constant, is the moment of creation. Once you put the things in, you can't fiddle around with it. There's a bunch of other things you can't do with tuples. You think, why even use tuples? We'll get to that in a second. So here is a 3-tuple with the numbers 3, 2, 1. You can't sort it because if you sorted it, that would change it. You can't add to it. You can't append the value 5 to the end of it because that would change it. And you can't reverse it. So none of these are allowed. Those are things you can do with lists, but you can't do with tuples. And you can read the documentation, but we can also use that built-in dir function, that really awesome dir function, where we make a list and we say, hey, Python, what will you let me do with lists? Well, you can append, count, extend, index, insert, sort, reverse, remove, pop. Lots of things. Now we make a tuple and say, hey, Python, what can we do with tuple? Well, you can do a count or an index, which means you can't do all these other things. So this is sort of a very much a reduction. Because everything you can do with tuples you can do with lists, but not everything you can do with lists you can do with tuples. So why? Why did I just waste all this time introducing tuples? All they are is have parentheses. What good are they? Well, it turns out that they're much more efficient because Python doesn't have to deal with the fact that we as programmers might change them. Python can make them quicker, they can use less memory, all kinds of things that save a lot of processing time in Python. So when would you use a tuple? Well, in particular, if you're going to create some list that you're never changing, we prefer to use tuples. And there's a lot of situations in programming where we create what we think of as a temporary variable. And if we're going to create it, use it, and throw it away without ever modifying it, we prefer tuples in those kinds of situations. Okay, so we prefer tuples when we create things that are just temporary. It's the fact that they're temporary variables. They're like temporary lists because they're efficient. They're quick to make, and they're quick to get rid of, and they're quick to go through. Now, another really neat thing about Python that I really like is the fact that you can do sort of 2 assignments in one by putting a tuple on both the left and the right-hand side of the assignment statement. So if we think about an assignment statement, I like to think of it as having a direction that says these things go there. Well, in Python, you can actually send 2 things at the same time. The 4 goes into the x and the Fred goes into the y. This is a tuple. This is a tuple. You cannot have constants on this left-hand side. You can have variables or constants or expressions on the right-hand side, but this must be 2 variables. Similarly, in this, the 99 goes into A and the 98 goes into B. Now, it turns out that you can syntactically eliminate the parentheses if you really want. And so this leads to a prettier syntax, I think. It's the exact same thing with or without parentheses, where we basically just say, hey, come back, A and B are assigned to the tuple 99, 98. And so you can eliminate the parentheses as long as it's very clear what's going on in the tuple. And so this might be a little disquieting when you first see it, but it's just a tuple with no parentheses, and the 99 goes to the A and the 98 goes to the B. Now, it turns out we already did this. I sort of blew by this in the previous lecture in dictionaries because it allows us to go through the dictionary's keys and values with two iteration variables. And so if you remember, here's a dictionary. We put two items into it, and we can call d.items and get a list of tuples. A list of two tuples. Two tuples are a quick way of saying a tuple with two things in it. It's a two-element list that consists, each element is a two-tuple. And it's the key and the value. Key and the value. And so if we just print this out, it's a list. So then when we put this on a for loop, it is a list, but the things inside the list are each a tuple. Each thing inside the list is a tuple. So when this iteration variable goes to there, it is like this tuple is being assigned into kv, which means the key goes into k and the value goes into v. The name I picked for k and v do not matter. It's just the first one and the second one. So k and v point here. Then the next time through the loop, k and v point here. And so that's how Chen 2, CSEV 2 and Chenwin 4 happen. And so this is really a tuple assignment, or a tuple iterating through a list of a tuple iteration variable, or a pair of iteration variables walking through the list. Okay. We don't do this a lot in this. It's most heavily used for this situation where you're going through a dictionary and you want to see both the keys and the values, and then you use this method inside of dictionary called d.items. Another thing that's cool about tuples are that they're comparable. So less than, greater than, equals. And so they first compare the first leftmost thing. Then if that matches, they go to the second one, and then that one matches, they go to the third one. And so if we're asking, is 0, 1, 2 less than 5, 1, 2? And the answer is true. And it only looks at the 0 and the 5, and that's less than, so away we go. If we ask, is 0, 1, 2 million less than 0, 3, 4? Well, the 0 and 0 match, so it goes to the second one. 1 and 3, well, they don't match, and they're less than, so 1 is less than 3. So it's true, and it doesn't even look at these numbers because it doesn't have to, right? In this one, it doesn't look at those numbers. And now if we say, come here, is Jones Sally less than Jones Fred? Well, it compares this, they're equal, so then it has to look to the second one. Is Sally less than Fred? Well, no, because S is not less than F, and so that answer is false. Is Jones Sally greater than Adams? Sam, well, Jones is greater than Adams, so it never looks at these variables, and that turns out to be true. So these are comparable, which means we can use the less than or equal to, greater than or equal to, or not equal to. So we can use these operators on whole tuples. Now this turns out to be quite nice, because things that can be compared can also be sorted. Okay? So here is A, B, and C. A maps to 10, B maps to 1, C maps to 22. If I look at the items, I get back a list of two tuples, 3 two tuples. They are not sorted because dictionaries aren't sorted. A maps to 10, C maps to 22, and B maps to 1. The order that these come out in is not something that we can control. But if we put these items into a variable, call it T, T is the list of tuples basically, and then we tell it to sort, it can do comparisons between all these and it can sort them, and now they're sorted in key order, A, B, C. Now you'll never get any keys that match, so it never looks at the second one, right? Because there's one and only one key A or B or C. The value 10 never gets looked at. So this ends up sort by keys. Sort by keys. Okay, so this is a way to sort by keys. We take a dictionary, we get back a list of tuples, key value tuples, then we sort that sort that list of key value tuples, and then it's sorted by key. Okay, so that's one sort. There is a built-in function in Python called sorted, which takes as a parameter a list and gives you back a sorted version of that list. So we can collapse these operations by saying, oh, well, d sub items is this list of tuples, non-sorted, but sorted of d sub items is that same list of tuples, but then sorted. So immediately, in one step, we have A, B, and C properly sorted. And we can combine all this into one nice little for statement where we say for kv in sorted of d sub items. So this is now going to first sort the key value pairs by key, and then kv is going to run through them. So k is going to be A, 10, then k is going to be B, V is going to be 1, k is going to be C, V is going to be 22. So now we've printed these things out in alphabetical key order. Okay? So by adding sorted to d items, that means that this loop is going to run in key sorted order. Key sorted order. And that's because sorted takes a list and then returns, as it takes a list as unsorted list as input and returns a sorted list. Okay? Now, if we're doing something like our common problem of what's the most common word, what if we want to say what's the 5 most common words? In that case, we probably want to sort in descending order by the values, not the key. Okay? So we want to sort by the values instead of the key. So this is a situation where we're going to create a temporary variable. So here's how we're going to do it. Here is our dictionary with A10, and we want to sort now by the values. We want to, maybe see the most common or sort by the values. And so we're going to make a temporary list, and then we're going to loop through the items. So this is going to just loop through them, and it's going to loop through them in non-sorted order. And we are going to add, using the append operation, to this little list that we're making, but we're going to add a tuple that is value comma key. So if we make the value first and the key second in this tuple. So this syntax here of this parenthesis v comma k, that means make a 2-tuple with values from the v and k variable. And append a list. So you're going to end up with a list of 2 tuples. So if we take a look, when we're all done with this, each of these is a tuple. 10a gets appended, 22c gets appended, and it was simply the opposite order. The tuple, each of the tuples now has the value first and the key second. Value first, key second, value first, key second. So this is a bit of temporary data that we've created. This is a bit of temporary data that we've created. Then what we do is we call the sort method. Sort, take this list. Lists are mutable. The individual tuples can't be changed, but the order of the tuples can be changed because they are in a list. Temp.sort, and then we're going to say reverse equals true, so we sort from the highest down to the lowest. Okay? And now temp has been sorted, and now it is in a new order. 22, 10, 1 is what caused it to be sorted, so we know that the biggest value is 22, the key of C. Next biggest is 10 with a key of A, and the smallest is a value of 1 with a key of B. So the trick here is if we want to sort in some other way, we just construct a list where we put it in the order that we want it sorted, and this is more important now. The value is more important than the key. Now if we had another, like a 22F, it would sort first on the 22, and then it would sort the F1 after the C1, right? So we don't have any duplicates, but we could have this. We could have the key of C to 22, and we could have F also to 22. Okay, so take some time on this, get this one right. So now I want to show you a program that is going to show you the 10 most common words. We did a loop before where we did the most common word by doing a maximum loop at the end by looking through all of the counts in a dictionary and then picking the maximum. But what if you wanted the top 10? Right? That you don't want to write a loop for that. So we're going to use sorting. So here's what we're going to do. We're going to open a file. We're going to create a empty counts dictionary. Then we're going to write a for loop that reads each line, for line in F hand. Then I'm going to split each line into words based on the spaces using the dot split. Then I'm going to loop through each word in each line and use our histogram or dictionary pattern where I say count subword equals counts.get word comma 0. That basically says go look in counts. If the word key exists, give me back the value that's in that. Otherwise, give me 0. So this both creates the new entries and updates old entries all in one nice simple statement. So at the end of this bit of code right here, we are going to have counts with keyword word count pairs. Okay, so this is something we've done before. It's just dictionaries, reading, splitting, and then this pattern of how to accumulate in a dictionary. Then what we're going to do is we are going to make a new list called LST, and now we're doing this key value in the item. So this is going to go through the key value pairs in this list, which is the key value pairs from the dictionary, right? But then we are going to create this temporary list of tuples that are val comma key. So val is like 20 the, 14 hello. And that's what the list is going to look like, right? It's going to be tuples, but it's going to be the value and then the key rather than the key and the value. This one here is key value. This one here, LST, is value key. Now that we have a list that's value comma key, we are just going to sort it because now it's going to sort based on the first thing in that tuple, and we're going to reverse it so the biggest values are near the top. And so when we're all done, this is going to be a list, except it's going to be sorted based on the value. So that's just one step to sort it. So this is a good example of how we sort of go through some work. We get a data structure, a list, the way we want it, and now we can sort of leverage the built-in sort. We had to prepare a list so we could use the built-in sort. We could do this by hand, but it'd be very difficult. But it's easier to say, I think I'll make a list, and then I'll sort it. Okay, so I made two lists basically. I made the original one. Now I made this one just for the purpose of sorting. And now what I'm going to do to print out the top 10 is I am going to write a for loop, val key. Remember, this list, LST, is value key. And I'm going to say for val key in list, using list slicing, up, starting at 0, up to but not including 10, which is indeed the first 10 items. Now I'm going to print out key value, so it's going to be like, it's going to print out the 22, Fred 16, and it's only going to first print the first 10. So this list is in val key order, the tuples are val key order, and so I'm going to print it out in key val just so that I print out in a way that makes the most sense. And so this is a simple way to do a simple histogram of the occurrence of words in a file. So again, you should know this. You should know every line. You should know every line. Go back, review a couple times, but you should know the meaning of every line of this. And if you do, that's really good. So as you become more powerful and capable inside Python, you will realize that there are sometimes even shorter ways of doing things. Now, what I'm showing you here is not that different than what was on the previous page. It's just really dense, but you have to concentrate. So if I want you to understand what's on that previous page, if you don't understand this, don't feel bad. I'm going to explain it to you, but don't feel bad if you don't get it. Okay? So I'm just going to explain it. If it doesn't feel right to you, go back and look at the previous page. Okay, so here we go. I'm going to have a dictionary, and then I'm going to print in one line, sorted by value. So we'll start from the inside out. So this is a thing called list comprehension. It looks like a list constant because we start with square brackets. But this is a Python syntax that says construct dynamically a list of tuples v, comma k, and I would like you to loop through the items with k and v taking on the successive values. So this is creating that reversed list where value and key are the order of the items in each tuple, and it's going to do that. So this is going to expand. It's sort of like it goes, expands this. It makes a temporary list right now. Now, if you look on the previous slide, we called that thing LST, but here we don't even call it LST. And then once we have the list of tuples in value key order, then we simply take and pass that into sorted. This is a function call, the sorted function, and then, now I'm not reversing it, but the print statement prints out its ascending order of the value, 1, 10, 22. Okay, so this, you can make these more dense once you're a little more comfortable with what's going on. It's sometimes easier to construct something that seems to have steps where you can put, you can put a debug print here, you can put a debug print here, you can do a debug print here, and you kind of see what's going on, right? Whereas once you really understand this, you can write some more dense Python. When you understand this, it's okay, right? So I'm not saying you're supposed to understand this, but I just want to point out that it's possible to do this in a tighter fashion. So tuples are like lists, except that you can't change them, right? You can't change lists, and you can compare them, you can sort them, you can sort lists of tuples. You can't sort within the tuple itself. The two values on the left-hand side of an assignment statement, we can use sorted, and we've played with sorting dictionaries by key and value. So that's kind of the end of this lecture, and so at this point I just want to kind of congratulate you on making it through the first 10 chapters of the book. So I'll drink a cup of tea to you. Here's your cup of tea. Here's my toast to you. In my Slytherin cup, and so it's time for a graduation ceremony. So I'll give a little graduation speech here with my graduation hat on, and this is my Slytherin wand. And so so the reason I'm congratulating you at the end of this chapter is that at this point you kind of know all the fundamentals of programming. Programming really comes down to what's called algorithms and data structures. Sometimes we solve a problem by a clever series of steps that we put together, and sometimes we solve a problem by creating a clever data structure. And so the first few chapters were about algorithms, steps, loops, functions, very procedural, how you sort of create these threads of stepping and do things a bunch of times or skip around or whatever. And in the last 3 chapters that we've covered, we're talking about data structures. And programming power comes when you combine algorithms and data structures. Now in the next chapters, starting with chapter 11, regular expressions, we're going to learn sort of more clever ways of doing the same thing. So you kind of know how to do a lot of stuff now. From this point forward, you'll see, oh boy, that's more clever. Or we'll use a database. Oh, that's more clever. But it's not fundamentally different. And so that's why it's important for you to understand before you leave this moment, to understand everything that we've covered so far. Loops, functions, strings, files, tuples, lists, dictionaries. because they're kind of the foundation, and everything else will just kind of be a subtle refinement slash improvement. So once you understand that, you've kind of begun. You become a basic programmer, and I like poof, like I like magically Asperio you and turn you a Pythonio and something like that. Okay, enough of the Harry Potter reference. Thank you for spending all this time with me. If you've gotten this far, I really appreciate it. And of course, it's really just the beginning, but I hope that it has been a good beginning. Thank you. Hello again, and welcome to Chapter 9, Python Dictionaries. As always, this lecture is copyright Creative Commons attribution. That means the audio, the video, the slides, and even my scribbles. You can use them any way you like, as long as you attribute them. Okay, so this is the second chapter where we're talking about collections. And the collections are kind of like a piece of luggage in that you can put multiple things in them. Variables that we've talked about sort of starting in Chapter 2 and Chapter 3 were simple variables. Scalar. They're just kind of one thing, and as soon as you put another thing in there, it overwrites the first thing. And so if you look at the code, x equals 2 and x equals 4, the question is, where did the 2 go? Right? The 2 was there, x was there was a 2 in there, and then we cross it out and put a 4 in there. This is sort of the basic operation of the assignment statement. It's a replacement. But a dictionary allows us to put more than one thing, not using this syntax, but it allows us to have a variable that's really an aggregate of many values. And the difference between a list and a dictionary is how the values are structured within that single variable. The list is a linear collection indexed by integers 0, 1, 2, 3. If there's 5 of them, it's 0 through 4. Very much like a Pringles can here, where they're just stacked nicely on top of each other. Everything's kind of organized. We talked about it in the last lecture. This lecture we're talking about dictionaries. Dictionaries very powerful. Its power comes from a different way of organizing itself internally. It's a bag of values, like just stuffs in it. It's not in any order. Big stuff, little stuff. Things have labels. You can also think of it like a purse with just things in it. It's not like stacked. It's just stuff moves around as you're going, and it's a very good model for dictionaries. And so dictionaries have to have a label because the stuff is not in order. There's no such thing as the third thing. There is the thing with the label perfume. There's the thing with the label candy. There's the thing with the label money. And so there's the value, the thing, the money, and then there's always also the label. We also call these key value. The key is the label, and the value is whatever. And so these pink things are all labels for various things that you can put in the purse. So you could say to your purse, hey purse, give me my tissues. Hey purse, give me my money. And it's in there somewhere, and the purse sort of gives you back the tissues or the money. And it's Python's most powerful data collection is the dictionaries. And it's when you get used to wielding them, you'll say like, whoa, I can do so much with these things. And at the beginning, you're just sort of learning sort of how to use them without hurting yourself. But they're very powerful. It's like a database. It allows you to store very arbitrary data organized in however you feel like organizing it in a way that advances the cause of the program that you're writing. And we're still kind of at the very beginning, but as you learn more, these will become a very powerful tool for you. Dictionaries have different names in different languages. Perl or PHP would call them associative arrays. Java would call them a property map or a hash map. And C# might call them a property bag or an attribute bag. And so they're just the same concept. It's keys and values is the concept that's across all these languages. Just a very powerful. And if you look at the Wikipedia entry that I have here, you can see that it's a concept that we give different names in different languages. Same concept, different names. So like I said, the difference between a list and a dictionary, they both can store multiple values. The question is how we label them, how we store them, and how we retrieve them. So here's an example use of a dictionary. I'm going to make a thing called purse, and I'm going to store in purse, this is an assignment statement, purse sub money. So this isn't like sub 0, this is sub money. So I'm actually using a string as the place. And So I'm going to say stick 12 in my purse and stick a post-it note that says that's my money. Candy is 3, tissues is 75. And if I look at that, it's not just the numbers 12, 3, and 75 as it would be in a list. It is the connection between money and 12, tissues is 75, candy is 3. And in the key value, that's the key and that's the value. So candy is the key and 3 is the value. Now, I can look things up by their name. Print purse sub candy. Well, it goes finds it, asking, hey, purse, give me back candy. And it goes and finds the value, which is 3, and so out comes a 3. We can also put it on the right-hand side of an assignment statement. So purse sub candy says, give me the old version of candy, and then add 2 to it, which gives me 5, and then store it back in that purse under the label candy. So we see candy changing to 5. And so this is a place, and you could do this with a list, except these would be numbers. You could say purse sub 2 is equal to purse sub 2 plus 2, or whatever. But in dictionaries, there are labels. Now, they're not strings. Strings is a very common label in dictionaries, but it's not always strings. You can use other things. In this chapter, we'll pretty much focus on strings. You could even use numbers, and then you would get a little confused. But you can. So here's sort of a picture of how this works. So if we take a look at this line, purse sub money equals 12, it's like we are putting a key value connection. Money is the label for 12, and then we sort of move that in. And it's up to the purse to decide where things live. If we look at the next line, we're going to put the value in with 3 in with the label candy, and we're going to put the value 75 in with the label of tissues. And when we say, hey, purse, print yourself out, it just goes and pulls these things back out and hands them to us. And what it's giving us both the label and the value. And it's necessary to do that because it's just like 12, 75, and 3. What exactly is that? And so this syntax with the curly braces is what happens when you print a dictionary out. The same thing happens when we're sort of printing purse sub candy, right? Purse sub candy, it's like, dear purse, go and find the candy thing. Look at that one, look at that one. Oh, yep, this is candy. But what we're looking for is the value, and so that's why 3 is coming out here. So go look up under candy and tell me what's stored under candy. These can be actually more complex things. I'm just keeping it simple for this lecture. And then when we say purse sub candy equals purse sub candy plus 2, well, it pulls the 3 out, looking at the label candy, then adds 3 plus 2 and makes 5, and then it assigns it back in. And then that says, oh, go place this number 5 in the purse with the label of candy, which then replaces the 3 with a 5. Okay? And if we print it out, we see that the new variable, or the new candy entry, is now 5. Okay? So if we just sort of put these things side by side, we create them sort of both the same way. We make an empty list and an empty dictionary. We call the append method because we're sort of just putting these things in order. You got to put the first one in first. So it's not telling you where. You kind of know that this will be the first one because you're starting with an empty one, and this will be the second one. We put in the values 21 and 183, and then we print it out, and it's like, okay, you gave me the values 21 and 183. I will maintain the order for you. There's no keys other than their position. The position is the key, as it were. If I want to change the first one to 23, well, I say list sub 0, which is this, and then change that to 23. So this is sort of used as a lookup to find something. Can be used on either the right-hand side or the left-hand side of an assignment statement. Comparing that to dictionaries, I'm going to put a 21 in there, and I'm going to put it with the label age. Then I'm going to put 182, put that in with the label course. So we don't have to like make an entry. The fact that the entry doesn't exist, it creates the age entry and sticks 21 into it. Creates the course entry, sticks 182 into it. We print it out and says, oh, course is 182 and age is 21. This emphasizes that order is not preserved in dictionaries. I won't go into like great detail as to why that is. It turns out that that's a compromise that makes them fast using a technique called hashing. It's how it actually works internally. Go Wikipedia hashing and take a look. But the thing that matters to us as programmers primarily is that lists maintain order and dictionaries do not maintain order. Dictionaries give us power that we don't have in lists. I mean, they're very complementary. Now, there's not this one that's better than the other. They're very complementary. Different kinds of data is either better represented as a list or as a dictionary, depending on the problem you're trying to solve. And in a moment, we'll be writing programs that are using both. So if we come down here and I say, okay, stick 23 into assignment statement, into DDD sub age, well, that will change this 21 to 23. So when we print it out. So you can, this part where you look something up and change the value, you can do either way. It's just how you do it here is a little bit different. Okay? So let's look through this code again. And so I like to use the word key and value. Key is the way we look the thing up, and in list, keys are numbers starting at 0 and with no gaps. In dictionaries, keys are whatever we want them to be. In this case, I'm using strings. And then the value is the number we're storing in it. So we create this kind of a list with those kinds of statements. This statement creates this kind of a thing. Now, if we think of this assignment statement as moving data into a place, a new item of data into a place, it's looking at this thing right here, right? It's like that's where I want to move it, and so it hunts and says, look the key up, and that's the one that I'm going to change. And then once it knows which it's going to change, then it's going to take the 23 and it's going to put the 23 into that location. And so that's how this changes from that to that. Similarly, when we get down to here, we're going to stick 23 somewhere, and this expression, this lookup expression, the index expression, DD sub age, is where we're going to put it. So we're looking here. Where is that thing? Well, that thing is this entry in the dictionary. And so now when we're going to store the 23, we know where the 23 is going to go. It's going to overwrite the 21, and so the 21 is going to change to 23. Okay, so they're kind of similar. There are things that work similar in them, and then there are things that work differently in them. We can make literals, constants, with curly braces, and they look just like the print. That's one nice thing about Python. And when you print something out, it's showing you how you can make a literal. And basically, you just open with a curly brace and say Chuck : 1, Fred 42, Jan 100, and we're making connections. Key value pair, key value pair. We print it out, and no order. They don't maintain order. Now, they might come out in the same order, but that's just lucky, right? All the ones I've shown you so far don't come out in the same order, which is good demonstrated. If it one time came out in the same order, that wouldn't be broken. It's not like it doesn't want to come out in the same order. It's just it's not internally stored, and you add an element and it may reorder them. You can do an empty dictionary with just a curly brace, curly brace. So I'm going to give you another example, and I'm going to show you a series of names, and I want you to figure out what the most common name is and how many times each name appears. Now, these are real people. They actually work on the Sakai project. Stephen, Zhen, and Chen, and me. So these are people that are actually in the data that we use in this course. Okay, and so I think I'll show you about 15 names, and you're to come up with a way. I'm going to show them to you one at a time. You need to come up with a way to keep track of these. Okay, so I'll just, with no further ado, I will show you the names. Okay, so that's all the names. Did you get it? You might have to go back and do it again. How did you solve the problem? What kind of a data structure did you build to solve the problem? Or did you just say, wow, that's painful. I think I will learn Python instead than solving that problem. Okay? So pause the video if you want and write down, or go back, write down what you think the number of the most common name is and how many times. Okay, now I'll show you. So here is the whole list. It's all of them. And now that we see all of them, we use our amazing human mind and we scan around and look at purpleness and all that stuff. And then we go like, oh, this is so much easier problem when I'm looking at the whole thing. And I think that the most common person is Jen. And I think we see Jen. I think we see Jen 5 times. And I think CSEV is 1, 2, 3, and Chen Wen is 1, 2, and Stephen Marquardt is 1, 2, 3. So the question is, what is an effective data structure if you're going to see a million of these? What kind of data structure would you have to produce? Because you can't keep it in your head. Even this number of people, you can't. Even this amount of data, no way you can keep it in your head. You have to come up with some kind of a variable, as it were, just like largest so far was a variable, some kind of variable that gets you to the point where you understand what's going on. And so this is the most common technique to solve this problem, where you keep a running total of each of the names. And if you see a new name, you add them to the list. So CSEV, and then you give them a 1. And then you see Zhen, and you give her a 1. And then you see Chen, and you give her a 1. And then you see CSEV again, and you give him a 2. And you see and a 2, and a 2, and a 1, right? And so then when you're all done, you have the mapping, right, of these things, and you go, okay, let me look through here and find the largest one. That's the largest one, and so that must be the person who is the most. So you need a scratch area, a data structure, or a piece of paper, as it were. And so that's exactly what dictionaries are really good at. You can think of this as like a histogram. You know, it's a bunch of counters, but counters that are indexed by a string. So we use a lot of this. And so this is a pattern of many counters with a dictionary, simultaneous counters. We're counting a bunch of that. We're looking at a series of things, and we're going to simultaneously keep track of a large number of counters rather than just one counter. How many names did you see total? Whatever, 12. But how many of each name did you see is a bunch of counters. So it's a bunch of simultaneous counters. So a dictionary is great for this. Dictionary is great for this. When we see somebody for the first time, we can add an entry to the dictionary, which is kind of like going, oh, CSEV 1, and then Chen Wen 1. Now these don't exist yet, right? So we got CSEV 1 and Chen Wen 1. So that creates an entry and sticks a 1 in it. And then mapping between the key CSEV and the value 1, the key Chen Wen and the value 1. And then we say, hey, what's in there? Oh, we got a CSEV is 1 and Chen Wen is 1. And then we see Chen Wen's second time, so we'd add another number right there. So this old number is 1. We add 1 to it and we get 2. And then we stick that back in. And then we do the calculation. We do a dump and say, oh, there's 2 in Chen Wen and 1 in CSEV. Okay? So this is a great data structure for these simultaneous counters. Like, what's the most common word? Who had the most commits? Da-da-da-da-da-da-da-da. Now, everything we do, we have to figure out, like, when you're going to get in trouble with Python. When Python's going to give you the old thumbs down and say, oh, you went too far. So one thing Python does not like is if you reference a key before it exists. We'll look at in a second how to work around this. But if you simply create a dictionary and say, oh, print out what's under CSEV, it gives you a traceback. It's like, I'm going to inform you that that's not there. And it says key error CSEV. Now, the thing that allows us to solve this is the in operator. We've used the in operator to see if a substring was in a string or if a number was in a list. So this in operator says, hey, ask a question. Is the string CSEV a current key in the dictionary CCC? Is the string CSEV a current key in the dictionary CCC? And it says false. So now we have something that doesn't give a traceback that can tell us whether or not the key is there. So if you remember the algorithm, the first time you see it, you set them to 1, and every other time you add 1 to them. So this is how we do that in Python. So here's how we implement that program that I just gave you in Python. So here's our names. It's shorter, so my slide works better. Here's variable, our iteration variable. It's going to, go through all 5 of these one at a time. And within the body of the loop, we have an if statement. If the name is not currently in the counts dictionary, counts is the name of my dictionary. If the name is not currently in the counts dictionary, I say count subname equals 1. Else, that must mean it's already there, which means it's okay to retrieve it. Counts subname plus 1, we're going to add 1 to it and stick it back in. Okay? And so when this finishes, it's going to add entries and then add 1 to entries that already exist and not trace back at all. And when we print it out, we're going to see the counts. And literally this could have gone a million times and it would just be fine and it would just keep expanding. Okay? So this pattern of checking to see if a key is in a dictionary, setting it to some number, or adding 1 to it is a really, really common pattern. It's so common, as a matter of fact, that there is a special thing built into dictionaries that does this for us. Okay? And there is this method called get. And so counts is the name of a dictionary. Get is a built-in capability of dictionaries. And it takes 2 parameters. The first parameter is a key name, like a string like CSEV or Chenwen or Marquard. And then the second parameter is a value to give back if this doesn't exist. It's a default value if the key does not exist and there's no traceback. So this way you can encapsulate, in effect, an if then else. If the name parameter is in the counts, print the thing out, otherwise print 0. So this expression will either get the number if it exists, or it will give me back a 0 if it doesn't exist. So this is really valuable, all right? This is really valuable. That's a really bad smiley face. So this is really valuable because it, once we understand the idiom, it really takes 4 lines of code and turns it into 1 line of code. Because we're going to be doing this if then else all the time. Now, so we can reconstruct that loop a lot easier and a lot more cleanly using this idiom, right? It's something that looks kind of complex, but you'll get used to it really fast. Okay? So we have everything here is the same. We create an empty dictionary. We have 5 names to go through. We're going to write a for loop, and it's going to go through each of those. And then we're going to say count subname equals counts.get the value stored at name, and if you don't find it, give me back a 0, and then whatever comes back, either the old value or the 0, add 1 to that, and then take that sum and stick it in counts name. Okay, so this is either going to create or it's going to update. If there is no entry, it's going to create it and set it to 1. If there is an entry, it's going to add 1 to the current entry. Okay? So this line is kind of an idiom. Read about it in the book, figure it out, get used to the notion of what this is doing. Understand what that is doing. Okay? Because I'm going to start using it as if you understand it. So the next problem is a problem of finding the most common word. So finding the most common, the top 5, is often a trigger that says use dictionaries. Because if you're going to have to count things up, you're going to, you don't know what the most common thing is at the beginning. First you have to count everything up, and dictionaries are a great way to count. So here's a little problem, and I would like you to read this text and find me the most common word in the text and tell me what the most common word is and how many times it occurs. Ready? I'm going to give you 1,000th of a second, just like I would give a computer. I would expect it to be able to do this in 1,000th of a second. There you go. Okay, I gave you 5 seconds. Time's up. Did you get it? Or did you say to yourself, you know what? I hate that. It's no good. I think I'll write a Python program instead. And he'll probably show me a Python program if I wait long enough. So here's a slightly easier problem from the first lecture. Ready? It's the same problem. Find the most common word and how many times the word occurs. you get it? I believe the answer is, and I could look really dumb here. Oops. The answer is the, and I think it's 7 times. So that's the right answer. Okay? Again, things humans are not so good at. So here's a piece of code that's starting to combine some of the things we've been doing in the past few chapters all together. We are going to read a line of text, split it into words, count the occurrence, how many times each word occurs, and then print out a map. So here's what we're going to do. We're going to say, okay, start a dictionary, an empty dictionary, read a line of input, then split it. Remember, the split takes a string and produces a list. So words is a list, line is a string, and then we'll print that out. Then we're going to write a for loop that's going to go through each of the words, and then use this idiom, count subword equals counts.get word comma 0 plus 1. So this is going to do exactly what we talked about in the previous couple slides back. Either create the entries or add to those entries. Okay? And then we're going to print them out. So here's what that program does when it prints out. Now this is actually one long line. I'm just cutting it so you can see it. Here's this line we enter, and the words the, there's 7 of them. Then it takes this line and splits it into a list, and there is the beginning and end of the list. The list maintains the order. So the list simply breaks all these words into separate words in a list of strings from one string to many strings. This is many strings. And so the and the spaces are gone, and so now here's this list. And then what we're going to do is we are going to run through the list, and we are going to keep running totals of each of the words in the list. And then when we're done with the list, we're going to print out the contents of that dictionary, and we can inspect it and go like, let's look for the biggest one. No. It's kind of like looking for the largest, and like, oh, 7, that's the largest, and the largest word is the. Okay? So that's how the program runs. It reads a line, splits it into a list of words, and then accumulates a running total for each word, and then we hand inspect to see what the most common word is. Okay? Oh, no, I don't want that song again. There we go. And so here we have in this kind of a smaller fashion, we make a dictionary. This entering a line of text is here. It's all one line. We do the split, and then we print the words out. And so that split creates a list of strings from a single string based on where the blanks are at. Chop, 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 chop. And then here at counting, we're going to loop through each of the words one at a time and use this idiom, count subword equals counts.get word comma 0 plus 1, which is going to create and or update. And then we print the counts out, and that comes out there. Okay? So again, this is the new thing we've done. Everything else here we've kind of seen before. Now we can also loop through dictionaries with for loops. The for loop, we've put all kinds of things over here. We've put strings over here. We've put lists of numbers over here. We've put files over here. And basically what it really says is, if this is a collection of things, run this little indented code once for each item in the collection. And key then becomes our iteration variable. And key is very mnemonic here. It doesn't know that they're keys. And so keys, the key here is that, there's a bit. The important concept here is that dictionaries are key value pairs. And so this is only one variable. And so it actually decides that they've decided it goes through the keys, which is actually quite useful. So key is going to take on the successive values of the labels, not the successive values of the values stored at the labels. But it's really easy for us to retrieve the contents at that label, counts sub key. So we're going to use the key, Chuck, Fred, Jan, to look up the 142, 100. And so it prints out the key and then the value at it, the key and the value at it, and the key and the value. And so we're able to sort of go through the dictionary and look at all the key value pairs, which is the common thing that you really want to do. Okay? Now there's some methods inside of dictionaries that allow us to convert dictionaries into lists of things. And so if you simply take a dictionary, so here's a little dictionary with 3 items in it, and we can say list sub and then give a dictionary name right there, and then that converts it into a list, but it's just a list of the keys. We can also say jjj.keys, kind of do the same thing, say give me a list consisting of the keys. And then jjj.values gives you a list of the values, 1, 42, and 100. Of course, they're not in the same order. Now, interestingly, as long as you don't modify the dictionary, the order of these two things corresponds. As long as in between here you're not changing it. So the first Jan maps to 100, Chuck maps to 1, and Fred maps to 42. So the order, you can't predict the order they're going to come out, but these two things will come out in the same order, whatever that order happens to be. Okay, and so there's one more thing. So we got the keys, we got the values, and we got a thing called items. Items also returns a list. It's a list, but it's a list of what Python calls tuples. That's what the next chapter is about. We'll talk more about tuples in the next chapter. A tuple is a key value pair. So this list has 3 things in it. 1, 2, 3. The first one is Jan maps to 100. The second one is Chuck maps to 1. The third one is Fred maps to 42. So just kind of bear with me for a second. We'll hit this a little harder in the next chapter. But the place that the idiom where this works really beautifully is on a for loop. Now, for those of you who have programmed in other languages, this will be kind of weird because other languages have iterations, but they don't have 2 iteration variables. Python has 2 iteration variables. It can be used for many things, but one of the things that it's used for that's really quite nice is we can have 2 iteration variables. This JJ items returns pairs of things, and then AAA and BB are iteration variables that sort of move in synchronized, are synchronized as they move through. So AAA takes on the value of the key, BBB takes on the value of the value. And then the loop runs once, then AAA is advanced to the next key, and BBB is advanced to the next value simultaneously, synchronized. Then they print that out. Then it advances to the next one, and they print that out. So they are moving in a synchronized way. Now, again, the order Jan, Chuck, Fred is not the same, but the correspondence between Jan 100, Chuck 1, and Fred, that's going to work. And so basically, as these things go, they work their way through whatever order they're stored in the dictionary. So this is quite nice. 2 iteration variables going through key value. Now, if I was making these names mnemonic, and they made more sense, I would call this the key variable, and that be the value variable. But for now, I'm just using kind of silly names to show you that key and value are not special. They're not Python reserved words in any way. They're just a good way to name these things, key value pairs. Okay? Okay. Now we're going to circle all the way back to the beginning, all the way back to the first lecture. And I gave you this program, and I said, don't worry about it. We'll learn about it later. Well, now later. At this point, you should be able to understand every line of this program. This is the program that's going to count the most common word in a file. Okay? So let's walk through what it does. And hopefully by now, this will make a lot of sense. Okay? So we're going to start out, we're going to ask for file name. We're going to open that file for read. Then, because we know it's not a very large file, we're going to read it all in one go. So handle.read says, read the whole file, new lines and all, blanks, new lines, whatever, and put it in the variable called text. It's just mnemonic. Remember, I'm starting this one, I'm using the mnemonic variable names. Then go through that whole string, which was the whole file, go through and split it all. New lines don't hurt it. New lines are treated like blanks, and it understands all that. It throws the new lines away and the blanks away and splits it into a beautiful list of just words with no blanks. And the list of the words in that file ends up in the variable words. Words is a list. Text is a string, words is a list. Then what I do is the pattern of accumulating counters in a dictionary. I make an empty dictionary. I have the word variable that goes through all the words, and then I just say count subword equals counts.get word comma 0 plus 1. That, like we just got done saying, it both creates and or increments the value in the dictionary as needed. So now at the end of at this point in the program, we have a full dictionary with the word colon count. Okay, and there's many of them. You know, all the words, all the counts, not in any particular order. So now what we're going to do is we're going to write a largest loop. Find the largest, which is another thing that we've done. So not only do I need to know what the largest count I've seen so far, I need to know what word that is. So I'm going to set the largest count we've seen so far to none, set the largest word we've seen so far to none, and then I'm going to use this 2 iteration variable pattern to say go through the key value pairs, word and count, in counts items. So it's going to just go through all of them. And then I'm going to ask if the largest number I've seen so far is none, or the current count that I'm looking at is greater than the largest I've seen so far, keep them. Take the current word, stick it in biggest word so far. Take the current count, stick it in the biggest count so far. So this is going to run through all of the word count pairs, word count key value pairs, and then when it comes out, it's going to print out the word that's the most common and how many times. So if we feed in that clown text, it will run all this stuff and print out, oh, the is the most common word, and it appeared 7 times. Or if I print the stuff that was 2 slides back, words.txt, from the actual textbook, then it says the word 2 is the most common and it happened 16 times. So I could easily, throw 10 million words through this thing and it would just be totally happy, right? And so this is not that complex of a problem, but it's using a whole bunch of idioms that we've been using. The splitting of words, the accumulation of multiple counters in a dictionary, and so it sort of is the beginning of doing some kind of data analysis that's hard for humans to do and error prone for humans to do. And so we're reviewing collections, we've introduced dictionaries, we've done the most common word pattern, talked about that, the lack of order, I've hit that a bunch of times, and we've looked ahead at tuples, which is the third kind of collection that we're going to talk about, and they're actually in some ways a little simpler than dictionaries and simpler than lists. So see you in the next lecture, chapter 10, tuples. So welcome to chapter 11, regular expressions. Now at this point I really am assuming that you've mastered the material in the first 10 chapters of the book. You know what a loop is, you know what a dictionary is, you know what a list is. You don't have to write super complex programs, but I want to be able to use those in a sentence and not have you say like, well, could you define that? Well, if I start talking about things that are hard for you to understand, that's what those previous chapters and any previous courses are for. So regular expressions are they're a very interesting thing in programming. They are themselves a programming language. They're like this own little tiny mini programming language that actually you can use in many different programming languages. So you can use them in Python, you can use them in JavaScript, you can use them in Java, and pretty much any time you have some kind of a complex string matching or extraction, you will run across regular expressions. Now the other thing that's really important to point out is that you don't really need to know regular expressions. As what I'll be showing you throughout this lecture is 2 ways of doing things. One is kind of like the using simpler capabilities that takes a little longer, and then using regular expressions, which tend to be more succinct ways, but then more complex. So a regular expression itself is a programming language that is specialized in string matching. It itself is a programming language. And the simple version of it is that it's just really clever wildcard expressions for matching, parsing, and extracting information from strings, which is a lot of what we've done so far in this class. And it's just a smart find or a search. Here's the Wikipedia definition of regular expression. And Some of you are going to like regular expressions. As a matter of fact, some of you might say, why didn't we start doing regular expressions at the very beginning? It'll be very natural to you because some people want to think deeply about a problem and come up with this beautiful expression of the problem. Then they go like, here, computer, this is my expression. Others like to use simpler multi-step. I find them fun, but they are their own language, and it's a language of characters rather than a language of tokens. So if you think of print and for and if, those are all tokens. They're word-like things, but in regular expressions, a single character. And it comes from a time in the 70s, and so it's a very compact little language. Regular expressions are a mark of coolness, for some value of cool. If you know regular expressions, people are like, oh, and they're not that hard to know, but they're so funky and weird that that it's kind of special when you know it. So you should be proud once you understand regular expressions. It's sort of a mark of awesomeness, like a little regular expression tattoo, like my little tattoo that I have here. So regular expressions, when you learn it, it's like you've gotten yourself a really cool tattoo. So here's a quick guide. And I didn't write this quick guide because, I wrote this quick guide because I need it. As a matter of fact, I have it with me, have it printed out on a piece of paper. And some of the regular expression stuff I remember, and I can write simple regular expressions without looking at a guide, but other ones I need a little bit of help. So if we take a look at sort of this table, the way this table works is I told you that regular expressions is a language of characters. And so instead of if or a tab or something having meaning, what it is a character has meaning. So if you're in a regular expression, caret means the beginning of the line. Dollar means the end of the line. It doesn't mean caret or dollar. Caret and dollar are special characters. So it's like a programming language, dot, asterisk, plus, brackets, and parentheses, among other characters, have meaning in this little programming languages. Little programming language. We make a little program that's really tiny and really short, which you'll see just in a moment. So if you're going to make use of the regular expressions, you have to import regular expressions. So you have to put that at the beginning of your application. You have to say import RE, so the RE library, and then you make use of these things with re.search. And so search is the name of a function that's part of the regular expression library. You pass in parameters, and it's kind of like using the find method on strings. And there's a couple of different ways that you can take things. You can either use it to search for things and tell you, did you find something that matched this regular expression in the string, or look through the string and pull out pieces that match the regular expression. Okay, so here's our first example, and this is an example that tells us, very much like some of our earlier examples, we're looking through like the needle in the haystack problem, where we're going to open a file, and we're going to loop through that file, and we're going to take away the suffix, the blanks at the end, and we're going to check to see if the line we're using the find to say, does this line have the string from colon in it? And so we're saying what position is it, and the position is line.find, and if that position is greater than or equal to 0, away we go. And so then we print the line. So this is like what this code really does is it looks through a whole file and shows you the lines that start with from. That's what this problem is solving. Okay? By now that should be relatively simple. Well, if we do the exact same thing in regular expressions, first we have to import the regular expression library. Let me change my color here. Import the regular expression library. Some of this is the same. We open the file, we loop through the file, we strip the characters at the end. And so now we're going to use, instead of the find operation, we're going to use re.search. So re.search is going to return us a true or a false, and it has a regular expression. Now later we will see that this can be very complex. None of those characters, F, R, O, M, colon, are special regular expression characters, and this is the thing we're looking at. We're saying find, look through this line here and find that string from. If it's there, you get a true. If it's not, you get a false. So this also will loop through the file, printing out the lines that have the string from in them somewhere. So we can make a tiny difference if we want, and actually in this case we probably do want to look for lines that only start with from at the beginning. And so in Python, with just strings, what we would do is we'd say, oh no, we're not going to use the find, we're going to use the starts with method. So line is that string of characters that come in from the line. And if it starts with a from colon, That's the line we want to send, right? That's the line we want to print. Well, in regular expressions, we're still going to use search, but we're now going to use one of these special characters. The caret is that special character that matches the beginning of a line. So if you look at caret from, what we're really saying in this little programming language is not look for the string caret, but instead say look for from at the beginning of the line. So we're asking a question here, dear regular expression, look through this line and find out if you find the string from at the beginning, and then return us a true or a false, depending on whether that happens. And so we sort of see, we change things, and you'll see in a bit that we will slowly but surely add more and more functionality and intelligence to these little regular expressions, rather than extending and adding more and more lines of code to our Python code. So that's the caret as a first thing that we learn. The next thing that we're going to learn is the dot. The dot is the wildcard character. And that's a little different than some things like star dot star or whatever. Usually the star is a wildcard, but star is not a wildcard. The wildcard is the dot character. Star means any number of times. Any number of times. Asterisk, any number of times. Okay, so star means any number of times. So if we carefully look at what this is saying, what this says is, I am interested in my little programming language, I'm interested in matching the start of the line, followed by the letter X. The letter X is just the letter X, it's not special. And then followed by any character, and then these two things go together. Star dot means any character as many times as you like, followed by another colon. So the X and the colon are not special, they're not code, they're not on my little sheet of things that have meaning, but the caret means beginning of line, dot means any character, and star means as needed. Now, that means that some lines number of these lines will match. This has an X, all these lines have X at the beginning, and then they have some number of wildcard characters, and then they have a colon. So that's all we're saying. Find a line with X at the beginning, some number of characters, and then a colon. It doesn't, this is okay. We're not, if we wanted to say that was the last character, I could put a $sign here, and then that would say the line would have to end there, but then none of those things would match. So X and colon are real characters, and caret, dot, and asterisk are like part of the little programming language that we've got going on here. Now, you might want to do things like not have extra spaces, right? And so if we look at this in this previous one, we look at this X plane is behind schedule. Well, it starts with an X and then has a colon and has all these things. And we didn't really want to match that, but it looked to the regular expression like a thing that had an X plus a bunch of characters and then a colon. And if we want to clean that up, we can clean that up by just tuning our regular expression a little bit. We can be a little more explicit. We can say, you know what, we don't just want an X at the beginning of the line, we want an X dash. So that says I'm going to match X dash. And then instead of any character, which a dot would be any character, but backslash S on the sheet, backslash S says a backslash capital S says non-blank character, any non-blank character, non-white space. And then instead of star here, star is 0 or more times, and plus is 1 or more times, followed by a colon. So this little programming language says the line must start with X dash, at least one non-blank character, but they all have to be non-blank up to the colon. And so this starts with X dash, at least one non-blank character, and a colon. Starts with X dash, any number of non-blank characters, followed by a colon. This one starts with X dash, it's fine, but now it says, oops, I am only looking for things, I got to find the colon before I hit a blank before I found the colon, so this line doesn't match. So take a look at it. You see how we're just slowly but surely adding a single character or a couple of characters, and it turns into code, right? These are, we are communicating with this regular expression code and telling it what we want to do. Now, maybe we are not making any sense, and it's quite often when you're making a regular expression that you won't make any sense. So the search tells you the true or false, whether or not you're going to find what you're looking for or not find what you're looking for. And then the find all will go through a string and look for something to happen multiple times. And so this slide also introduces a new syntax, and that is the bracket syntax. And so the square brackets enclose a set. And so the square bracket is a single character. And what's in between the square brackets is the legal things that we're willing to take. So what I'm saying here is this is one digit. So bracket 0-9 close bracket, that says one digit. And then the plus as a suffix says one or more digits. If you had star, it would be 0 or more digits. But in this case, I'm saying at least one digit and then any number of digits. Okay? So that is a digit, somewhere in the range 0 through 9. You can have things like A-Z in there. The sheet talks about this. So that's a expression. So at least one or more digits. And find all is another method within the regular expression library that says go through this string I'm looking at and find all the situations that all the substrings of that string that would match my regular expression. So just to express roughly what we're doing here, here's the string we're looking for, and we're saying, dear regular expression, find me any string that's one or more digits and give them back to me. That's one or more digits, that's one or more digits, and that's one or more digits. It's like give them back to me. And so it pulls those out and it puts them in a list. And so this is the list we get. And there's a lot of code in there, right? And this is a relatively simple regular expression. I'm looking for numbers. 1 digit, 2 digits, 5 digits, 100 digits, doesn't matter. Some numbers, pull them out, and then give me a Python list. So this is a Python list. So whenever you're extracting using find all, what you get back is a Python list. And in that Python list, we have 3 strings. 2, 19, and 42, and those are exactly those things. So that's a pretty powerful little bit of code to say, go through and find me all the numbers and give me the numbers. Don't just tell me that they exist, true or false, and I want the numbers to be pulled out. If you think about how you'd have to do that, I mean, you have to use split and you have to do some checking, check if they're integers. I mean, you could do the same thing with splits and a for loop and a couple of other things, but that's, 5, 6, 8 lines of code that regular expression does for you. Okay? So find all is our way of extracting data. Search is our way of asking whether there is a possible match. Find all both says, is there a match? How many matches are there? And what are the things that I extracted? And so if you look at this, the same string right here, the same string, and I used my one or more digits extraction, I get 3 things in a Python list. And if I say, I'm looking for any number of uppercase vowels, A, E, I, O, or U in a bracket, remember that's one character, and this is one or more. One or more uppercase vowels. So find me in this string right here, find me all of the sequences of one or more uppercase vowels and give them back to me. So it looks through, goes like, nope. So it gives us back an empty list. So the fact that it didn't find it at all is why we get back an empty list. We call find all, and you don't find anything. So it doesn't return false. It always returns a list, and if there was nothing found, it returns a list with nothing in it. Okay? Now, these matching operations are what are called greedy. And greedy means that as they're extracting, they're pushing outwards. And it wants to return in the return codes that you're getting. It wants to return the largest possible string. So let's just take a look at this. So here's a thing that says beginning of line, starting with an F, any character, 1 or more times, right? Actually, I already had those arrows right there. First character has got to be an F in the first character of the line, followed by any number of characters, blank, non-blank, because dot matches all characters, and then colon. So you think, oh, that's going to go from colon and give me that. But it doesn't, because it's greedy. And so it could either give you this matches and that matches. We could tell it, I'm not interested in a colon. You could say, start with an F, as many non-colon characters stopping with a colon. You could say that. So it could either legitimately say that is starting with F and ending in colon, or it legitimately could say starting with F and ending in colon. Greedy says prefer the larger. Right? So Greedy says make the string as large as possible, and so that's why we get this string. Both strings legitimately match, but if you have a choice, take the largest of the two strings. So non-greedy matching. Sometimes if you really want to only stop at that first colon, then you add this little question mark, and the question mark says don't do the greedy matching. Okay? And so that says satisfy the regular expression with the shortest string rather than the longest string. And so other than this greedy matching, it starts with an F and ends in a colon, starts with an F, ends in a colon. Well, non-greedy matching says prefer this one. You know, that's the one we want, because don't go as far as you can. And sometimes that's really important. And so in this one we get from back. Okay? So that gives us kind of a start. We'll continue in a moment on regular expressions. So now we're going to start playing with taking our Python applications and changing the source of their data. Up till now we've been reading files, the mailbox file, the Romeo file, but often a lot of what you need to do is look at data that's coming in from the internet. And so we're going to look at how we write Python programs to talk to the internet. And what we're going to do is we're going to play with the request-response cycle that your browser does. So your browser, when you're clicking on pages or watching this, is talking across the internet to servers. And we're going to take a look at the protocols and all the kinds of things that are happening. And your browser displays web pages and runs JavaScript and does this, that, and the other thing. And then it sends commands across the internet to these servers. And the servers run server languages like PHP or MySQL and send stuff back. And so we're going to spend our time in this section sort of learning about this area, what's going on back and forth as your web browser is talking to the internet. And then what we're going to do is we're going to write a Python program over here. And our Python program is going to talk the same protocol as your web browser, and we're going to do this to read information so that we can read information across the internet. Now I'm going to talk really quickly through some of what the internet is. That is a whole class. I wrote a whole book called Introduction to Networking that talks all about these kinds of things. And if you need more detail, then go ahead and get your hold of that book. There's also a free copy online of this book. And I also teach another Coursera class, Internet History, Technology, and Security, that goes into much more detail than this lecture. And so if you're interested in that, you can stop and go take that class right now in its entirety and then come back. But now this is the short version. The too long don't read. This is a picture of the network architecture, the TCP/IP, Transport Control Protocol. And it's this layered architecture. And these two ends, this is the your computer and this is the server's computer. And the data sort of works its way through various elements of your computer, walks across the network, and then takes multiple hops, actually many hops as it goes across, and then finally makes it into the destination computer. And then the data that you're getting from that computer sort of walks its way back through all these hops, walk back, and then the application. And so this is your web browser, and this is the web server over here. And again, I teach class upon class about this, and you can go take all those classes. And so there's lots of detail that we're not going to cover. There is a layer that is the first end-to-end layer. We call it the transport layer, where your web browser on this end and the web server on this end, in effect, makes a connection and doesn't worry about all this detail, kind of ignores all this detail. Says, I'm going to talk to this endpoint, and then gets its data back, and then the data comes back. And so the first thing we're going to talk about is this peer-to-peer transport layer, the way that effectively computer applications make telephone calls from one application to the other. And so there's a lot of cool stuff that happens, and like I said, I wrote a whole book on this stuff, and you're welcome to go look at all that. But first we're going to really focus on how this works inside of Python. So a socket can be best thought of as a connection that we don't worry too much about. when you make a phone call and you start talking to somebody on the phone, you don't worry about the magic that gets this phone talking to the cell tower or anything like that. You just say, I need to connect to a person, and then once the connection's made, you do your talking. And applications inside of computers do the same thing. And we call this abstraction, this concept, a socket. A socket is two computer applications or computer processes that are talking across a network. And they sort of have this one endpoint, one puts stuff in and pulls stuff back out. And then there's all this magic that happens in the middle. And it's really complex. And then the other's getting stuff out and putting stuff back in. And so the socket is sort of like this abstraction that gives us like a phone call between two applications. In the beginning, this will be like a web server. And this is the code that you're going to write. This is our code. But socket is the way that it talks. Now we're doing something similar when we talk about files. So your code runs here, and if you remember, we had a file handle, and there's a disk drive out here that has data on it, and we'd use an open call, and we'd read stuff back and forth. So that was our way of saying a file handle is a way to look at a file and get stuff from it. A socket is a way to look at a connection to another process on the end of it and then get data back. So both of these are like portholes that allow us to look out of our application to somewhere else in the world and exchange data with that. And so when you're making a connection, different applications, like there's applications like email and the web. And the web is the application we're going to play with, but these applications can all run on the same server. And so these applications have what's called a port number. And each port is a way to say, you know what, I want to talk to the web server on this host, or I want to talk to the email server on this host, or I want to talk to the network news server on this host, et cetera, et cetera. And so these are like extensions within phone numbers. And so if you have one big server, and it has the ability to do email, there's an email server application. This side here is the server now, and this is our client, like a browser. Well, this is not a browser, this is a browser, that's a browser. So the client is the thing initiating the connection, the server is the thing reacting to it. And the way they find each other is through these port numbers. So there would be a mail application, an application to do login, a web server, or a personal mailbox. And these things connect themselves to various ports and say, I will listen for connections to come in. And then when your web browser starts up and it wants to make a connection to the web server at University of Michigan, it makes a connection to port 80, and port 80 is then routed to the web server. The web server reads data somewhere and then gives us the stuff back. Okay? And so there is this thing called the IP address, which is like the phone number of the destination computer, and it's equivalent to the domain name address. Remember, there's a whole class that explains this if you and it turns out that this isn't all that essential once we start programming. I just kind of want to give you a sense of what's going on. And so there is a domain name address that turns into an IP address that's the real address of the computer. And then within that, there's like this extension that says, I'm going to talk to the web server. And you could, using different numbers, port 80 turns out to be the one we'll use the most, and it's the way that you talk to the web server. So you talk to a host on the internet and then talk within that host to a particular piece of software. Okay. So some of the common TCP ports, HTTP, which is the web server, the secure web server is port 443, mail's on 25, secure login is on 22. And so every time someone builds a new application protocol, they come up with a new port for it. And then all the clients that want to talk that protocol know what port to talk to. Sometimes you'll use a web browser and you will see a colon after the end of the host name, and that's what's happening when a web server is running on a port other than port 80. So this happens to be a development situation where I'm actually running on localhost, which is, if I was doing software web development on my computer, I would talk to localhost, which is talking to myself, and then on port 8085. Just means that it's a port other than port 80. So these are the normal ports, like 80 is the normal web port, but it doesn't have to be port 80. Okay, with all that, that's a lot of like blah, 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 blah. Now we're going to talk about how it happens in Python. And the beauty of this is there's a really nice library in Python called socket library, that we import a socket. So we say import socket. That makes available to us a whole bunch of library code that allows us to make sockets. And then this is kind of like fopen. It's like open, right? When we're doing file handles, right? If you think about our application as having these portholes that allow us to talk to disk drives or allow us to talk to the network. This is our way of opening a porthole out through the network. And so we say socket.socket. It's a little bit of a weird syntax. This is the library, and this is the method within the library. So that says make a socket, which basically says open me a porthole outside of my computer. And these next two parameters, you'll probably never change them, but what they really say is this says I'm going to make an internet socket, and it's a stream socket. A stream socket means that I'm just going to send data, and I'm going to get back the data and just keep track of the data. Give it back to me in order. There are ways to use it at a lower level where you're not giving it back in order, but these two things, you just are going to put those things in. Now this actually has not connected the socket. So we have our application. The socket effectively opens a porthole to the outside world, and there is nothing connected to the other side. And we get back this variable mysock, kind of like file open. It's almost like you say, I'm going to open a file, but I don't want to tell you what the name of the file is until later. But here is where we do. When we take this thing we get back from socket and it says, please connect, please establish a connection between me and go across the internet and find the host, www.py4inf.com. That's a host. And then go to port 80 on that. So the second thing is the port. So we're saying, so we start the socket, and then we effectively say, dear socket, I want the other end of you to be this server with that address over there. And so at that point, if there is a server connected, a web server connected, then we can actually send data back and forth. So that is the number of lines to establish a connection between our running Python program and a server on an application running on the far end. You can't just connect to anywhere or anything. There has to be running software ready for you, waiting for your connection to show up. But that's the only 3 lines of Python. And so it's a good example of how something extremely complex that took 40 years to develop the internet, and now in Python we do a single import statement of import socket, and then magically we can code over top of it without any knowing of any of the details whatsoever. And of course that's what this XKCD of import anti-gravity is talking about. So the next thing I want to do is talk about moving from making a socket connection to actually solving a problem. So sockets are like making a phone call, and applications are what you say and expect to hear on those phone calls. So now what we're going to do is we're going to take this concept that takes all this low-level routers and Ethernet and fiber optic and simplifies all that down to this one thing called a socket. We make a socket, and then we connect the socket to a far-end application. But then the problem is, what do we do to talk to that application? And so we just got done talking about how the transport layer talks back and forth, and we can open this connection between our application. Remember that this side is our computer and this side is the server computer, and we're going to pretend that all this complexity doesn't exist, and we've made a socket connection. And that is what we just got done talking about. But then the question becomes, what we're really interested in is not actually just making sockets, but doing something useful like web browsing. Web browsing to a web server. And then the question is, now that we have a connection, what do we say? That's really what this is. Our next problem to solve is, what do we say? So the most common protocol that we run across these days is a protocol called HTTP, which stands for Hypertext Transport Layer Protocol. And it's really the most dominant application layer protocol on the internet. It is how we retrieve HTML documents, but it also does web services like API stuff, and we'll talk to those things as well. And part of its success is its simplicity. It's so simple that I can explain it to you in like 20 minutes, and you can actually hack it yourself within 20 minutes. So we take this socket, this ability to call, and you basically say, I'm going to make a connection, and I'm going to ask for a document, and then wait, and you'll send me the document, and we'll disconnect. So it's a very simple protocol that has a whole ton of subtlety to it, but at its core, it's very simple, and that means we can use it to do lots and lots of things. And it's just the set of rules that tell browsers what they are supposed to talk when they're talking to servers. What are they supposed to say? Who talks first is one of the biggest questions of one of these protocols. So a protocol is just a set of rules of the road, right? Do we drive on the right side of the road or do we drive on the left side of the road? In driving and in protocols, it kind of doesn't matter as long as we agree, just so that we don't bump into each other. And like I said, one of the first things that you got to figure out in a protocol is who's going to wait for the other to talk and who's going to talk first. If you're both waiting for the other person to talk, then nothing good happens and you can't get started. So you have to start. So if you look at HTML and we look at sort of what our web browser has in its location bar, who knows, someday or in the future they won't even show us location bars, but this is what's called a URL, or a Uniform Resource Locator. And if you watch the video that I have of Robert Caillou, you will see that he says, and I agree, that one of the critical things that the web did was created the Uniform Resource Locator. And the Uniform Resource Locator, before that, I mean, it's a simple concept, but before that, we had to know what kind of host to talk to, what kind of service to talk to, what kind of application protocol, and what kind of document. And so if you take a look at your typical URL, like this YouTube URL, it's broken into what protocol are we going to use to talk to the server. This is the Hypertext Transport Protocol. What host are we going to talk to? And then what document are we going to get? So we're going to connect to this host and use the HTTP protocol to request this document. Okay? And you can see the same thing. We're going to talk to YouTube, a host named youtube.com, and this is the document that we're asking to get. Okay, and so that's how these URLs work. They have a protocol, a host, and a document. And again, a simple concept, but as long as everyone does it the same thing, things work out quite well. If you look at the specs for the URL, they're actually somewhat complex, but in the basic thing. So if we think about the act of surfing on the web, you've got some page that you're looking at, and then you've got these little hot links on that page, and you click something, and then you get a new page. This is what we call the request response cycle. So let me show you that in a web browser. Okay, so let's find myself my web browser. Okay, here's a happy little web page, right? Here's a URL, drchuck.com/page1.htm. And so it's a rather nondescript web page. The only thing that you can do is go to a different page. So right now, this web browser is not talking to any web server at all. And at some point, I hover over this little link and I say, oh, I would like to get this other page. And so I click the button. And when I click the button, that tells the browser to go retrieve a different page. And if you look down here in the lower tiny left-hand corner, down here, let me go back to it now. If you hover down there in the corner, you can see which page it's going to go to. Okay? So when I click, the browser says, oh, the user, me, needs a different page. And so it then makes a socket connection and retrieves that page and shows the page. Now this is all happening at the moment I press click. Click. Okay, that's a different page. And now I'm looking, reading my page. I'm going to click on something else and it's going to go somewhere else. Okay? So that's called the request response cycle, because at the moment you click, it makes a request. The other page that it gets is the response, the request response cycle. Okay, so request response cycle, you are asking for a new document. So this is how it works. All right, you're going to hover over top of that first link. You click on the link. That click is an event that goes to a piece of software running on your computer called the browser. Could be Chrome or Mozilla or whatever, Firefox. And then the browser makes a network connection to the web server. The web server is a different computer, and it makes a connection on port 80 because it's like we're going to talk the web. And then it sends the application request for a document, and that's the GET request. It sends this GET request. The web server goes la 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 and does all these other things. And then it sends us back a page that might have come off of a disk drive, it might have come off of a database, who knows how it made that. And it sends us back some HTML with less thans and greater thans. And the browser receives that back as the information and then shows it and formats it. Okay? And so this is the request response cycle. This side is the request, and this side is the response. And then every time you click, it kind of goes and gets, retrieves, displays. Get, retrieve, display. Get, retrieve, display. Request response cycle. And that's what your browser does over and over and over again. Now, if you wanted to write a browser, you could go find the standard that would talk about how to send this data. These standards are often developed by an organization called the Internet Engineering Task Force, or IETF, and they're often called requests for comments. It's kind of ironic to name a standard that we've been using for years and years in RFC, or request for comments, but that's an irony on purpose that basically is saying none of these internet protocols are so set in stone that we could never imagine changing them. So these things, even though some of them are many years old, this particular one I'm looking at is the IP layer, right? And it's September 1981. Now, a lot of things have changed, and that's why they call them requests for comments. And so you can see these. They're all open standards. There's no charge to look at them. And you can go read the standard for IP, and you can go read the standard for TCP and HTTP and all these things if you really want to read it. So if we were to look at one of the protocols, this might even be obsolete by now, of this Hypertext Transport Protocol, the HTTP, and then we could read through it. And it's hundreds of pages long, and if we read down and farther and farther and farther, you read far enough, it would say, if you are a client, like a browser, that wants to send to a web server, what is the syntax of that, right? And so it basically tells you what the thing is supposed to look like. You read a little farther, and what it will tell you is that you're supposed to send a first three characters are capital G, capital E, capital T, followed by a space, followed by the page you're interested in, and there's a little bit about which protocol version you want to use. And so if you look at what goes on underneath, this is how it works. And you can actually, if you have the right software running on your system, you can hack HTTP as well. And so that's such an easy protocol that we can fake it. And Telnet is a command that was originally used to log into other computers, but because it's unencrypted, it generally is not used to do login anymore because we want to use a secure login. But some computers, I'm using a Macintosh, Linux has it. You may be able to download a Telnet for Windows. I don't know, you probably Google Telnet for Windows. But basically this is a command line, and I'm going to use this to hand talk the protocol. So let me show you how this works. Okay, here I'm in a command line. And so I am going to use the Telnet command, which is not a web protocol. Telnet simply makes a connection and then sends whatever characters I type at the keyboard across that socket. So I can say telnet www.dr-chuck.com, and I'm telling it that I want to connect to port 80. So I told you that port 80 was the port that we use to talk to web browsers. So now it's opening a socket and connecting to port 80, which is, I showed you a little while back how to do this exact same thing in Python. And now what's happening is it's waiting for me to talk. I might say, hello there. And I'm not talking the right protocol. I said this, I typed this hello there, and it blew up. And it's saying bad request, your browser sent a request the server could not understand, additionally a 404 was not found, blah, 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 blah. Okay, so that is something, that you will not see this if you use a browser because your browser won't be dumb enough to say hello there. Because if we read the specification, we know that the first thing you're supposed to type is get. So let me try this again. I'm going to again make a telnet to that web server. The web server got a request. It was just a badly formed request. And this time I'm going to do it right. I'm going to type capital G, capital E, capital T, get. And then the page I'm looking for, http://www.drchuck.com/page1.htm. I have to tell which protocol I want to use, HTTP 1.0. And you also see the IP address. Oh, I was too slow. I was too slow. It was mad. Okay, I'll do it faster next time. I'll just point out that this is the IP address. The domain name is www.drchuck.com, but the actual low-level phone number of drchuck.com, at least for today, it could change, is 192.150.251.66.43, and then within that server we're talking to port 80, and that's how we talk to the web server. Okay, I'm going to put this little string in my cut and paste buffer so that I can type it faster so it doesn't blow up on me. Okay, that's bad. I didn't type it. So now I'm going to make my connection again, and I won't be so talkative this time. Now I type really fast, get, and then I hit enter, and then I hit enter again. And now I have talked properly to this web server, and it's given me good stuff. I typed this blank line, so you have to type get, and then you have to type enter twice, basically. And that's part of the protocol. You have to type get and enter twice. And then it gives me a set of headers, which are metadata about this document. And it says when we're doing this, and what server I'm talking to, and how much data I'm going to get back. I get 131 characters back. And then it gives me a blank line, again, part of the HTTP protocol, and then it gives me the actual content of the document I asked for. The first page, that's the HTML for that page, and then it closes the connection. I mentioned it opens a connection, sends a GET request, retrieves the data, and the connection gets closed. This is why the HTTP protocol is so delightfully simple. Okay? So that we just hacked into a web server. And you can try to do it in any web server. You'll notice, as this one did, if you type too slow, it's like, you must not really be a browser, you're running too slow. So they do attempt to defend themselves sometimes from you doing things and just typing them randomly. And if you're talking the secure protocols, I can't hack the secure protocols nearly as easily as the insecure protocols. Okay, so back to our talk. So that's it. That's the request response cycle done by hand with no web browser whatsoever. Now, interestingly, part of my obsession with the command line is that in the real world, most hacking is done by people who are very skilled with command line. And you can see an interesting scene that one of my former students helped write in the Matrix Reloaded, where they're actually doing hacking and they're doing it right in the command line. And this is sort of this use of a very accurate hacking scene is now, lots of movies now do accurate hacking instead. Now, this request response cycle, when you grab a whole page, it actually does it many, many times. And so the original HTML comes back, and then CSS comes back, and there is a way in most browsers to turn on developer mode. So let me just show you how that works in a second. So here is, let's go to www.pythonlearn.com. So there's a page. It's got a lot of stuff on it. It's got some images, got these, that, and the other thing. And I'm going to show you what happens when you retrieve this page, but instead watch developer mode, view developer console, and I am going to turn on the network. So let me make this a little bigger so you see it better. So this is a debugger that most of you could turn on, and I'm going to actually look at the network, and I'll clear this all out. So I'm going to refresh this page, and you're going to see that it's making many request response cycles, right? So it actually pulled in the very first page, which is the HTML for the page, then it pulled in CSS, and then it just kept doing more and more things to the point where it took a total of 20 requests. So it's more complex than the single request response cycle, but each of these things are another request response cycle. And you'll notice that sometimes your browser will spin or something while you're waiting for a page to load, and that's because it's got to go request response, request response. Oh, and I got to get this image file and the CSS file, et cetera, et cetera, et cetera. And so that's but they're all based on a request response cycle, which is that GET request. So that is the application protocol for HTTP. Open a socket, send a GET, send a new line, get back the document, display the document, and do that over and over again. So now that we sort of, all these, whenever I tell you about application protocols, it's always more complex than actually using it, okay? So up next, we're going to do something a little easier than understanding application protocols, and instead, let's just use an application protocol. Okay, so all that was pretty complex, learning the HTTP application protocol. It's going to be simpler when we actually do it in Python. That's what's fun about writing code, is like once you get it working, and you can borrow my code. So if you recall, we start with this socket, right? Our application is running on the one side. You know, our application runs on the one side. Oops, get that right. Our application is running here on our computer. It creates a socket, and then remember the connect, these first 3 lines we saw before. The connect extends the socket to talk to the web server that is files on disk drives, etc., etc. And so this connect is the thing that extends the socket. I like to think of it as like you have a socket and then you sort of push it across the internet and then lock in on the other side. If there was no web server, this would blow up right here. This actually works all the time because it's like just open a connection that I'm going to tell you what to connect to later, and then the connect says make the connection. But when we're all done at this point in our code, we've imported the socket library, we create the endpoint, and then we push the endpoint through the web. We now have a socket that sort of starts in our computer, our application, and ends in the web server application. So that's the web server. And port 80 just happens to be the phone number we called them on. And one thing that's different about a socket compared to a file is you can both send and receive to the socket. And so like I said, the first thing that you got to figure out in a protocol is who starts. We are the browser, we are the client, we initiated the connection, we're not going to look at the code in here, but there's a similar set of first few lines to say I'm ready to get a connection. So that's different code, but we're initiating the connection. So if this is the HTTP protocol, then we have the responsibility of sending the GET request. But it looks exactly like what we sent before. We did this with Telnet before. We send a GET request followed by a blank, followed by the document we're interested in, followed by a blank, followed by the web protocol we want to use. We're using the old protocol, HTTP 1.0, and then we hit the enter twice, \n/n. So it's exactly what I typed. The difference is Python's typing it now, right? I'm not typing it, Python's typing it. And so we've sent this request across, we send the GET across, and then this server retrieves it, parses it, says, oh, I know what you want. Let me go open a file, and let me send that file back. And it starts sending the file back. Send, right? And so then what we got to do is we got to write a loop to read. And that's what this little loop right here is doing. While true, we're going to receive up to 512 characters at a time. That says, give me up to 512. If it's only sent a little bit, like 100 characters, you'll get it back. So the length of the data is important. If you get nothing, if you've got the end of file, when this is finally sent all of its data, it sends a special mark, that says, oh, that's the end of file. And that kind of like when that end of file reaches you, then this call to receive will give you back -1. There is no data. It's less than 1. And then we break out of the loop. And then all we do is we just print that so that the data comes out on the screen, print the data, and then we close the socket. Okay? So that is a very simple web browser. So let's run that. So here's a little trick. Don't name your programs socket.py, because then you actually conflict with that socket library, and then you'll get this import will start blowing up, right? So don't do that. So this is the code I just showed you. Import the socket, create the endpoint, connect to the endpoint, send the application GET request down, and then receive the data, and then close the socket. Okay? And the host that we're connecting to in the document is all hard-coded in there. We just say Python socket1.py. This is an application that's going to make a network connection. If you're not connected to the network, this one's not going to work very well. And there we got. It was exactly the same stuff as we got before, right? We got the headers that told us something about metadata about the document, and then a blank line. This one's a little different. Our content type on this one, remember that Romeo.txt is just flat text because it's a .txt file, so this is plain text. So there's no less thans or greater thans or anything. So this is how a text document looks like. So we just wrote a web browser. It's not a very pretty web browser, but we made a connection, sent a request down, and then got the data back and showed it to ourselves on the screen. So that's pretty easy. So that's all it takes, like 12 lines of code, 11, 12 lines of code. Easy money, right? So there we go. And that's what you get back. And again, this first part is the header part, and then there's a blank line. If you go read the spec, that's what the spec says you're supposed to do. You get a blank line, and then you know it's the separation between the header and the data. Okay, so that seems easy. But if we're going to do this a whole bunch of times, We don't even want to write 12 lines of code. So we can make this even easier with another library called URLlib. So socket is this low level, like make phone call and then you choose how to talk. URLlib is like an application layer library that knows about get and all these other things. And it knows about headers and it knows about the blank lines. It knows about all the rules. So URLlib makes it even easier. So to do the same thing, URLlib makes URLs seem like files. Okay? So there's a transport layer. When we're talking socket, we're talking transport layer, and we're talking URLlib, we're talking application layer. It should probably be called HTTP-lib because that's sort of what it's doing. But actually, no, it can talk FTP URLs and other things as well. So I guess it's okay to call it URLlib. Given that I didn't name it and people smarter than me named it, we'll keep it that way. Okay, so here's that same line of code. I mean, we're solving that same problem now in 4 lines of code. And one of them is the import of the URLlib. What we get back, we say URLlib.URL open. This is the method, this is the library, and we give it one parameter. We don't have to worry about port 80. It knows about port 80. We don't have to worry about get. It knows about get. We don't have to worry about anything. Okay? We just say, give me this URL and open it and give me back. This is like a file handler, and you can see that we can then use this in a for loop just like we would use in a file handler. Now this code should start to look kind of familiar. We're going to open a URL and loop through line by line through the URL and then print it out. That's what this does. But from here on, that could be the same thing for opening a local disk file, opening romeo.txt off of your disk. So let me run that one. Another, don't call your thing URLlib. If you name your file the same as a Python library, it will not go well. URL lib1 py. Boom. Now one thing you'll notice is we do not get in this URLlib, we don't get the headers. We only get the text. And that's because it assumes that URLlib, we want it to read the content of the file, because this is just metadata up here. It's useful. Now it turns out there's a way in URLlib to say, hey, give me the headers instead of the body. But URLlib is the common thing you pretty much want to do is not see the headers, but instead just see the body. So URLlib has simplified that and just given us that. But URLlib is really beautiful because it turns something super complex. That, of course, it was super complex with 12 lines of code, super complex, but it then reduces it to 2 lines of code. So it's pretty cool. And so that's what it does. We already saw that. But the whole idea of URLlib is it just turns URLs into files. And so we can put these first 2 lines at the top, import and open, and then we can write pretty much any program we want to do, right? So this is a program that we've done before where we're going to loop through all the lines in the file. Then we're going to split the lines into words, and then we're going to loop through all the words in the file, and then we're going to do a dictionary get pattern, right? And then we're going to print the counts out. The point is, this code is identical to a program that we did earlier that read a file and counted the frequency of words in the file. Now we're using this exact same code, only changing the top part. Open a URL and then read it, versus open a file and then read it. So everything that you've been doing with a file in Python, you can just as easily do with the URL. And you're saying, like, why did he tell us about all that crazy detail? I don't know. I want you to know the detail. When it's easy to use, I want you to understand that it's amazing that it's this easy to use. Okay, so now we have got to the point where we can retrieve and view the contents of a URL. The next thing we're going to do is we're going to tear apart and try to make sense of that HTML in our Python code. So now that we're able to retrieve a document, HTML, text document, whatever, from a web server, now we're going to actually start sort of sense making of the web document. So here's our code, right? We can, this is an example of reading a web page. We import the URL library, we open the URL, we read through it like a file and print out stripping new lines at the end, right? And out comes the less than's and the greater than's, that's the web page. And
Of course, what the browser does is it looks at the H1 and makes the font differently and makes it pretty on the page. And so there's a rendering, what's called rendering, where it takes that HTML that's in the actual return document and makes it look pretty on the page. And that itself is a whole class of how to make pretty web pages, and that's not what we're going to talk about here. But basically, when you return this information, if you return this information inside this text, and this is just string information at this point in your application, you can look for like an anchor tag and the end of an anchor tag and then the href attribute and find in these double quotes, and you can find another page. And so you can parse using regular expressions or find or who knows what. You can parse out these things, and then this is exactly the string that you would put into that, right? To open the URL, and then if we made a loop around this that was a bigger loop that would read this data, extract this string, and do another open, and then read that and extract that string and do another open, and so on and so on and so on. And that is how we cruise through the web. We put a loop around this where we pull the URLs out, and then we read them, and then we pull a URL, and eventually you will find your way to pretty much everything on the web by starting at one page, pulling all the links to that page, and then hitting all those links, on and on and on and on. Your computer will probably run out of memory before you've read the whole web, but that's sort of the beginning of a Google crawler. And so now we're talking about sort of how we're going to take a look at this web with scraping. So web scraping is the term, or web crawling is the term that we use for writing applications that pretend to be web browsers and retrieve these web pages and then look for the links in those web pages and then continue. And it's a science all itself, and it's a way that you can sort of crawl the whole web or make a copy of the web or just a piece of the web. Now, what we're really doing is we're taking that request response cycle that I talked about before, where you click on something in the browser, your browser sends a GET request, the server responds with some HTML, and then formats it up and makes it look pretty on the page. You click again, around and around and around. And instead what we're doing is we're just kind of doing the same thing from Python, doing the same thing, and we're not clicking, we're sort of parsing. You parse all this stuff and then go to a different URL, round and around and around. And the servers can try to do things like put up CAPTCHAs and other things to detect the difference between a human using a web browser and a Python application. But ultimately, the more sophisticated they become to try to do things to fake us out or detect and not allow this, then these applications just get a little smarter. Now what we're going to do in this class is we're only going to look at web pages and websites that don't mind this. And some explicitly don't care, and some care a lot. So you got to be a little careful when you do this, and with great power comes great responsibility, okay? Now why might you want to do this? Well, sometimes you have a system that you don't have an API that has no export capability. So you write a Python program, say, okay, I'll go grab all your pages and pull all my stuff back out. Sometimes you might build a bit of code that checks for something, like looks for new apartments on Craigslist. You could go read Craigslist website. Or you could make a spider to do your own search engine. Sometimes people use it to pull social data. So you see a lot of applications that are like Twitter applications. You give them permission to look at your Twitter data, and off they go looking at your Twitter data. And so it's a way to pull data out when there is no API, application programming interface, to get that. You got to be careful, because if everyone taking this class immediately started scraping one web page or one website, they might get a little grumpy because we could sort of crush them. They would think this would be like a denial of service, because so many people are pulling web pages by writing Python programs. It'll be bad. Now, Facebook has some rules about this. You can't scrape Facebook. Now, the interesting thing about Facebook is that, and this is a thing I grabbed, the interesting thing about Facebook, if you're not logged into Facebook, you really can't see anything. There's no public data on Facebook. At least with Twitter, there's public data that you can see. But at Facebook, You have to be logged in to see anything. So you can actually write a scraper for Facebook, but you have to log in as yourself as the first thing your scraper does, and then they know it's you. And so they're like, oh, all that logic that they put in to determine the difference between when a real web browser is working and a piece of Python's working, they do that so they catch you doing something that you said you weren't going to do. So you accepted when you went into Facebook, you accepted that you're not going to do it. So don't do it on Facebook. As long as it means that, like, if you do it on Facebook, then they will blast your account and they'll try to make sure you never get to use Facebook again. So you can sort of Google things like Google, Facebook scraping block. And there's all these people like, oh, I'm sorry, please forgive me. Well, just don't do it. And you can't scrape Google search engines because they get mad about that too. So, can't write your own search. You could technically write a search engine that took a search term and wrote a Python program to submit the search term to Google and then parse the results that came back from Google. And you could have a really awesome search engine called, Bobble, right? But you'd be violating the terms of service. And, Google copyrights their search results, I believe. And so if they caught you doing that, they'd be super grumpy. So as I'm showing you all this, be careful. Don't be mischievous. Okay, so I'm going to stop and talk about how to parse this with a library called Beautiful Soup in a separate section. So now we're actually going to write our real web crawler, and we're going to actually parse the HTML. And most of the time, I show you the hard way first, and then I show you the easy way second. But in this one, we're not going to bother with that. I'm like, oh, look how much easier it is. No, we're just going to start with the easy way. The problem is if you look at HTML, just, here's some sample HTML. You can break this stuff on, it doesn't have to all be on one line. The way you might write HTML makes really good sense, and so it could be ugly. And you don't even want to know the rules of HTML. It's bad enough to know the rules of HTML when you're writing web pages, let alone trying to read someone else's crazy HTML. And as HTML starts coming from applications, if you're going to learn how to do web development like in PHP, the HTML that comes out of these programs is sometimes really ugly with blanks and new lines and all kinds of crap. And it's all legit, right? And the browsers are really smart about compensating for ugly HTML that's valid but ugly HTML. And slowly but surely you could write a parser for HTML, but then you would find out like, oh, somebody did this page and they used a single quote or they forgot the quotes or whatever. Well, someone's done that already. And they wrote this thing called Beautiful Soup. Beautiful Soup is sort of a play on the children's book called Stone Soup, where you kind of throw a bunch of junky things in and it turns out great. Well, it's sort of like, I think that's what they mean when they call it Beautiful Soup, that HTML is all junky, and if you throw all the crappy HTML into Beautiful Soup, then what comes out of Beautiful Soup is wonderful and delicious parsable HTML. So this is also a good time to talk about Python 2 versus Python 3. This class, of course, for now is in Python 2, and so what I'm going to show you is how to use Beautiful Soup in Python 2. The concepts are very similar. The installation is a little different for Python 3, and Beautiful Soup is ported both to Python 2 and Python 3, so you can use this library. It's a great library. Now, if you're doing Python 2, which is our Python, you can download the file beautifulsoup.py, put it in the same folder as your Python code. There are alternative ways to put this in, but this is the crude way. And if you're having trouble finding beautifulsoup.py, it's on my Python for Informatics website, and you can download it from there as either that or from the original crummy.com. So here is a easy way to do it. I mean, literally, this is the whole program. What we're going to do in this program is we're going to retrieve a web page, and we are going to parse the web page, and we're going to look at all the anchor tags and print out the hrefs. That's it. This is the whole thing. Thanks to Beautiful Soup. We're not doing any irregular expressions, any find operations, nothing, because Beautiful Soup does it all. So if we look at this, we have imports at the top. We import the URL libs. That's how we're going to actually read the HTML data and retrieve it into our program. Then we're going to import the library, all the routines that are in the beautifulsoup.py file. That's kind of what that says. We're going to use raw input. That's familiar to us. How we prompt for the name of the URL. Then we're going to call urllib urlopen with the URL as parameter. Now, the one thing we haven't done before is we're just going to call the read method on that. And what that means says read it all. New lines and all. We've done this before. And so it gives us all the lines in a single call with the new lines intact. But if you think about it, well, in this case, we're not going to do any splitting, but it's okay to read it all. The pages shouldn't be all that long. And so this not only opens the URL, but reads it. So we collapse that down to a single line. Read it all. So what we get, this is a string. I call it HTML, but it could be anything. HTML is a string, which is the entire web page with less than's and greater than's and new lines. That's what that line does. Again, with Python, collapses right down to one line. Really nice. So Beautiful Soup, we're going to call Beautiful Soup, say, munge this, read this, figure this out. Here's our string that we read, and then make sense of it and give us back this soup object. So soup is neither a string nor a Boolean or a dictionary. It's lots of stuff. It is the parsed HTML data, and then you can ask soup questions, okay? So this is a soup object that's there for you to make use of. And so we can retrieve a list of tags by saying soup and pass the a tag. And what that really is looking for is things that look like a ... slash a. So that's what an anchor tag looks like. And what we're saying is, find me all the tags. So don't find me p tags. Don't find me bold tags. Don't find me any of that stuff. Just give me the tags. And what we're really getting is this data right here. That's the tag itself. Okay? And so that is a list of tags. And so if this had one anchor tag, this would be a list of one tag. If there was 0 anchor tags, we'd get no tags. This is a really smart lookup that reads the entire HTML document, and however many tags are there, it gives them to us. Okay? Ignores all these other tags and just finds those tags. So that is a list of tags. It's kind of like a dictionary, because if you look at what the tag says, it's like a href equals quote, double quote, and so these things here are called attributes. And so when we grab the tag, we get all of this, and then it parses these things as well, hrefs, as key value pairs in like a dictionary. And so what we can do is we can look at all the tags in the document, for tag in tags. That's looping through all the anchor tags in the document. You know, how many A's there are in this document, loop through them all, ignoring everything else in the document, and then give us the href value for each of those tags. And we're going to use a get, and we're going to have a default value of none so that we can, if there is no href, because it's possible to do an anchor tag with no href. And that literally is going to retrieve the document and show us all the anchor tags. Seriously, that's it. That's it. So let's just run that. Come back. What's the name of that file again? URL links.py. Let's take a look at it. That's it. Read a web page, any web page we type, read it, use Beautiful Soup to parse it, look for all the anchor tags, loop through the anchor tags, and print out the hrefs. Okay? Python URL links py. So let's just start with that other file, http://www.drchuck.com/page HTML. We know what this looks like. And you can put print statements to print the HTML out, but I don't have that. It's going to retrieve it with a dot read, pull all the text, pass it into Beautiful Soup, and then loop through and print out all the hrefs of all the anchor tags. End of story. Right? Did it. That's just 7 lines of code, and you just did all that work because we're depending on the urllib library and the Beautiful Soup library. But we don't have to just have a page with one link. We could say www.drchuck.com. See what happens there. See how many links I've got on that page. So there we go. That is all the links on that page. Right? It read all that stuff. So right here, drchuck.com, these from here down are all the links in that page. Now you can see how easy it is to eventually write a web scraper, which we will do later in the book, basically. Okay? And so that's it. That, and I mean, I guess that's it. That's the simple essence of using really powerful Python libraries, both built in with URL-lib and with Beautiful Soup, to both retrieve and parse these things in just a couple of lines of code. And I'm going to guess that the first Google crawler was probably looked just about like this. These days it's super sophisticated code, but in the early days you could write a crawler that used this essential bit of code that would retrieve these pages, parse them using Beautiful Soup or a similar library, and then make a list of the next things that have to be parsed, and then just go and go and go and go. And eventually you sort of end up with a full list of everything, and you could have a search engine. But it's a little late now because someone already did a search engine. So if we take a look at this whole chapter, the internet and the internet protocols are very beautiful and very complex and knit us all together and connect applications to applications. In a programming sense, the lowest that we tend to talk to is these sockets, which are like make a phone call to this address, which is like make a phone call to a phone number with an extension. The ports are the extensions that allows us to talk to the web server, the mail server, the login server. So on one host you can have multiple servers. And then once you talk to that server, you've got to know the application protocol. And in this case, we played with the HTTP application protocol. We send these GET requests, and we've talked to the socket library, we've talked to the URL-lib library, and then we talked using the Beautiful Soup library. And when it's all said and done, our programs end up relatively small. And Python has really good support for talking across the network to these various applications, retrieving, parsing, and making sense of it. Now, up next, we'll be talking to things that are even more intelligent. Now, HTML is not designed to transfer data, but using Beautiful Soup, we can kind of pretend that it is data and tear our stuff out that we want to look at. But up next, we're going to talk to things that actually want to talk with us and give us data in an even better format than HTML that makes it easier and more natural for us to make sense of that data. So that's what we're going to do next. We're going to keep using the network to retrieve data, but we're going to use very different techniques in the next lecture. Hello and welcome to Chapter 13. What we did in the last chapter course is we learned how to make request-response calls across the internet, but instead of from a browser, from Python. And now we're going to become much more powerful with that. We're going to really push this. And we're going to talk, instead of reading HTML, which is not really intended for consumption by an application like yours that's interested in data. Sometimes HTML is all we've got. Now we're going to talk to web services. And these are URLs that are designed explicitly to hand you data back for your application. And so the data, it was a natural thing once we had browsers that were talking HTML to come up with a way to structure the data. To say, look, we're going to make the data look clean. We're expecting this data to be consumed by your application. And so we're going to come up with some formats to represent that data going back and forth between applications across networks. And there are two technologies that we'll talk about. One will be called the Extensible Markup Language, which is XML, and the other one is called JSON, which is the JavaScript Object Notation. So the problem is when we're sending data between applications, we have things like lists and dictionaries in Python. And if you were to go into the Java programming language, you wouldn't find lists and dictionaries. You would find what we call a hash map. And so you really can't send a Python dictionary across. You have to send something that both Python and Java agree on, and then they convert. And so we call this the wire protocol. We call it the wire protocol because if you were to sort of split this and you were to look at the stuff going back and forth and you were to say what is going on the wire, we think of the internet as a series of wires. So if you were to grab one wire and you were to look at it, tap into it, and you say what is this Python program sending to that Java program on the wire? So we call it wire protocol, even though hey, it may be fiber optic these days, so we don't even know if they're wires, but we call it the wire protocol. And so we have to agree on a wire format, a format that is neither the Python format nor the Java format. It's just a format that we'll use. And once we've agreed on the format, data inside of a Python application has to be transformed in some way to the wire format. The wire format's sent across, and then for Java to understand and make use of that, they've got to pull that wire format off and then turn it into an internal structure. So dictionaries and hash maps are internal structures for Python and Java. This introduces a term that's very important: serialize and deserialize. Serialize is the act of taking internal structure and creating the wire format, and deserializing is the act of taking that wire format and creating an internal structure, and in different languages. And it allows us to create sets of applications that work in different languages, right? This particular thing that I'm showing you in the middle is XML. So XML is one of the two formats we're going to spend time talking about in this section, and it is the different formats are better and worse for different things. XML kind of came first. XML came shortly after HTML, and so it has kind of the less thans and greater thans that HTML has, but it's very structured data. The other thing that we'll talk about is a wire format called JSON, or JavaScript Object Notation. And this is a little different. Instead of using less thans and greater thans, it uses curly braces, double quotes, colons, and this actually starts looking like the format of a Python key value dictionary, right? And so even though it kind of looks like it, this is still a wire format, and this is a textual representation of a Python dictionary, and it can be read and turned into a Java hash map. And so JSON and XML are the two formats, the two common wire formats that are used for applications to exchange data. So coming up next, we're going to talk about XML itself.
The REST architectural style started as a model of how the web should work, how web applications should work, in the sense that we had, in the early 90s, back in 1993, 94, we had a pretty good deployed system for World Wide Web. We had clients and servers, user agents, browsers, whatever you want to call them, and simple servers primarily serving up files and a few database systems. And we had this desire to, once there were more than a few implementations of the web protocols, we wanted to standardize those protocols as part of the W3C and as part of the IETF, and in general just to resolve some of the disagreements amongst the developers. At the time, most of the web was built informally using a mailing list primarily as our coordination mechanism. We talked all around the world about a new feature, and frequently we would come up with an idea in one time zone and someone would implement it in another time zone, and by the next morning you'd know what worked or what didn't work with that feature. So it was very free form, very fast. As the companies got involved, they of course wanted to find ways to make use of the web corporately, to make it as one of their platforms. And so they wanted to make it more businessy. And one of the ways to make things more businessy is to create common standards for everyone to adhere to rather than adopt things as you go along. As one of the developers of a protocol library for the web called libwww-perl, and that's the last time I used www in a product name because it's too hard to say. I was asked to help work on the standards, both the URL standard at the time, the HTML standard, and later on the HTTP standard. Because I was a graduate student at UC Irvine, I had all the freedom in the world. Hadn't started working on my dissertation yet, and but I'd finished all my classwork. And that gave me both the freedom and the ability to write for the web in addition to the programming that I was still doing. And it just worked out that being in that position was great. I could have a hand at making the web better, because at the time it had grown out in every direction at once. But at the same time, I was faced with the dilemma of I have many competing interests working towards making the web what they think is a better place. And how do I differentiate between the ones that are actually better for the web and the ones that are back to some older version of an architecture or an architecture that doesn't make any sense at all on the internet? And so I came up with something called the HTTP object model. At the time, object models were the thing. So that's why I called it an object model. Even though it had nothing to do with objects, it was a model of how I expected web applications to behave. And the team that was working on the specification, mostly myself and Henrik Friedrich Nielsen at the W3C, we were asked to write the HTTP standard. And this was my model of describing to each other, basically, how a particular change to the standard would affect the resulting web. Because the web itself is really a network of standards. And I used that throughout the years just as basically a thought description. If someone would offer a feature or describe something that they thought was wrong with the web, I would use the model as a sort of analogy or a proof point to show what it is about HTTP that works at that model and what it is that the new feature might hurt or might help. And that allowed me some intellectual leverage in many ways to affect how the HTTP standard worked. It wasn't until many years later, after I'd done the literature search for software architecture, that I figured out the right words to use to describe it. So I saw a paper by Duane Perry and Alex Wolf in the software engineering, one of the software engineering papers. It was buried in one of the ACM SIGSOFT proceedings, which are distributed very far beyond your school library and things like that. But I found this paper, and it was the only software architecture paper that described architecture in terms of both the components and connectors of typical architecture diagrams, but also the data that's processed through the system. And my realization was that all these architecture papers which I had read, which didn't make any sense to me, because they are all talking about the blueprints of an architecture. And this paper was talking about the actual runtime architecture, the actual behavior of the system, and that's what I was building.
It sounds like you were flowing between a very practical and pragmatic world and this kind of theoretical world, and just flowing gently back and forth for some period of time and like picking up on both sides.
Exactly. I mean, one of the great benefits I had at UCI was all the freedom to pursue these different areas. I was actually working in a team doing research on global software engineering environments. So I was trying to use the web as a platform for software engineering, essentially what GitHub is today. That was my research project. And as part of that, I could do all of this other work related to it. One of the nice things about general research funding at the time.
So at some point you had to sort of like take a breath and finish a thesis.
Yeah, I came from an academic background. My father's a professor of geography and urban economics. And so I always wanted to complete the PhD. It was never a question of running off and joining a startup, even though my startup friends were becoming millionaires left and right. There was always that desire to finish the PhD.
Was it easy to write? Did it come naturally at that point? Was it the idea fully in your mind at that point?
Oh yeah, the idea was not only fully in my mind, but almost past at that point. It was long, because I finished the HTTP standard in 1997. And it wasn't until I had done the work that actually a colleague of mine, Larry Macintyre, came and was talking to me about a related subject. And I was telling him about how, I've done all this work. I don't know what to do for my dissertation. And he just looked at me and said, well, you're the only one who can describe HTTP, why it's there, and what it's there for. Why don't you just do that? And so that gave me the impetus to actually, well, I can do this. I can describe what I already did. I can actually describe it. But then the question was, I've been just fooling around in my, in that wasn't my academic work. My academic work was over here, and my practical work was on the web, and I hadn't really mixed the two other than general knowledge. And for me, going back and trying to find the real knowledge framework for architectural styles was my way of fitting it all together.
What's it like to be the creator of a dissertation that someone actually reads?
It's funny because when I was a graduate student, one of the main motivators that the professors would have, they'd very seriously look at us as, don't worry about what you put in dissertation. Nobody's going to read it anyways. I might because I'm on your committee, but don't worry about it because no one outside your committee is ever going to read this thing. Just get it done and go on. It's just not my style to do that kind of writing. So I consider my first book, my only book really. And for me, writing is very difficult in the sense that I spend a lot of time thinking about each sentence, each paragraph. I'm not the kind of person who writes down a quick rough draft and then goes through and edits it again. I tend to edit sentence by paragraph, then add a paragraph, then delete 2 paragraphs, and then go back and that kind of thing. So it's gratifying that people like to read a dissertation. It's certainly an accessible piece of work. It's not full of equations. There's one equation. The equation is there just to have an equation, by the way. It's not actually necessary, but it's nice to have one.
It's rare that academic research has the profound impact, and honestly, the freedom that you had is what everyone should have.
Exactly. The freedom gave me the ability to do technology transfer beyond their wildest imagination, which is great. What's hilarious from my standpoint is I was just having fun. I was trying to do a good for my good deed for the universe kind of thing, but and it was all for free basically. But it was, for me, fun, enjoyable people, wonderful conversations, learned an incredible amount.
So one of the 2 serialization formats or wire formats that we're going to talk about is XML. And XML stands for Extensible Markup Language. And it is the older of the 2 formats that we're going to talk about, and it's kind of the heavier weight of the 2. Often developers, when given a choice, would prefer the thing I'm going to tell you next, which is JSON, or JavaScript Object Notation. But it turns out that XML has some advantages, in particular when you're doing documents, representing things that are more like documents. If you're just representing arrays and stuff, then JSON tends to be better. So just because XML is a little harder, sometimes it's better. And so if you look at the latest Microsoft Word and PowerPoint formats, they're named PPTX. Well, that X stands for XML, because if you were to look in them, you would see that they use XML to represent things like, the bold, italics, and the metadata about your stuff, or whatever. That's inside the doc file or the PPT file. XML is used to represent the shape of the document. And that's a good choice actually, to use XML to do it. And so XML is basically a textual representation of a tree structure of nodes. And it uses less thans and greater thans. And so you have a start tag, like name and /name, and so less thans and greater thans, and that's a start tag. And a simple element is something that has just a tag, some text, and another tag. And a complex element is a tag that starts and ends, but then within it, it has other tags. Okay, and so a complex element is simply a tag that is intended to include other tags, and a simple element is a tag that simply includes text. And this is like a tree, as we'll talk about in a bit. Another bit of terminology that's important is the start tag and the end tag. So the end tag has the slash in it. There's name and a slash name. So as you look at these things, you've got to match them up, right? The end. So phone and end phone. And then in addition, on the start tag, you have what are called attributes. Attributes are key value pairs, and it's generally, this is some key, and then there's a value, and we enclose this in quotes. So type equals international, or height equals yes. And what do these mean? Well, it depends, right? It depends on the application and what data we're trying to represent. And then the last thing that we have as a bit of XML syntax is what's called a self-closing tag. And so sometimes all the knowledge that you want, all the data you need to represent, there is no data in between the tags, so you just have the start tag and end it with a /greater than sign, and that is, there is no need to have /email at the end of this thing. Okay, so that's called a self-closing tag. So this again is just some terminology: start tag, end tag, textual content, which is the stuff between two tags, and then attribute, which is sort of it's metadata on it. So you tend to use this to describe it. In this particular case, I'm saying, okay, this is an international phone number, right? And it's a way to put a metadata, but the phone number itself is that phone number. Okay? So that's just some XML terminology. White space tends not to matter except sometimes in the textual area, and it's generally discarded. And things like we indent and all that, it's just for readability. And so these two things are roughly equivalent, and some it's all sort of pulled up, and some it's more indented. And I could draw this in many ugly ways with no indentation and extra new lines and extra white spaces. It doesn't matter. We tend not to want to look at that, and often we'll use what's called a pretty printer. And so if you have some XML that's ugly, you can cut and paste it and type, like in Google, go to pretty print XML. You can paste ugly looking XML in that's syntactically correct and hit the button, and it'll pretty print it with all the indentation and stuff. Because if you're looking at XML that doesn't indent, our brains are really bad at parsing it. Computers don't care, but our brains do care. So we tend to pretty print stuff, and all the stuff I put in the slides, I kind of make it reasonably pretty so that I can look at it and know, oh yeah, this is the beginning and that's the end, without it just being all gibberish and pulled up. So white space technically doesn't matter, but as we show each other XML, we tend to make it look really pretty. So here's just a little bit of XML, and so this is a recipe, and there's a title for the recipe. There is some attributes for it. There's each ingredient has some attributes. Then it has the name of the ingredient. Things can be in order. We can have tags within tags. Here's a multi-set step thing. So you get to name these things, right? In HTML, you don't get to. A paragraph is a P tag, and a header 1 is H1 tag. In XML, you make them up, and you use them to describe actually something meaningful. And these attributes, like in HTML, a href equals, right? Somebody made this up. Somebody told you that's how it is, and that's what you got to do to make HTML. But here, name equals prep time, cook time. This all has to do with the application that's going to create and or use this data. And so we create XML formats based on what's most useful to us. And this is how XML is so much more useful to an application than, say, HTML. Even though HTML is crude and effective, and we can get stuff using HTML, but it's so easy to break it. But now we're in XML, and it's pretty and it's elegant. So I've already hit on these terminology. Tags are the beginning and ends. These key value pairs are attributes, and serializing is the act of taking an internal data structure in some programming language and converting it to XML. Deserializing is reading XML and then converting it into some structure inside the programming language so we can actually look at the data inside of that programming language. Now, when we start thinking about XML, maybe we're designing XML, or maybe we're reading somebody else's XML. As I mentioned at the beginning, XML is really a textual representation as a tree, and that's why we see it tend to indent, to capture the nesting. But you can also kind of look at this as a tree, and that is that the A tag here has two child tags, the B tag and the C tag. Those are the tags that are sort of one level down from the root, which is the A tag. And then if you look in the C tag, there's the D tag and the E tag, and so those are the children. So you can think of these as the parent, and these are the child. And then this, of course, becomes the parent, and this is the child, right? And so it really is often very, very helpful to think of this as a tree. And when we write code that's looking through it, sometimes we'll actually drive down the tree and back up the tree and down this tree and back up and down and back up as a way to, in effect, visit all of the nodes in the tree. Okay? So that's one way to, when you see this, mentally you should be able to construct this tree. The attributes in the text itself are kind of like a child of the nodes. So if we take a look at this little bit of XML, and we have the B tag and the NB tag, and then there's the text bit, you can think of the text node itself, the X, which is the text body part of that node, that's a child of the B node, but another child is this attribute W. And so there's might be many attributes. In the text node, there tends to only be one text node. There's a text node and then many attribute nodes depending. And that's kind of how we mentally think of and model the attributes and nodes and the text within nodes. You can also think, and it's totally equivalent, to think of these things as having paths. And it's kind of like folders within folders within folders. And then we concatenate sort of the whole path down using slashes typically to represent each step. So slash means the very top. Slash A means, this stuff. And then slash A slash B means this thing. And so if you were to ask, what is it slash A slash B, you would say, oh, well, I go to A, then I go to B, and what have I found? Well, I have found X, and so that's why slash A slash B. The other path is slash A slash C slash D. Well, what's there? That's Y. Okay? And so you can think of these things as what's the parent, what's the child, or you can sort of think of these as sort of fully realized A, C, E paths, which is the path to Z. Okay? All these are equivalent. They're just all good ways to visualize in your mind as a programmer going, because what you're going to do as a programmer is you're going to dig down and find this Y thing. All these are way too simple, but you kind of have to dig down and go down one, down two, down three, and then you go to the fourth one and then grab this other thing, and that's how you pull out, a header of a document or something. Okay, and somebody will tell us what this XML is supposed to look like. So that's XML itself, but in order to make life better between two applications, we need a contract. And a contract as to what is valid and not valid XML so that two applications don't have to argue. So that's what we'll talk about next. So now we sort of understand the basics of less thans and greater thans and attributes and tags and simple elements and complex elements. In XML, it's important to understand how to describe what is and isn't valid XML. And we call this XML schema. It's a schema for XML, which is sort of the proper shape. Schema kind of means proper shape. And so imagine there are two applications, and you're an airline company and a hotel company, and you write this code and you send data back and forth, and it's all working, and then one of you changes something, and then it breaks. Whose fault was it? Well, was it like a mistake in this one, or did they introduce a new mistake? And so it's nice to be able to say that this XML, this is the contract that we're going to work together, and if I break something or I change something and our connection breaks, at least you can check to see if what we're sending back and forth meets the contract. We call this validation, right? And so the idea is you don't necessarily do this every time it's rare that you do this every time you send the data back and forth. It's more like you do this at the time where there might be an argument as to whether the XML is valid or not. So what you tend to be able to do is if you take this schema contract and you hand it to this validation software and you hand a XML document to the validator, it'd be like, you're valid or you're not valid. So it takes two things, a potentially valid or not valid document and a contract, and then looks at it and says, does this meet the contract? And so we'll talk about what it takes to make these contracts. So here's a real bit of simple XML. Now it turns out the XML schema itself is XML, which means it's turtles all the way down. So here's a little bit of XML with a complex person tag and a simple last name and an age and a date born, right? And we can come up with a schema that describes what is and is not legitimate for this particular thing. You could say, hey, look at that sample XML. That's what we're going to send. So you put the last name, age, and date born. Do it that way. And lots of times that's all they do. They just sort of like make up some sample stuff, and programmer A and programmer B just kind of do their thing, and away we go. But it's not the best way to do things. So what we do is we have this contract, and it is itself XML with this XS colon stuff. And if you remember, I talked about complex types and simple types. Complex types are those that include other tags, and simple types are things that only include text. And so this is basically saying we're going to have a complex type, and it's going to have the name of it's going to be person, and then we're going to have like a sequence of 3 tags, and the first one's going to be name, and it's going to be of type string. The second one's going to be age, and it's going to be of type integer, and the third type is date born, and it's of type date. And so you can see how if, for example, somebody sent back like X here, I mean, it does have a beginning and an end tag, but you could look at this thing and says, no, that second tag is supposed to be AGE, so that is not right, right? And that's what the validator would say. And so it's just a way to programmatically verify that the XML meets the contract that you've agreed to in advance. Now, it's not like you can't use XML without a schema, but it's often a way to formalize a relationship between applications in a nice way. It turns out there's a number of different schema languages. These things all sort of came out in the late 1980s, early 1990s, and there's a lot of sort of chaotic invention going on. And we use this one schema that's often called XSD, the XML schema from the World Wide Web Consortium, which is kind of the more later of these things, because this is sort of like 1995, 94, 95 time frame, and it's actually probably the easiest one to understand. You take a look at some of these things, go ahead and look at them, and they're all doable, but they're kind of scary and harder to use, and certainly harder to read and harder to write programs to validate. So there's a couple of differences. We're just going to stick with the easy one and the one that's most common, and it's often in a file suffix called XSD. So if you like download something and you unzip it and you get this file called the XSD, it is probably the schema for what you're supposed to be sending back and forth. And like I said before, we don't tend to use the schema every time we send or receive data. We mostly use the schema when we're arguing. Say, like, you sent something and blew me up, and I'm going to run it through this schema, and you fail, so you got to go fix your side. It's really whose side we're going to fix. So this is the one we're going to do. It's also called XSD because the file names end in XSD, and I said all that already, so we'll just skip down to here. So as I mentioned, there's a way to represent a complex type, there's a way to represent a sequence, and then the simple type is merely an element. And then the interesting thing sort of becomes, and this way we sort of create sequences and nesting. And you can have complex types within complex types. So we are capturing the nesting and the naming. So that what is nested within what, and what the names of the tags are, and what the orders of the tags are. So we're getting all that. And then the interesting thing becomes, what are the types of the tags? What are the legal types of tags? And that turns out to be some of the more interesting things, and a way to sort of lock this contract down very nicely, because you could basically say this is a string, and this is a string, and this is a string, but if it's an age, you want to say something a little more restrictive than it's a string, right? And so we want to be able to say more restrictive things. Okay, so here's a little bit more of a constraint, right, where we're saying, okay, here's this XML's got a complex element, and then we're going to have a complex type within that, and then a sequence, and the first thing is a full name, and it's a string, and min occurs, these are attributes of this element now, and max occurs. So min occurs says it must occur at least this number of times, and max occurs means it can occur no more than those number of times. So that says that valid XML here has got to have, always must have, in effect it makes this required. Some things are optional. Here we have child name, and it's a string, and min occurs is 0, which means it's optional, which means it doesn't have to be there. If it is there, it's kind of there after the full name. And then max occurs says there are no more than 10. But in this case, we have 4 of them, so it all validates. And so this is good valid XML for this bit of XML schema. And so there's some other kinds of things, right? The string is just a random string. That's a string. The date starts with a 4-digit year, dash, 2-digit month, dash, day. Different parts of the world represent dates differently. Computers kind of prefer to represent them in this year, month, day format. And the reason is because they sort naturally, right? So the year is the biggest thing, and so it sorts like numbers or even strings as long as the string length is the same. So if you are in a date time, it's date followed by the capital T followed by hours, minutes, and seconds. And then the last little thing here is the time zone. And Z stands for UTC or GMT, whatever time it is in London, basically. So that's another thing that computers tend to do. When you're starting to exchange data between computers that might be anywhere in the world, the current time, you really don't want to think about the time zone, especially when you're thinking about things like Eastern Standard Time and Eastern Daylight Time, and I don't know. They even a long time ago made a watch that all the watches were set to the Greenwich Mean Time. So all the people around the world would have the same concept of time. It was a cool hipster idea, but many years ago it was a good idea. They don't do it anymore. But you can have a decimal number like 99.50, which means letters aren't allowed, and then there's an integer, which now you don't even allow periods or fractional parts. So you can sort of lock these things down in your XML schema contract. And so I already mentioned the time format, which is the 4-digit, 2-digit. You don't call this -5 dash. You want to be able to sort this thing. And if you look at this from sort of most significant to least significant, the year, month, day, hours, minutes, seconds. And you put the zeros in. That's what we computer nerds like to do. Put the zeros in. It's a computer thing. And the exact same number of columns all the time. And then the whole thing, if they're all this long, they sort naturally. The sort is natural. So, so 2010-01-05, well, that's going to sort the right way. So the later date is going to sort later. So you make them all the same length, adding zeros where necessary, and you go year, month, day, hour, minute, second. And Z, Zulu time zone, universal time. This whole format that we're talking about is the ISO 8601 format. And if you're ever doing dates inside of a computer, just use this. Don't mess around. Don't mess around with time zones. Unless, of course, you're displaying them to users. So what you do is we tend to store internally times and dates in Greenwich Mean Time or UTC, and then we convert them just at the moment that we show them to people. Not that we're building web applications or anything, but that's how we tend to do it inside of computers. So this is just another schema that's going to demonstrate sort of 1 or 2 new things. So these should be, they start looking really crazy after a while, but go look them up on Wikipedia or whatever and figure out what it is. But here we have an element. Get my pencil back. The outer element is named address. And then within that we have a recipient, a house, a street, a town. These are all strings, not too bad. And then a country, which is optional, min-occurs of 0, which really is saying this thing, we don't really need a country value. And a postcode, which is required, and it's a type string. But then we have this element of country. But we basically are going to put a restriction on it. We say, look, this is indeed a string. The base of this is a string, but it's got to be one of these 5 strings, right? FR, DE, ES, UK, and US. So apparently those are all the countries in the world, at least all that matter on this screen because my screen is only so high. And so this is a way for you to say, hey, this is part of the contract. Yes, it's a string, it's 2 characters long, and there's only 5 possible values for this that are legitimate. And so, again, you can get very specific in these contracts. And so now, if we sort of take a look at this, this is legit because it matches that country code, and the rest of it's legit as well. Okay? So that it's just something, we're not going to spend too much time with it. I just sort of want you to understand roughly about these contracts and maybe look at a few of them, but not really make them. That's pretty sophisticated. Here's just another example of a schema that demonstrates a few other things. It's a string, ship orders the outer key. This is another element that has a name, address, city, county. That's all pretty straightforward. Here is an item. The max occurs is unbounded. Now that's a new thing. That says we don't care how many. It's not like 10. Maximum is however many of these things you want, right? And then the other thing that's sort of different in here is the fact that this is a positive integer instead of just an integer. So you could say this is a number or this is a positive number, okay? And so there you go. And this one says it's required. So you just have to construct these things, and they are the way that we construct contracts about what XML. So now we've learned a bit about XML and XML schema. Now we're going to talk about what would you do with XML if you found XML in Python, and we'll do that next. So, wow, that was a lot of terminology. XML, schema, min occurs, max occurs. It's time to write some code. That's what we're here for, actually, is just to write some code. And this is the payoff. So part of it is so that when I tell you about this stuff and I say, oh, and there's a attribute, then you'll know what you're doing, okay? And so it turns out that XML is built into Python. There's a lot of things that are built into Python. That's kind of why we love it. That's why it's charming. So let's take a look, and hopefully you've got at some level all the code downloaded for this class and in a little folder called code, and you've got lots of files. And if we take a look at XML1, there's xml1.py. So that's our little program. Now, what I'm doing in this program is I'm actually not retrieving this XML off the network. If you did, you'd sort of do a URL lib and you do a read. We learned all that in the previous lecture. So somehow you've got this XML data in the form, in this case, in the form of a string. So that's the XML data. Might have come from the internet, might have come from a database, which will be what we'll do next. But somehow we've got this. Now, the syntax, if you haven't seen it, this is what's called a triple quoted string. And the start of the triple quoted string is 3 quotes, and the end of it is 3 quotes. And I'm using single quotes because double quotes are actually part of XML. So this is just one big string that goes from here to here, okay? And the new lines are actually part of the string. New line, new line, new line, new line, new line. It's just a quick way to have multiple lines of data all in the same place, okay? And so that is sort of my XML source. Okay, so that is the data. But remember, this might come from a URL or some other thing. URL lib or a get or who knows what we want, but we got our hands on it some. We might have even opened a file up, right? And we're reading through the file and find the XML in a file. But this is just the XML that we've got. It's the important part, it's in a string. Now, you could use regular expressions, you could use find operations, you could look for a less than, then you could look for the tag. You could write some really nasty code if you wanted to. Please don't. Because built into Python is a XML parsing mechanism, okay? And so this is our import statement, pulling in this thing, as ET gives us kind of a shortcut to this really long XML etree element tree as ET. Just put this in, and then we'll just use ET as our way to get at this functionality. So this is sort of a library that we're naming in this code ET. And so all we do is we basically say, hey, take this string data and pass it into the element tree library and parse that string. So this is the act of parsing. It's like deserialization. I can't write that. Deserialization. And that's, I don't know how I got this XML, how it arrived on my doorstep, but I want to make sense of it inside of my application. So we're deserializing it. The method inside of the element tree library is the from string, where we say pass in a string and we get back an object. Now I named it tree. It makes sense to name it tree. By the way, this is just my text editor, so ignore those little blue tildes. So tree is a variable. I could have called this x for all I care, right? And it would be x and x. But tree is kind of what it is. And so what this does is it parses it and gives us back an object. and we can do things to that object to actually look at the underlying data. So this from string finds the less than, finds this less than, finds that less than, makes all these things, yada, 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 and reads all this stuff. You could write it, but you don't want to, right? So you just do it. So then what happens is go read the documentation on this, and it basically says you can take this object that's returned and call various methods on that object. And so what we're basically saying is go find the tag of name. And so that, this little bit of code right here, tree.find of name, gets this thing out of the XML. Then that itself is an object, and we can say, oh, we would like the text of that thing. So that looks inside this thing and pulls that text out. Okay? Or we can say tree.find email. That is this thing right here. That's the tag. This looks a lot like Beautiful Soup, remember? Beautiful Soup is kind of a tree of HTML tags. The difference is the tags in XML are tags that we've defined, right? Tree.find email, bingo. And then .get is a method that we can call. We call the .get method, and we look for the hide attribute, which effectively pulls this little yes guy out. Okay? And on and on and on and on and on. And you can go read the element tree stuff. And so there's just, the whole thing is parse or deserialize the data, get back an internal object that makes sense inside of Python, and then start using that object to look for things inside the XML. And so this is where the magic is all happening. That's where all the hard stuff is happening and the fun stuff is happening. Let me just go run that. Python XML1. Oh, come back. Python, no, clear, escape. Python XML1. This is totally self-contained. And it pulls out the name and the attribute of that email thing. So not too impressive, but it does what it was supposed to do. Okay, so that's our first little application that we're going to play with. And so here's another one, and this one is now going to look at a list of things, right? And so sometimes you have, you know, a tag within a tag within a tag, and there's some text. And that was exactly what we did in that last one. We pulled out text and attribute. But what we're going to do here is we have a set of users, and then there's little user elements. And you'd think of this as like ... There could be many of these things. So we want to parse out the users from within this. The fact that I'm using plural and singular, it's very descriptive, but it has no meaning. This could be X, it could be Y. But we tend to do it when we do XML, when we have a tag that is expected to have a bunch of the things of that, we'll tend to use the plural name for the tag and then the singular name for each of the things in there. So it's a really good common thing, but don't get stuck on the notion that somehow the world understands plurals and singulars, okay? So don't get stuck on that. So here we go. And so what we're doing again is we're using this triple quoted string. So this again is the XML that could have came from anywhere. And then we're going to call from string. We're going to pass in a string. And we are going to get back a tree. I named it stuff this time, okay? So that is, stuff is a, you could almost think of stuff as, you know, we got stuff, and then under stuff we got users, and then under users we got user, dot, 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 and then under user we've got X, which is an attribute, and then we got a thing that's ID, and then name, and then Brent, or one, and Chuck. So this is like this tree view of this stuff. And so by calling from string, we are reading this and producing this structure. Now it doesn't look that way inside Python. It just is something that you can now say, walk down here and grab me all these things, because that's what's going on here. Go down here and grab me all these things, okay? And so that right there of walk down and grab all those things is what this line does right here. Stuff is that whole tree. Find all users / user. So that's a path, right? users/user, it's really all of these. There's going to be many of these second thing. Find everything that matches that little user/user and return me a Python list with one entry for each of the tags. So this turns into this list ends up being a Python array that represents those two users. And each user that you get in that array represents the sequence. So list ends up being a list of users. And because it's a list, we can say, how many did we get? In this case, we should hopefully get 2. Then we can write a for loop. Okay, for item in list. And the things that are in our list these are also XML nodes. They're node objects. And so they have like the ability to find and pull the text out or find and get attributes, right? And so we do the same thing we did in the previous thing where we say item, but really item is now this guy, and we're saying dot find, which means finds this guy, and then dot text, do that better. So item is this, find of ID gets this, and then dot text gets this. So we're sort of, but now we're going to do this inside of a loop. So it's going to do this as many times over and over and over as many users as there are. Okay? And again, this is really simple, and the XML I'll be giving you for assignments is also really simple. But you could also, at the end of the day, even if this turned out to be super complex, sooner or later you would just kind of work together and build a bit of Python code that would pull the pieces that you're interested, because that's what you're looking for. You're looking for like a list of the people's names. Okay? So let's take a look at this one. This was called xml2.py. And if we take a look at it, vi xml2, come back. Click. xml2.py. There's that code. Again, the triple quoted string and the code we just showed you. So if I run this, Python xml2.py, boom. Loop through, found the ID, found the attribute on that thing, found the name, and looped through and did it twice. There were 2 users. This was the first one, and this was the second one. Okay? Now again, the data that you're probably going to be working with came from a file or URL, blah, 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 blah. But you get the idea. And this is very simple, but from these 2 basic patterns of looking down to find a tag or looking down to find a set of tags, that's the 2 basic things that you tend to do with XML. And it's not too many lines of code to find your way into even relatively complex XML. So that sort of summarizes what we're going to talk about for XML. And XML was the hard stuff. Up next, we'll talk about the fun stuff. We'll talk about JavaScript object notation next. So now we're going to move into talking about databases. And it may seem a little strange to be talking about databases in a programming language, but we are using this programming language for doing data analysis. And so it turns out that it's quite often necessary when you're pulling data, especially data you're pulling over a network where you might be rate limited, or you want to store the data in a database. You have a process that reads the data and puts it in a database, and then you can analyze it out of the database. And it makes some of your processes go really fast. It allows you to change your analysis and not lock your analysis into the retrieval of the information. So it speeds up your overall workflow, but you have to learn a bunch of stuff so that you can put the information into your database. Now the first task that you have is to install your database browser. There's a couple of different ways to read and write these files. We're going to use Python to read and write the files, but we want a way to read and write the files directly. And so this is a code that you can download for the Mac, for Windows, for Linux. And there's also a Chrome plugin that you can get for SQLite that you can do everything that we're doing in the class. And so I don't really care how you achieve the things you're going to achieve in the class, because we're going to grade you not so much about how you use things, but instead we're going to look at the databases that you produce. Okay, so stop now, download this, install it. It should be simple, should be easy. Check with the forums if we have some problems. So relational databases are a whole subfield of computer science, and it might be best to talk about what life was like before relational databases. You use relational databases thousands of times a day without even knowing it. If you imagine something like a learning management system where there's hundreds of thousands of users and terabytes or petabytes of data, and you log in and within a half a second it shows you what you're supposed to see. You can't read petabyte of data in a half a second. You just can't. And in the early days, we used to have data that was small and computers that didn't have a lot of storage in them. And so we tended to use tapes. And we would put the data like on a magnetic tape, and we would sort the data. We would have the old bank balances on one tape. We would have the transactions, and then we would apply read one balance, check to see if that transaction, if it changed, then we'd store the balance. And then you would have like last night's bank balances and tonight's bank balances. And then the next day you would put this over here and read the old bank balances and make changes. And this is how day after day in the 60s and the 70s we would update data. If you look at old computer videos, you'll see these little spinning things. Well, those are tape drives, and that's where most of the real data was stored. And it was but as computers got faster, as they got more memory, and as we started to store data more in the memory of computers and on the disk drives, whole different ways. So you didn't have to read to get through the account that starts with a letter S. You didn't have to read through all the data from A through S just to get to my account that starts with S. And then it'd be like, oh, wait a sec, we have a disk drive that we can skip all the way and skip back and skip over here. And so the problem became how to make use of this random access medium in which we can store data in a way that's efficient and fast and clever. So just because you could randomly access the data didn't mean it was fast. You still had all the data to look at, and if you just looked at it sequentially. So relational databases were this applying cleverness to how we would use random access data storage, mostly disk drives that spun. And it really sort of emerged in the 60s and the 70s, and whole companies were formed like Oracle. Oracle exists because smart people figured this problem out before other smart people did. And so they got to form a company, and Oracle is the leading database vendor on the planet, and much of its revenue comes from its database product and things built on top of its database. But literally, before 1960, the concept of database really wasn't an idea. It was something that happened as storage and what we wanted to do with computers. So this is where if you had to really read a tape to log into a computer, it might take 4 hours to log in, which would be unacceptable in this modern day and age. As I mentioned, the database is sort of this technology that emerged, and it emerged from a lot of theoretical analysis. And the underlying foundations of database have to do with some really powerful mathematics. And so this powerful mathematics still is present in some of the terminology that some people use to describe databases. And so there's really kind of two parallel terminologies that you will encounter. You'll pick a book up and you'll kind of be able to read it and say, oh, this is using the highfalutin, hoity-toity language, which is the more math-oriented. So in the more math-oriented, we use the words relation, tuple, and attribute. That's kind of the fancy way of speaking about it. But sort of we programmers who just do our thing, we would call it a table, a row, and a column. Now, table and row and column is kind of the wrong way to think about it if you're trying to understand the true underlying amazing mathematics. The underlying mathematics is, don't worry about the underlying mathematics. Just be aware as you're reading. Don't be surprised when people lapse into this more fancy nomenclature. So the idea is that you model data at a connection point. Rather than like, here's data and we're starting here and we're reading through it, the idea is if you model everything as a connection, like who a person is a connection between this, that, and the other thing. And so this notion of modeling stuff at a connection is the underlying math that makes databases fast, But when we programmers think about it, we kind of think about it as rows and columns. And so here's just a screenshot of a spreadsheet that I made. Along the bottom, you see the names of the various subsheets: tracks, albums, artists, genres, and titles. And those are like the database tables. And then each table, if you select it, has a row and a column. And so it's got these columns. This has 3 columns in it, and it has a bunch of rows. The other thing, when you're doing stuff in a spreadsheet, you just kind of come up with a data model, a schema, a strategy, so that you know that the first column is always the title, second column is a rating, because if you didn't label it, it would make no sense. So we often do something where the first row of a spreadsheet is kind of metadata about the columns, right? Now, the spreadsheet doesn't exactly know that you're doing it, even though some of the things you do, like sometimes it sorts and says, oh, check this tick box to say the first row is title, so don't sort it. So when you sort stuff, you only sort like the bottom part of it, right? And so it sort of knows that the title, but in a database, this becomes what we call the schema. All these titles, and we have rules, like this have to be integer numbers. This has to be an integer number. This has to be string, no more than 128 characters. So we make strong contracts about the content that sort of at some level feels very similar to what we're doing when we're writing these titles, but in reality, as you'll see, is far more complex and far more intricate. Now, if you've ever tried to do something like we're going to do with this database, and that is categorize your music collection, you find that a spreadsheet is a really hard way to categorize your music collection because of so much repeated data, and we'll figure that out in databases. So the idea that they came up with in the 60s and the 70s is there was a way to represent data on a disk, and it could be randomly accessed, and there was pointers that pointed to something else, and whatever. And in the early days, they figured out how to technically solve fast access to lots of data by hopping in various ways, indexing, doing clever things. And the early ways that we programmed these databases is we sort of revealed to us application programmers the low-level capabilities of read this thing, then jump to this other thing, then read this other thing, then jump to the other thing, read this thing, jump to this thing, which made our lives really difficult. And so we had to write really sophisticated programs, but when we did, they could function very rapidly. And so what happened over time is instead of our code talking directly to the files or the databases, instead a layer started to build up that we called the database application, or database. I'm not doing a very good job drawing there, right? So here's our database, and it has lots of complexity in it. And originally we would sort of just talk straight to that complexity, but after a while we would have a database application, and then our application, our code, would talk to the database application, and the database would know all the magic stuff. And it was what we call in computer science an abstraction, which means that our job, this is us, and our job was easier because of the complexity could all be hidden here. And so the question becomes, then how do we talk to this really powerful piece of software that we call a database? What is living here? What is the way we communicate? Sometimes we would call this an API, Application Program Interface. So this is our application. This is actually another application. The database itself is an application. And so we have to have an interface so that our application can talk to the other application. And just like in the previous lectures, this is like a service. It's taking care of it. And ultimately, let me change the color here. It's getting kind of messy. We can sort of think of this thing right here, both the data and the software that understands the shape of the data, as just a service in a service-oriented architecture. So once again, what we have to do is define, to use the service-oriented architecture, the cut point. What is the cut point between our application and this magic stuff? And this is Oracle, right? So it's lots and lots of money, and it's amazing. It's just really good software, right? Oracle's really good, Microsoft's really good. So what happened was we decided to create a standard at this point. The industry did. Folks got together with National Institute of Standards and Technology, NIST, and they agreed on a language that was the API between an application and a database system. And the name of that thing they came up with was SQL, or the Structured Query Language. Okay? And so that means that, wow, I've made such a mess of this, I have to start over again and draw another picture, right? So that means that over here you could have Oracle, over here you could have Microsoft, and here you could have App 1, and here you could have App 2. And App 1 could talk to Oracle, or it could talk to MySQL, or App 2 could talk to Oracle, or App 2 could talk to MySQL. And so because they use the same communication between Oracle and MySQL, it means that you can write an app that's portable between different databases. And it turns out that this SQL is a beautiful language. It's just a gorgeous language. The reason I don't teach SQL as the very first programming language is you would be ruined. If you learned SQL, you would never want to program in any other language. I think it's the most beautiful language that I've ever encountered. It's beautiful because of its simplicity and its expressiveness and its power, but then it's a very beautiful and elegant language. The problem with SQL is it depends on the data being pretty. It's a great way to write code about really gorgeous data. So part of what we're going to do is learn how to make the data look really good and then write really cool stuff. Python, on the other hand, is a little rough around the edges, but it just has no problem dealing with unstructured data or data that's imperfect or whatever, and you can just keep writing more Python, and eventually you're like, oh man, I thought it wasn't as complex as this, so I got to add a little bit of if statement here, and add another if statement there, and do another thing. So Python handles unstructured, rough data much better than databases, and that's why Python plus SQL is such a powerful thing. Python cleans up the data. SQL is a great way to store and retrieve data. So what SQL does is it has 4 basic functions. We call it CRUD: create, read, update, and delete. Update is missing here. CRUD. So that's a database term, is CRUD: create, read, update, and delete. So up next, we're going to talk about how you as the application developer are going to interact both in large projects and in small projects. Small projects are going to be the more typical thing that we use in this class. So that's what we're going to talk about in a bit, and how you use software to interact with databases. Now we're going to talk about the second of our serialization formats. So you take a piece of code, a piece of data inside of Python, you got to send it to Java or PHP or whatever, and you got to come up with a serialization format. XML is a great serialization format for documents, especially things that kind of have infinitely nested kinds of things like a paragraph within this and that. And HTML is kind of like XML, and it's a good way to represent documents. And so that's why this JavaScript object notation is not really used to represent HTML at all. And so JavaScript object notation, and I'll give you this video of Douglas Crockford. You should watch it. He's a pretty funny guy. He claims that he did not invent JSON, that he simply discovered JSON. And it is really just the literal, it's a subtle cleanup of the literal syntax for JavaScript, or the constant syntax for JavaScript. So in Python, you say, here's a list, and it's curly bracket, a square bracket, this, comma, this, comma, this, comma, that, and that's a list, right? That's the constant, what a list constant looks like. Well, JSON is really nothing more than a cleaned up version of how you describe a list or an array in JavaScript, or an object in JavaScript. An object then becomes like a dictionary in Python. And so JSON looks a lot like Python. It looks like Python constants. And so it's kind of very natural for somebody who knows Python to look at JSON. But it's not Python, it's JavaScript, but it looks pretty much the same. And watch the Douglas Crockford video. Douglas Crockford is an irascible, funny guy. He wrote this book. The book on the left is written by Douglas Crockford called JavaScript: The Good Parts. And on the right side is another book written by another author called JavaScript: The Definitive Guide. And the relative thickness of the book is making the point. So JavaScript is a super powerful and amazing language. And what Douglas Crockford says is we shouldn't use all of it. We should only use the good parts. So as you will see in the JSON video, the interview that I did with Douglas Crockford, JSON.org is something that he just put up, and he pretty much defined it, and the world just started using it. He didn't have a corporation or the US government or anybody trying to force JSON down anybody's throats. He just defined it, registeredjson.org, and voila, we have a whole industry of JSON stuff now. So JSON solves roughly the same problem. The thing that JSON doesn't do as well is an infinitely set of nested things like XML is better for that, and it's a little less self-describing. Okay, so JSON really only has two basic structures. It is either a list, it would call that an array, or a dictionary, it would call it an object. Okay, so dictionaries and objects are key value pairs, and then lists and arrays are lists. And so it turns out that one of the things that JSON has as its best advantage is the fact that inside Python we tend to make lists and dictionaries. And in JavaScript we tend to make arrays and hash maps. And JSON is a great way to represent both of those structures. So those are the two structures that we tend to do language after language after language. So if you think of the goal of one language has some data in it, we need to serialize it, send it to another language, deserialize it, pull it out to another language. Why not come up with a format that's most natural between those? Okay? And so the syntax, again, will seem familiar to you because it almost looks exactly like Python. So this is some JSON. There are no lists. This is just objects. And so objects can be nested. So again, this is the triple quote syntax. So this is a string. And again, where you're going to get this is not necessarily just from a string, but it makes these very simple. And so this is, when you start with a curly brace, then you're going to get a set of key value pairs followed by commas. And then this is a key, this is again a key, and this is a value. But this value here is a whole object. And within that object, there's key value pairs, comma, key value. And then there's another one. So if you look at this outer thing, there are three keys. The first key is a string, the second key is an object, the third key is an object. And then within this phone object, we've got a key value pair, two key value pairs, and within the email object, we have one key value pair. And this is kind of roughly the equivalent of the person's name and the fact that the internet phone number is international. Now, one thing you'll notice is there's no attributes. And again, that's where XML sometimes has advantages. And so, but that's okay. We just made a different data type called type to capture what was an XML an attribute. We really have we just have key value pairs here, and that's it. Dictionaries within dictionaries within dictionaries. So it's a data structure thing, and you kind of construct your shape of your JSON the best way to move data around. Okay, so this again is that JSON string in triple quotes that came from wherever, and we have to deserialize. That's the first thing you got to think about. Got me some JSON, time to deserialize that. Well, like everything we do in Python, we have an import statement. JSON, built into Python, boom. Okay, so it's built in. So you say import JSON. So that means you have a whole library of stuff to do all this stuff. It's even cleaner than element tree. So import JSON, that's the JSON library. Use the load S. So the load S, load from string is what that says, and we pass in this string data, all of it. Double quotes are just part of the JSON, right? The double quotes are just part of the JSON. So that says this is the deserialize step. Deserialize from string to internal structure. But this is where everybody loves JSON. The thing you get back is a dictionary. It's not like an object that you can query, it's an actual dictionary. So if you were to look at this dictionary that comes back, well, it's got 3 keys in it. How many things? There's 3 of them. It's got key values. And the way you pull stuff out is you just use it as a dictionary. Info sub name or info sub email sub hide. So info sub name is that text. You don't have to go in the dot text. If you go back to the XML, we had to do all these, find this, then go within that thing. Because XML was thinking of the world as trees, which is not how this is. This is thinking of them as lists or key value pairs, right? So info name says info is this whole thing. Sub name is this value right here. That's what you get. Info sub email is this thing, but that itself is a dictionary. So this sub email retrieves a dictionary, and then sub hide within that retrieves the value that's under the hide key within that inner dictionary. So you can see that it's a lot easier to think about how to pull this apart, because this turns into a native dictionary. That is super nice. That's one of the super advantages of JSON, and that's why everybody loves it, is you just parse it with this load S, and then you use it in its natural form in JSON. So you start with a hash map, or you start with a dictionary and a list, you make JSON, and you pull that in to Java, and it's a hash map and an array, and it just works, because it's really better at representing the natural things that applications do. So this code's in JSON1.py. It's going to be super boring because it's going to be really easy. VI JSON1. So there we are. Code you just saw before. We'll run it. Boop. Pull that stuff apart. Simple, beautiful, elegant. Similarly, if we take a look at a situation where we're going to do a JSON representation of a list, what we see here is a square bracket. Again, looking like Python. Square bracket is the way to indicate that it's a list, although they would call it an array in JSON, but for us in Python we call it a list. And in our list we have two things in our list. A list is things, in this case an object, and another object separated by a comma. So these are a kind of a person object, and in the person object we got ID maps to 1, X maps to 2, name maps to Chuck. In the second object, ID maps to 9, X maps to 7, name maps to Chuck. So there are two objects, 0 and 1. Sub 1, this is sub 0, and this is sub 1. Okay, so again, we're using the triple quote syntax to produce our deserializable code. The string that's going to be deserialized, we use the JSON library that comes from the import. We do load string, which is the deserialization step. And what do we get back? This is a list. Not an object that acts like a list, it's really a list. Because JSON has these two simple things, it's just lists and dictionaries. So JSON loads, sees the bracket, says, oh, it's a list. So you get back a native Python list. Okay? So we can do a len, say how many did we get? In this case we're going to see 2. And then we can loop through using for and in for item in each info. So that means that item is going to loop through this one, and that's going to loop through that one. And then item, because these are curly braces, item is an object. So item sub name, item sub ID, and item sub X. So we're just using standard Python-ness of this. Again, super elegant. Okay, let me show you that one. Not that it's very exciting. That was called JSON2.py. So there we are. We have at the top, we have the string, and then we parse it and print out, it's not working very well, parse it, print it all out, and then we loop through each one, which is effectively looping to that one, and then that one, and printing out the pieces based on the fact that this is a list of dictionaries. So Python JSON2.py. Poof, extracted. And again, you can kind of compare the XML and the JSON because they're really solving the same problem. But there are subtle differences between the XML and the JSON. And the JSON is much easier to work with, but the XML, if you keep looking back and forth between the XML and the JSON, I think you'll agree that the XML is harder to work with, but it's more expressive. And those are like two sides of the same coin. And so for the things that you can express in JSON, JSON is pretty much uniformly preferred. But for things that are more complex, that are hard to represent in JSON, it's like you're kind of shoehorning them into JSON. You go like, oh, XML would do a better job. So I think as we go forward, we're going to see applications that talk to one another, sometimes use XML and sometimes use JSON. So up next, we're going to take a step back and talk just a little bit, including a video, about what's called the service-oriented approach. And that's how you build meta applications out of little pieces that cooperate over APIs and web services. So we'll do that when we get back.
So JSON is the world's best loved data interchange format. I discovered it in 2001. I don't claim to have invented it because it already existed in nature. I just saw it and recognized the value of it, gave it a name and a description, and showed its benefits, but I did not invent it. I don't claim to be the first person to have discovered it. There were other people who I later found out had come along the same idea in 2000. The earliest instance I found of JavaScript being used as a data interchange format was at Netscape in 1996. So it's an idea that's been around for a while. And if you look at other data representations, like the property lists that were used at Next and then later at Apple, except for a couple of cosmetic changes, it's the JSON notation as well. So it seems like it's an inevitable sort of representation for data, at least data that is intended to be consumed by programming languages. And ultimately, that's all data. I started with JavaScript, but my first application was facilitating communication between programs written in JavaScript and servers written in Java. So I recognized that even though it was born out of JavaScript, it could be and should be language independent. I simplified it as much as possible, took as much out, tried to make the simplest possible specification for how to structure data and put it on the wire. And that ultimately became called JSON. In 2001, I was in a company I had started called State Software, and we developed a platform for doing applications which could be delivered through unmodified web browsers, what today is called Ajax. But in 2001, that was kind of a radical idea, and not many people would believe that it was even possible, or if it were, that it was a good idea. But we produced some brilliant demonstrations, and we were starting to make some progress in trying to convince potential customers that they should adopt this style of application development. And as part of the description, we'd say, and then we use this JSON idea for communicating the stuff back and forth. And they say, JSON, what's that? And they say, it's this thing we found in JavaScript, and it's really great. And they say, oh, we can't use that. We just committed to XML. So, no, we can't. But XML is wrong for all of these reasons. It's hugely expensive. It's much harder to use all of that. Well, we can't use that thing you did because it's not a standard. And we said, it is a standard. It's a proper subset of ECMA 262, which is a standard. They said, no, that's not standard. So I decided if I want to be able to use this thing, I need to make it a standard. So I bought JSON.org and put up a web page and sort of declared it's a standard. That's it. That's all I did. I didn't go around trying to convince industry and government and everybody that this is what they should do. I just put up a website, basically a one-page website, and over the years people discovered it and realized, oh yeah, this is so much easier, I'm just going to do that. The thing I never understood about XML for data interchange, okay, so generally the pattern is you've got a query, you send it to the server, it gives it to the database, and you get back this XML thing, and then you have to send queries to that in order to get the data out of it. And it says, why can't you just give it to me in a form where I know what it is and I can use it immediately? And so that was the main benefit of JSON, I think. It wasn't that curly braces are so much better than angle brackets. I mean, ultimately, none of that matters. The thing that mattered was that the data structures that JSON likes to represent are exactly the same data structures that programming languages represent. when Ajax was formulated, the X in Ajax was supposed to be for XML. And the smart kids right away realized, well, this is too hard. We don't want to be doing XML here. And some of them discovered, hey, you can use JSON here instead, and it is so much easier, so much faster. So they started doing that. And for a while there was a debate, where some people were arguing, Jesse James Garrett said the X stands for XML, so you can't use anything but XML. That didn't last very long. There were a number of other alternatives to XML that were being considered around those times, but JSON was the only one that was designed specifically for Ajax. Probably the boldest design decision I made in designing JSON was to not put a version number on it. So there is no mechanism for revising it. So JSON, we're stuck with it. Whatever it is in its current form, that's it. And that turns out to be its best feature. Because it wants to be a low-level thing. It's basic infrastructure. It's the thing that you pile everything else on. It's sort of the equivalent of alphabet in a language. We might make up lots of words and lots of ways of having sentences, but it's very uncommon to make up new letters. And that's sort of the place where JSON lives. So it's good that it's not going to change. I expect maybe someday we'll find that there are really important things that JSON doesn't do, like cyclical structures. Graphs are not easily represented in JSON. They can be, but it requires a level of indirection, a little bit more work. Someday we might decide we don't want to do that work, and then we replace JSON with something else. We will not extend JSON to do that. We'll replace JSON. And even after we do that replacement, everything that was ever developed that still uses JSON will still work, because JSON will never change.
So now that we have all these skills of parsing XML and reading XML and reading JSON, it's a good idea to take a bit of a step back and say how applications that work together, most typically like an airline website, can take data from many different sources and bring that data all together. And we call this the service-oriented approach. And so you go to this application and it's like, why is it that when you book an airline ticket, they seem to be able to also book hotels? And that's because, are you really giving your credit card to the hotel site when you're reserving a hotel? And you're not. If it's a well-designed hotel credit card site, it's not. And so what happens is these meta applications assemble capabilities from many different applications. And so these are a way to use services from other applications. And these services often publish rules that say, okay, this is the URL that you hit, and we're going to give you XML, and you got to do this other thing to log in and do these other things. And so it's sort of like how you would use an application, except instead of being like, here's what it looks like and here's where you click, it's how the application that you're going to write is going to use their application. So that they are a service. They're probably in the cloud, and they're sitting on some bunch of servers somewhere, and you're going to start hitting their URLs, and you're going to accomplish something using that. And we're going to even do some sample code in this. And this is called the service-oriented approach. And we have a little video from some friends of mine in England that sort of tries to make sense of this, to talk about how it is and why you need to apply standards and why you need to be sort of very thoughtful about how do you build these APIs and how they cooperate and how they work together. What happens is you sort of build a thing, and then you like break it into a piece, and you pull these things apart and you talk, and then you realize, oh, it'd be better if a whole bunch of things talk together, but then we got to write down documentation about how it all works. And then it evolves to this thing where you say, look, now we've really got a very carefully and well understood notion of what these applications are supposed to do. And so that's what it is in this service-oriented architecture and web services. And so this is just sort of my intro to the video that will come next. So now that we understand what a service-oriented architecture is, we know how to write Python to read and write this stuff, and we can talk URLs, we're going to bring it all together now, and we're going to actually talk to some real live web services. As we talk to web services, we have to understand how they think. And we may later be building applications that export web services, but the first thing we're going to do is use somebody else's web service. And we'll have to read their documentation. And the documentation, they often call these web services APIs, or application program interfaces, because they have an application that's got brains and skill and all this stuff, and we have an interface that we can make use of the services that an application provides. So you're like, whoa, what's the API to Twitter, or what's the API for this, or what's the API for that? So that's when you hear this word API, that's really what we're talking about. It is a defined set of rules to interface with an application program. There's a couple different web service technologies. Thankfully, the crappy old SOAP is really complex. If you work at a big corporation, they might still use crappy SOAP. It's whatever. It's just whatever. Just tell them they should do REST, and if they insist on you using SOAP, then you should double your salary. Just tell them that. So SOAP is so bad that you have to pay me twice as much to work on it. REST is the way we're going to do this. I'll have a video about REST from the creator of REST, Roy Fielding, and you can see this. It's a way of sort of viewing these services as a set of resources that we're pulling, and it makes this sort of interaction be more like the simple use of the web the way browsers use it. We go get data. It's in a different format, but we're still sort of saying, give me this thing, give me this thing, give me this thing, and that data happens to be in XML or JSON. So REST is a pattern that we use. So the first API that we're going to play with is the geocoding API from Google. Now, Google has a great search engine. They have all this data about the shape of the world and maps and all this stuff, and you can make use of it. If you have, say, a survey and you ask people where they live, well, they're going to be rather imprecise. They might say Ann Arbor, Michigan, or they might say Eastern New Jersey, or they might say, Beijing, China. And you may not, it may be very difficult, but you can actually send all those queries to Google's geocoding API, and you will get a ton of data based on Google's best estimate. It's the same thing as what you would type in Google Maps, like Ann Arbor, Michigan. It figures out what you mean. Well, this figures out what you mean and gives you back a bunch of data about the statement that you make. So here's a little example. It's much longer than this, but this is a JSON interface. And if you know what the API is, and you got to read all the documentation, so go ahead and read all this documentation. And the documentation will tell you, unless they've changed it, which they have the right to change it. It's like free, so we can't complain too much. But for now, what that says is you say mapsgoogleapis.com /maps/API/geocode/JSON, question mark, all this is necessary, sensor equals false, ampersand address equals, and then you put the actual address, Ann Arbor, Michigan, plus means space, and %2c, I think, means comma. Okay? So it turns out that what's cool about these REST-based web services is I can actually just take that URL, this one right here, copy it, and go stick it into a browser. Come on, browser. And I'm going to just paste that URL exactly as it says. Now again, you derive this from the documentation to figure out how you're supposed to put this URL together. But in effect, this part here, this part right here, that was that user entered data, right? And you encode it a certain way. And there's actually libraries in Python that help you do this. But for now, I just want to show you how you can type this in. Ann Arbor, Michigan. And when I hit enter, it retrieved JSON. This is like a web page, but it's a resource. It's actually a dynamic resource because the resource isn't the same. It depends on the query values that we put in here, Ann Arbor, Michigan. And so it tells us something about this. We'll make it big. It's in Michigan. It's the United States. Here is the geometry, the boundary of it. It is the center of it. Here's the center of it. Latitude and longitude of the center of it. That would allow you to place this on a map if you want to take all your students and put it on a map. So if you can retrieve this JSON based on this parameter, then you can parse this JSON using the JSON library that we just showed you. Okay? So that's what we're going to do. And the real application for this might be a survey. Matter of fact, it's the application I use it for. When we do survey data of all the students, so we want to geolocate them, I just take the words that you put into a field and I send it to this API. We'll talk about some of the issues and limitations, but let's just take a look at how it actually works to do this. So this is a bit longer bit of code, but let's take a look at what it's really doing. It's not all that complex. When we run it, our program's going to ask for a location, and we'll type one in, Ann Arbor, Michigan. It can take anything. And so I am going to use URL-lib, which is how we retrieve data on the internet. We need a URL and import JSON. And JSON is how we're going to use to parse the data that comes back. So the URL that we're going to use is this URL that we read from the documentation. We're going to stick the question mark at the end of it. And then we're going to write a loop that goes around and around and around and asks for the location and checks to see if the input that came back is 0, and if it is, we're going to end our loop. And then we're going to take that service URL, and remember the part where we had the plus, Ann Arbor, and the plus and the %2c? Well, there's a magical thing inside of Python. We don't need to know that. We call urllib.url_encode, and we have the key value pairs in a little tiny dictionary. That's what this curly brace is. It's a dictionary of key value pairs. Sensor equals false, and address equals, this address right here, is whatever address we typed in. And it does all that encoding for us. That's what it's saying. Encode this address value that the user typed in a way that's legal to be put onto a URL. Do that for me, please, automatically. Right? This is string concatenation. And then it'll print this whole URL out. And then what does it do? It does a URL open of the URL. And then it does a read of that whole thing, which reads that JSON, which is the curly braces and all that stuff, right? So that reads the JSON. So this line right here, Python, we don't have to do too much work. Open URL, read the whole thing, new lines and all. And we are going to get something that looks like that. This is what's going to be in that string. So that's what's in the string. And we're going to use a try and an accept, because sometimes if this data is bad, then load S will blow up, and we're going to do an accept. We're going to do a try and accept in case that blows up. And then we're going to take a look at the JavaScript to see if we got an OK status. So JS ends up being the parsed JSON, right? So JS is the whole JSON, and this is a little bit tricky, but ultimately you're just reading inside here to check the status. So it's not down here, status. Oh, no, status is right there. So we're checking, is the status okay? We're also being a little more clever in the code that I wrote to check to see if it went wrong, or the exception happened, or if the exception happened or the status is not okay, then I just print out the nasty stuff, and then I continue back up and loop again. Then the first thing I do is JSON. This is in the JSON library. Dump S says dump in a string. And takes the JSON, which is the parsed. In this case, it is a parsed dictionary, because the outer thing is a bracket, which means this is a dictionary. There are lists within it, but the outer thing is a dictionary. And so this is a dictionary, the parsed dictionary. And then this is called pretty printing, and I mentioned that before. It says take this stuff, print it out nicely with an indent of 4. So it does all the indenting and all that stuff, so it's readable by humans. But computers really don't care if it's indented, but we humans care a lot if it's indented. And then what we're going to do is we're going to parse it. Now, it's a little tricky. And when I'm writing this code right here, I don't all write it at once. But what you're really doing is you're looking at the JSON syntax, and you're sort of diving down into the JSON. And I sort of do it one at a time. And I use a lot of print statements, do it over and over and over again. But then when it's all pretty and I know exactly where the thing is that I'm looking at, I'm in good shape. So what we're doing is we're taking the results. So let's go back. The results is this. And notice that the results is a list. And it turns out that there is more than one location. And so this is a list of locations. But what I'm doing is just taking the first one. So result sub 0. All right, result sub 0. And then if we go up, result sub 0 is this whole object. And then we have geometry, which is this little object. And then we go to, within geometry, we go to location. So now we're down into this little thing. And then we pull out the latitude. So this, let me clear that. Let me clear that to make it clear. Clear. This whole thing, that expression extracts this number. So that's how you sort of build your way down in. And we had to go through a dictionary that included a list that had another a list of dictionaries, and then a dictionary that had a dictionary and another dictionary inside of it. Right? But that's what we're doing here. Look up in a dictionary, then the first element of the list that you get, then there's a dictionary inside of a dictionary, and then a value inside the dictionary, and out comes the latitude. It takes a while to write this, right? I mean, it's much easier for me to explain this than to write this, and if you watched me write this, you would see I don't write it all correct because it'll usually blow up with a, error of some type. I write it one piece, I kind of go here, I get that part working, then I add another thing, and then I add another thing, and then finally I get the thing I want. So you don't try to write this all at the same time. So this pulls out the latitude and the longitude, and I print it out, and then I just pull out the formatted address, which is within results, the first entry, and then the formatted address, which is Ann Arbor, Michigan, USA. So we typed in Ann Arbor. This is what we typed in and then Google did the rest of that for us and gave us back the actual address. This is an address that is sort of like a more precise address than what we typed, and so it got, pretty awesome. Okay. Okay, so it'll take you a while to look at that. That's a pretty complex bit of code, but it's, constructing a URL using this URL code, hitting the URL, then parsing the JSON, and extracting just the information that we want. So it's a lot of fun, actually. A lot of fun. So let's actually run that guy. It's called geojson.py. So cat geojson. So there it is. That's that same code I just showed you. So now I'm going to run it. Python geojson.py. And I'll do Ann Arbor, Michigan. And so you'll see, so that was really fast. So this is the URL that it hit. We use the encoder to get this little bit right here right, because there are rules about passing parameters on URLs. We don't need to know the rules, we just use the encoder. We got 1,736 characters back, the status was okay. This was the geometry. We got the, it also knows this in terms of like the boundaries of the location, like a square. The actual address and all these things, the formatted address, we pulled all that stuff out. And here is, so this is the JSON we got back, and this is the stuff we extracted, right? So I can say things like North Quad. I don't even know where North Quad is. North Quad is my office. Will it find it in the right place or not? I don't know. There might be many North Quads. It's not. It doesn't know that North Quad is my office. Apparently it thinks that North Quad's in Claremont, California. What are they thinking? I don't know. Oxford. Where's Oxford? So there's Oxford. It knows where Oxford is, obviously. So we can ask where Universal Studios is. Where's Universal Studios? Florida. Let's see if I can make a typographical error. Dinsey land. Disneyland. But I've got it wrong. Will it find Disneyland? It can even fix spelling errors. So what you've got is like 35 lines of Python or 30 lines of Python code, and you're taking advantage of like all of Google's awesomeness by talking to the Google API to do this. Okay? So I'll just hit enter and we're done. Okay, so this is, again, this is how your application can become more powerful by integrating the services that are provided by another application, or in the case of you cleaning up data, it does that too. So you got to be careful. There's no such thing as a free lunch. We love Google, and they give us this free geocoding thing. But the data is super valuable, and there are people who would do nothing except sort of like make a really dumb website to help people look up addresses and just use all the Google stuff, and their website would be making money and putting up crappy ads and that stuff. So these folks often will demand an API key or charge for usage or have rate limiting. And they might change the rules as things get more and less popular. So that's how we're going to talk to this first API. But we're not done yet. And there's actually some more issues having to do with APIs that we'll cover in the next lecture. So we just got done doing something almost magical. We wrote a Python program that talked to Google and used the Google search engine, geolocation search engine, to look up on a user-entered bit of data and get back all kinds of information, like the real address of the place, and perhaps if there was a business there, we would find this. And you're like, whoa, that's pretty cool. Well, Google doesn't just let you have access. What we did was free. But these APIs, the data, the compute servers, and all the debugging are not free. I mean, Google spent a lot of money to make sure that that data really worked. Now, we use it every day in Google Maps, right? And they make some money off of Google Maps. But they don't want you to be able to use their intelligence to make your own competitor. And so these are rate limited. So if you take a look at Google, you will see that you cannot do infinite number of these things. Or in other situations, you have to have a key, and you might even have to charge for usage. So if you take a look at some more detail, you will see that this geocoding API that we just used means that you can only do 2,500 requests per day. If you want to make a business, you can pay for a higher limit, for example. And you can read right there. They're there to abuse or repurposing, and they might change it. So always when you're working with an API, figure out what the rules are. It turns out we're going to use this API later in the course, and we're going to have to use a database to deal with the fact that if we really were going to use this seriously, we could only do 2,500. And if you had 10,000 of these things, it would take you 4 days. But you got to run a program that starts and stops on one day, then waits, starts and stops the next day, then waits, and on and on and on. So that's the Google Geocoding API. I like that because it's rate limited and it doesn't have a password. So now what we're going to do is we're going to use the Twitter API. So I started with the Google API because that did not require an authentication. But the Twitter API does require authentication. Now I've given you sample code that does this. Please don't sort of abuse Twitter. Don't get yourself kicked off on Twitter when you're running these applications. Make sure that you print everything through a loop and hit Control-C or blow it up or whatever. So don't get yourself in trouble using the Twitter API. I'm not going to give you any Twitter assignments. I just want to sort of show you how this works. So what happens with Twitter is that you must run this API as yourself. So, normally you could log into Twitter and you could use it on the web and it knows who you are. But when you're using this API, you've got to hand some information to the application to pretend to be you. And in Twitter, they use a technology called OAuth, and they give you what are called access tokens. And what you do is you use these tokens to generate signatures that you send, and then Twitter checks the signature and knows it's you. So Twitter has a rate limiting, but unlike Google's rate limiting, which kind of is based on your address or who knows what it's based on, Twitter's rate limiting says you, no matter what, can do sort of 25 of these things a day or 2,500 of these things a day. So you have to go into Twitter if you have a Twitter account, and you go into access tokens, and you basically are going to create a new access token. And so you have to authorize an application. And so you say, I'd like to add an application. I'd like to give it permission. So you add the application. And ultimately, when it's all said and done, and I just called the application Python on my laptop and then gave it a key. Now the key ends up on the screen where, like here, it ends up in little areas that you cut and paste. And you have to cut and paste these keys. You click on here and you read all the stuff and you get all the stuff. And then you have it. And then there is a little file in my application called hidden.py, and it's got exactly this. It's not the real key, but they look kind of like this, except much longer. So if you're going to use the Twitter API, the first thing you have to do is edit this and put in the consumer key, the consumer secret, the token key, and the token secret. And those things all come from this page and this page in here. You just are cutting and pasting. So there's API. You scroll down, you'll get a secret. You click on here, I'll get the other two values. So you have to know what those are. And don't share those with people. You notice I have them hidden. And that's because I don't want to share them with you, because then you could do something, right? So I take the screenshot and then blank the stuff out. And then when I put this in the file for myself, which I won't show you, I currently have my values in there. Now this doesn't authorize anybody, but it authorizes an application. So I go to Twitter, I put these values, I say I need to authorize an application, and it gives you these 4 strings that you then can authorize the application. So what happens is, once you've done this, you use these tokens to create URLs that allow you to legitimately access Twitter's API, Application Program Interface. And so we're going to use this thing with OAuth, and it turns out OAuth is this technique for sending signatures and verifying signatures, and it's used in many applications. Google uses it, Facebook uses it, Netflix uses it, Twitter uses it. It's a really simple and yet very elegant security mechanism that can make it so each URL that you're going to hit can be signed separately using OAuth. It's quite elegant. I've written some OAuth code myself. And we're going to actually just hit a URL, this URL right here, and we're going to go find a timeline. And we'll talk a little bit more about making these things. Right now I want to talk about the OAuth, the security that it takes to do this. And so I have written a bit of code called TWURL, and that's actually right here. It's in the thing, and it takes those secrets and it calls a routine called OAuth. So OAuth is a library. So Python, like always, has OAuth built in, and hidden is the hidden file. Hidden.py is this file. Hidden.py is that file, and then the TWURL reads the secrets. It imports the OAuth library, uses URLlib because it is going to encode one of those parameters. And then, so this stuff here, don't worry too much about that. If you were to say, like, how do you do OAuth signing in Python and go to Stack Overflow, you would probably see something that looks something like that. As a matter of fact, that's probably how I got it. But the idea is this is a function that takes a URL and then some key value parameters. This is a dictionary. And then it basically creates this long URL. So this is the URL. And then all this other stuff. And when you look at this, all this stuff here, this is the signature part, right? And this URL, the screen name of Dr. Chuck, well, that's sending a parameter. The timeline is what data you want. And then this code right here adds all this other stuff, okay? And so I just made it so I had this thing like, oh, here's the URL I want to hit, and here's the parameters I want to put on that URL. Augment this URL with all this magic stuff. So this routine called augment adds this stuff right here so that we can just hit the URL and then get data back. If you go back to the previous thing where we were talking to Google, we would just make the URL and retrieve the URL, and it worked. Now we have to make the URL, augment it with the signature stuff on it, and this is the signature stuff, and then we can do a GET request on that URL. So let's take a look at what we do once we have this. So we have this little guy called twtest, and it imports the augment function, and it imports URLlib. And so it says, okay, I would like to see the user's timeline for the screen name of Dr. Chuck and show me the first 2. And so it augments the URL, which means it's adding the stuff. So we take this thing, and that's how it adds all the stuff, right? We pass in this part, and then we pass in the 2 parameters, the count and the screen name. And then the augment adds the security stuff. So when we print this URL, clear that. When we print this URL, it's going to look pretty much like that. And I'll run this in a second so you see how it really works, ... something. Then this bit of code is pretty much exactly the code we used when we were doing this with Google. And so we do a URL open, and then we do a read, and then we print that data, and this is going to be JSON data. And then we can ask information about the headers. If you go way back 2 or 3 lectures ago, I talked about how you get the headers of a HTTP request and the body. This is our way of asking for the headers to this. Let me clear that. This gets the body, and this gets a dictionary of the headers. And you'll see why we want to see that. And I'm just going to print all that stuff out. So in this I'm going to keep it really simple. I want to focus on what's going on here where we're augmenting this URL. Just remember that we're getting JSON back here and we're getting JSON back there. So let me go ahead and run this. It's going to be really boring. TW test. So that's the program. And again, this is really to show you how this augment thing works, because the next one I'm going to just assume you know that. And then we're going to just read it. We're going to read both the headers and the data. We'll just print everything out. So if I say Python TW test py. So it just ran. So let me sort of show you, walk you through what happened there. Okay. So this is that augmented URL, and all that junk is the signature. It's not, OAuth is really cool. You don't actually send the secret. You send this thing called a signature, and it's got these things that include the time, so you can't do it twice. All these other things are really cool. And so we just did a URL lib open and a read, and then we got some JSON, and it's a lot of JSON. And later we'll take a look at this JSON. So what we got were the first two entries of my status, which is going to go down, down. Well, there it goes. Let's see. So this is the end of that. We'll see this in a prettier way in an upcoming slide. And remember, I printed out both the body and the headers. And so in the headers, it's a dictionary. So this is a dictionary, and this tells us something, right? And if you go back to HTTP, you don't have to know all this stuff. There was a content length, and this turns out to be like when our rate limit is going to get reset, because we're talking to an API that gives us our rate limit. And this one's probably the most important thing. The rate limit remaining says 178, which means we can only do this 178 times today, right? It's going to reset perhaps tomorrow. So I'll do it again, and you'll see that my remaining thing will go down to 177. So I'll just run it again. I did it. Oops. I went down to 176. So it's the rate limiting factor, 176. And there's other things. And as you read the API specifications, and I'm not going to, this is not a class on how to talk to Twitter, you will see, oh, I will give you back the rate limit, the number of API calls you have remaining in the header field x-rate limit-remaining. So you just look that up with square brackets, and then you can get that number. Okay? So now what we're going to do is we're going to take a look at a little more sophisticated application that's going to do this same thing. And we're just going to do something a little more intelligent and parse the XML and actually go through not just one thing, but parse the JSON and go through it. So we're going to take a look at the API developer documentation for the friends list. So we're just going to say, I want to see this person's friend list. We're going to tell it which screen name we're interested in. We're going to use the augment, everything, except now we're going to spend a little more time focusing on the data we get back and parsing. Okay? So here is twitter2.py. So twitter2.py, it looks a lot like that twitter1.py, except, the TW test py. We import URL lib, import TW URL. We're going to import JSON because we're going to actually parse what we get back. We read the API documentation, and that's the base URL. And we're going to write a loop here, a while loop, and we're going to ask for a Twitter account. If we just press enter, which means the length of that string is less than 1, we're going to break. Then we're going to augment this URL with the account. This account comes from input, right? And we're going to say, give me the 5 friends. Give me the 5 friends of whatever account we type in. And then we will print out, just for debugging, the whole URL. This is the augmented URL. That's the augmented one. Then we're going to open, this code is just from the previous one. We're going to open the URL. We're going to read the body, which will be JSON. This reads the body, which is in JSON. This is the headers, which are a dictionary. So as a side effect of this read, we can say, oh, read the body, but also hold on to the headers and give them to me later. So data will be the JSON and headers will be the remaining. And so if you recall when I was showing you before, we can find out what the remaining number of times I can use this API by looking up in the headers that we got back under x-rate-limit-remaining. Look it up, print it out. Okay? Then what we're going to do is we're going to deserialize the JSON. Remember the JSON, the body is like curly braces and dot, 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 dot. And we're going to turn that into a list, an array, because we asked for 5. It's going to start as an array and give us back the array of entries in this person's friend list. Then what we're going to do, and this is really common and helpful, is we're going to dump that out with an indent of 4, and that's pretty printing. And there, if you're ever looking at JSON, and I guess I'll show you this next time I flip over, you can find a pretty printer where you can cut and paste ugly JSON into a web page, and it'll show you the pretty JSON. But this, I'm going to do this with JSON dump S, and that's taking this array of objects and then dumping it in a nice thing where everything lines up and they indented and outdented and stuff like that. So that's nice debugging. I like doing that. Indents 4 is how many spaces to put on each thing. So then what I'm going to do is I'm going to go through the list of all the users who are friends, and then for each user, so user is going to go dot, 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 dot. That's how you loop through a list in Python because of the JSON turned into a Python list. And then we're going to print out the screen name and their status subtext. And so we're just going to parse all this stuff and go dig through it. And so this is what that looks like. We're going to retrieve the URL. We've got an object that includes the users, which is a list. And here's the first one. And then there's many of these things. There, it's very, very long. I truncated it here. And then it's showing me the screen name and the person and the status. And it's just pulling it out. So let's see. We find the screen name is here. We find the status text is here. Right? So clear this. Let me be clear on this. So this is the JSON debugged, actually truncated. And we're going to go in for each of the users. We're going to pull out the status text, which is this bit right here. Show that. And then we are going to find the screen name of the person right there. This happens to be my friend list from a while back, and I had just added Leigh Culver. She's an open source software developer, and she wrote the PHP OAuth. She wrote free code. So thank you, Leigh. She wrote it. I use her code all the time. So let's run this code. Let's go ahead and run this code. And before I do that, I'm going to show you how to do JSON pretty printing. So if you end up with some really ugly JSON like we had from this other thing that I just did, and it's really long and really bad, I can copy this. I can take this, the JSON starts there with that square brace. It looks scary, but you kind of get, it's like the Matrix. After a while, you sort of figure out what's going on. It starts to make more sense. Okay, and there, oh, I messed up. I got to start over, get that JSON. So, right there, I copy it. Then I go to a Google browser and I say pretty, print JSON, and pick one. Hopefully one without too many ads. Paste that monstrously difficult stuff to read, and then there you go. It reads perfectly, right? And so this just, if you're debugging something and you're printing JSON out, fine, but it's easier it's easier in Python to do what I'm doing here in Twitter2.py, and that is I've got my own pretty printer right here where I dump S. So this is the JSON data that's been parsed, but then I dump it with an indent of 4. Okay, so we already talked through this thing. We read an account, we augment a URL with these 2 parameters, we do a read of it, we're going to look up the remaining rates, the number of things we got, and then we're going to pull out the screen name and the status text and print that. So Python Twitter2.py. Leigh Culver won't be my first friend anymore. It'll be who I ever did recently. Yeah. Okay, so there I get. So you see the pretty printing works out really nice, right? I asked for the last 5 users. It's quite a bit of stuff. You know, after a while you don't want to print all this stuff out, right? So let's go up to top here. So I have 14 remaining calls to this, so I got to figure it out nicely. It looked that up. And then users is an array, and there's all this data. Let's see, let's find the screen name. The status text. I pulled that out for this first person. And let's see if I can find the screen name. Screen name Knight FDN, Knight Foundation. So let's go back down to the bottom. So I said that's a person and then Rose. Hi, Rose. Rose from UCLA. And let me see who Rose's friends are. So I had 14 left. Okay, so this is Rose's 5 friends. All right, so U.S. News Education. Let's see who U.S. News Education's 5 friends are. Now I'm doing all these as me, and if we go way up to the top here, well, I don't know, view ways, come on, little mouse cursor. Let's see how many I got left. Every time I do this, my number will go down. Right there. See, I only have 12 left. After a while, I would comment out the dumping of this JSON. I only print the JSON out when I'm actually trying to figure out how to parse it. So that gives you a sense of using that Twitter API. And that sort of brings us to the end of this API web reading structured data using web technologies. And application program interfaces, you know, their set of rules. We can read the documentation, figure out how to write code. Sometimes you have to use things like OAuth to secure your URLs, and often these things have rate limits. And we talked both about XML and JSON as serialization formats. So we've covered a lot of stuff. We've covered APIs. We've talked about OAuth. You don't have to know all this stuff. As you start to look for sources of data, these are just tools in a toolkit. And we'll have you do some assignments that hit on some of these things. And then later in later lectures and later courses, we'll make use of the skills that we've learned in this section. So welcome to our chapter on objects. Now this chapter doesn't actually exist in the book, at least not in the current version of the book, but I thought it was a good time as our skill level and the complexity of the programs that we're writing starts to increase to talk about object-oriented programming. The key is we're not going to spend a lot of time writing a bunch of objects, but we're going to use a bunch of objects. And frankly, we've been using objects all along. This is not so much about a new code technique. It's just to try to give you a little explanation as to what was been going on all along for this class. When I say things like constructor or this is how you make an empty dictionary, I want you to have a better understanding of that. So suspend disbelief, and I'm not really trying to teach you at this moment a skill so that you can become an object-oriented programming wizard, but I want you to get to the point where I can use a series of terms in the remainder of this class and not have you get confused. So we have been seeing object-oriented programming all along. So here is the Python documentation for lists, and it's a data type, and it talks about methods. We've been talking about methods all along. I've been using the word methods. Methods are like functions that are part of an object, okay? And so we've been using this all along, and when I say we just construct an empty dictionary, the word construct is a loaded term that has to do with create a new instance of a particular object. So we've been using this. And as we move into databases, we see that, you know, as we read the documentation, they start using the word object, they use the word method. And so all these things are terms that I want you to be at least familiar with the terms, not necessarily a wizard at writing objects, because you don't always want to write objects. Just like with functions, you don't always want to write functions, but we use them a lot. So even functions and objects, we use them far more than we actually build them. Okay, so let's take a look at programs that we've talked about before. Here is my favorite elevator floor number converter. And this program is sort of my simple favorite program because it has input, processing, computation, and output. And right now we think of this. And if you think of all the programs that you've written so far, they're just variations on this. They start somewhere and they do some stuff, maybe have some loops in them, and then they finish. Okay, so that's a very sort of classic program. It's a monolithic program. We might write a function, but it's only one way to think about a program. As we build more and more sophisticated programs, we start building more and more sophisticated data structures. And so in this little example, we are going to make a list and have that list be a list of dictionaries. And so, you know, we say, let's construct a list. That's object-oriented isms. Let's construct a dictionary. let's store some keys in the dictionary, and then let's append to the list of movies. So movies.append, and the thing we're adding is a dictionary. So there's a list that has dictionaries, and then we're going to do this again, make a new dictionary in movies, and add the second movie, and so we'll end up with 2 dictionaries. So we end up with a data structure. This is a data structure, and you know, when we were doing sorting, we would make a list of tuples, and a dictionary becomes tuple. So coming up with shapes of data is part of solving programming problems. And so we've been doing this. Now, the thing about this, if we start looking at this, we're going to realize that we have decided that this data, each dictionary in this list, is going to be shaped the same way. It's going to have a key of director, title, release, running, rating. And frankly, if we misspelled this, you know, missing the I there, that would mean that this was somehow kind of a broken one. Now, there's no way for us to say exactly what these keys are supposed to be, but in a way, this is like an object already, in that there is 2 things, thing 1 and thing 2, and they're very similar in terms of the kind of data that they contain, and they sort of have a shape. There's a shape. It's not enforced in any way, but by convention, we just do the same 5 things in each one of these. There could be literally hundreds of these. So we can write code that basically takes advantage of the consistency of the shape of these little dictionaries. So basically, to recall, we've got a list, and then we have a dictionary with keys, dictionary with keys. So that's what we're doing with. So we can, in effect, loop through the list and go through, then so item becomes this guy right here. And we know that there's certain keys. And because we are shaping these dictionaries the same and using the same keys, then what we can do is we can basically loop through all the keys that we expect to be there. So we're saying, I'm expecting to be this. So we're going to loop through each one of these, and we're going to go through each of the keys and then grab the values. So we'll print key and item sub key. Okay, and so this is just a way for us to iterate. We are keeping track of, in effect, the schema, the data model, as it were, of these little dictionaries. And so what we're going to do when we start talking about object orientation is we are going to find ways to create structures that look like this, but we have a much better way of sort of enforcing the naming conventions and building a contract as to what kind of data is inside of a movie, et cetera, et cetera, et cetera. So that's kind of bringing us into object-oriented programming from kind of how we would use it if we didn't have objects. So now when we start looking at object-oriented approaches to programming, I mean, like I said, you've been using these all along. You make a string object, a dictionary object, but the whole idea of object-oriented programming is there are pretty powerful little gadgets that we are connecting together. And so the program itself is more of an orchestration of multiple different kinds of things and the capabilities that those things have. And so the word we use for all those little things is object. And an object is a bit of self-contained code and data. It's not like a function, which is a bit of code, but it is code and data. So if you're going to build on the concept of function, you're adding local data and multiple instances. And part of the goal of object orientation is to take a hard problem and kind of break it into parts and to make each part smaller and then hide the complexity in one part or the other part. Just for an example, when we build, a program and it's going to make use of a database, SQL, this code that's inside there, that's really large and really complex. So what we do is we sort of hide it. We firewall it. It's like, oh, okay, we keep our little bit simple, but that thing is really complex. But we have a really simple way of looking at it. So it's also a complexity hiding and detail hiding that goes along as well. And like I said, we've been using these things all along. Okay, and so then you start to model a program, and it still has input and still has output, but now it's a network of objects that are making use. And so the string object, a dictionary object, and there might be objects that you define yourself, and these objects you're orchestrating in your code, saying we'll take this out of the dictionary and put it into a tuple and do this, and we'll sort this thing, and then we'll print some stuff out. And so you're still orchestrating it to produce the overall input and output. It's kind of a different way. Now, so far, we haven't built our own object yet, but we've been using things like dictionaries and strings, and inside of string is uppercase, right? To make things go in full uppercase, or split is in here, And so each of these objects has capabilities that we're going to make use of. And so each of these things has a bit of code and a bit of data in it, kind of like a function, but the difference is that functions themselves don't have separate copies of data for every separate copy of the object. And like I said, part of the goal is to hide the detail. And so at some level, if you're working inside this object, you can write real complex code and be real clever, think really deeply, but then we don't have to think about the rest of the program. Part of it is not to worry about it. Okay, so let's put some complexity like SQL, or even, it's a string. The strings themselves are pretty powerful. And so that's a string or a dictionary or something. All that stuff is very powerful, but when you're the person building the string object code, you have to think deeply about it. But we think about it exactly the opposite. We're like, oh boy, that complexity, who cares? I just care about all the cool stuff that I can do. And so it's a way of isolating complexity and presenting a relatively simple interface that hides complexity in both ways. Both, if you are the maker of the object, you can say, I don't care how this program is going to use me. I'm going to give these little things out to them. I'll deal with this. They'll help me do stuff. I'll do whatever for them. And my stuff is complex. And the other stuff, this side might be complex too. But all we care about is this. And so the complexity can be partitioned. So there's really two domains of complexity, and each domain can ignore the complexity on the other one. And so that's a little bit about how we put programs together from separate objects. Up next, we're going to look at some terminology and figure out how objects can be defined in Python. So now we're going to just cover a bit of terminology for object-oriented approaches. There are two ways to look at terminology. One is I can write quiz questions about terminology, and the other is later I can use these words in a sentence and expect that you understand them. So basically these are some words that we throw around in object orientation. One is class, which is like a template. And I love the idea of a cookie cutter. And a cookie cutter is not a cookie. But if you have some dough, you can make as many cookies, and they're all based on that template. And so that's one. Within a class, you have code is capability, but it's more like a function. We would call that a method. Some people would call that a message, and those two terms are kind of equivalent. You either call a method in the class or you send a message to the class. Whichever you're doing, you're kind of activating a little tiny bit of code in the class, like causing the dog to bark. So here's the barking code, which would cause a little bark noise to come out of our speaker, for example. And then there's code and data. So method is how we access the code inside of an object. And the data is like a field or an attribute, which is really just a variable that lives inside the class. And then the actual object that we're going to use, or instance, that is, back to the cookie cutter model, the class is how you make cookies, but the cookie itself is the instance. And so we can have lots and lots and lots of cookies, right? So class describes the abstract characteristics, including all the methods, it's all the data that's inside of it, the code that's inside of it. Another way to think about it, it's like a blueprint or a factory that manufactures these things, but it's not the things that come out of the factory. It's a pattern as compared to the thing itself. It's what we expect to see coming from all of these objects. So when we look at the string documentation and we see, the starts with method, that basically says that all strings should have a starts with method. That doesn't mean that the class defines what things should be there, but it is not the thing itself. The instance is the actual variable, the thing that we're going to use. So if in our program, we might have 40 variables that are all strings, and that's okay. There are 40 instances of a string object, right? So there are 40 instances of a string class. Class is a whole category of things that are all like strings. They're all pretty much the same, but like we have X and we have Y and we have Z and A and B and C. Those are the instances. And so we often use the word object and instance. As I said, classes contain code in addition to data, and the method is the way that we activate the code. And it's basically a function that's scoped to being within the class. And so that's our quick summary of terminology. Up next, we're going to actually build one of these things. So enough with the pictures and enough with the terminology. It's time to write some code. So we're going to actually write a sample class. It's not going to do anything useful whatsoever, but here we go. So here is our class party animal, okay? And it's a kind of an animal, and it has inside this class as a new reserved word like def or break or continue. Class is a reserved word. This is, we're defining, and it's kind of like a def. Remember, the def doesn't actually execute, it just remembers. So class says, remember this template, and I'm naming the template party animal. I haven't made any objects yet, but this is the class. And then for inside this, we indent, and we just simply say, oh, x equals 0, and that's a variable that's part of every instance of this class. And then if we want to do a method, we have some code, like the def, and that's indented, and then it indents even farther, right? So it's, it's indented to be part of this class, because that's part of the class. And then we do def, which means here's, and we could have multiple of these. We're just not showing multiple of those. And so we have the name of the method, which is party, and then we have a parameter. Now, if you're familiar with other object-oriented languages, one thing that's different about Python than other object-oriented languages is the concept of a pointer or a variable that is an alias to the instance, which we'll cover in more detail. And so the first parameter, by convention, not by requirement, but by convention, is always self. And then if you have more parameters, you put them after this. So pretty much every method has to have one parameter if it wants to talk to the instance variables. And then within the code, it has this thing called self, and that says there'll be many x's, which we'll see in a bit. Self.x is a way to talk within an instance of an object to the x that's part of the particular object we're doing. And so you'll see these things to go to these objects. We could have like a equals 2. Those aren't object-wide variables. That's just a local variable in that code. So self.x is a way. Well, I'll cover that in a bit. So there's a bit of code in there. Has some rules, the self parameter, which we'll come back to. And then what happens is, so this part here gets all just recorded, and it remembers it in the name party animal. And now we're saying that we want to actually create an object, okay? So this is a class, and now we're going to create an instance. So we basically say, call the party animal thing, and make me a party animal object, and return me the party animal object, and put it in the variable an, okay? So now at this point, the variable an is an object, and we can do things to it based on the definition of the class. So we can call the party method, and we can call the party method again, and we can call the party method again. Now, to just sort of clarify this, not that we have to fully understand this right now, but since an is of type party animal, the way this works is it calls partyAnimal.party, which is this code right here, and passes in the instance variable an. So this, you can think of this as almost a syntactic transformation, where this code is being called and this is being passed in, and that's how this self becomes an alias of an. And again, we'll hit this later and it will make some more sense. But I'll just put this here as these two things. This is like a short form of this, okay? So if we watch this code run, okay, like I said, as Python encounters the class, it's like the def, and it simply records this and defines the new concept party animal, right? And so when the program runs, no output happens. It just remembers, I got a template, I got a cookie cutter named party animal. I can make as many of these party animals as I like. And then we hit a line that basically says, make me a party animal and give me back an instance of party animal. And I'm going to, this is like a function that gives you an instance, and then there's an assignment statement that says, put that object into the variable an. And that's what happens there. And at this point, Python uses this class to create a variable called an. And it says, oh, there is a variable x inside of an and a bit of code called party inside of an. So this little green box here, that is the object, and it has stuff inside of it, code and data. And this object is created when we construct a new party animal, okay? So now we're going to call the method the first time. And so if you look, that effectively fires into party and starts running that code. And self.x is this thing, and so now it changes that from 0 to 1, and it then prints out so far 1. Okay? Then the def returns, and then it comes back to the main program just like a function would, and it says, oh, let's call party again. So it goes back up again, and it runs the code. It adds 1, so this becomes 2, and then it prints out so far 2. And then it comes back to here, and then it runs the code again. It goes up, runs this code, this x within, which is from 2 to 3, then it prints out so far 3, and then it comes back down here. So this function has access to all the data that lives inside this object while the function is running, and it's using self as the way to access this thing. And so you can think of this as self is an alias to this an. This out here, an is a variable that we've got, and we can just do stuff to an in our main code. But we don't know about an here, but while this code is running, when we call an.party, self is an alias to an because of this. Okay? So self is like a global variable that's throughout this whole thing, and it's a way that we access the actual instance of the object. See, I told you how much fun this was. No, I'm just kidding. So far we've talked about class, which is a template. Just for review, the methods or message is the code that's within there. There's also fields or attributes, which is the data in there. And an instance is when you use the class to make an object and then you have an object instance. It's the particular instance of a class. Okay, so if we take a look at this, what we're really doing is making new types of variables, right? So we have like integers and floating point numbers and strings and Boolean and whatever. But what we have done with class is we've made our own type of variable. And so if you recall, if we make a list and we say, what kind of thing are you with type? And it says, oh, I'm a list. And then remember what dir does. Dir basically tells us what are the capabilities of this. Now we have a word for this. These things in list, like extend, count, pop, remove, reverse, sort, these are methods. List is a class that's already built in. X is an object that we get back from it. And we say, what kind of thing is X? Well, it's a list object. Oh, we say dir of X. We say, what is X capable of doing? And we see all of the methods. Append, index, insert. So these are called methods. We've been using them all along. Okay? So that is dir and type on objects and classes and instances that we've been using so far. Okay, and so remember, when we did dir with a string, we make a new string object, we assign it into y. That's the long version of that. We ask, what's in it? Oh, we got an R index, we got a split, we got this, we got expand tabs, we got all these. These are, again, methods. Right? Turns out that these are also methods as well, with special names that have to do with supporting things like greater than, which supports the greater than operator, and less than is when it gets called when then we see syntax like, if I see like x less than y and these are strings, it actually calls this method. Not that you need to know that, okay? R index or is upper, those are things that we call when we want to accomplish things. So every string has all of these methods in it. Let's take a look at the thing we just made. So we made a thing called class party animal. Python reads that and says, oh, I'm going to make a template that's shaped like a party animal. So we shape like a party animal. And this is it. It's got some code in it. It's got a variable in it. And we're going to make an instance of it and assign the instance in the an variable. And now we're going to say, what kind of thing is an? Print its type. And then dir says print all the methods. And so type says it is an instance, which means it's an instance of an object or instance of a class. And we do dir, it says, well, we can call doc and module, those are built in. Party, that's our party. X, that's our X. And so Python itself knows the member functions and the attributes in a class that we created. Okay, so that basically gets us through some of the syntax, the concept of self, the fact that self is the alias for the actual instance, and then we'll continue and do some more in just a bit. So now we move from sort of the SQL and the contracts we need to talk to a single table to linking multiple tables together. And this is where the real power comes, and this is where the complexity comes. So up till now, it should be real simple. When you start a company, we're going to kind of pretend we're going to start a small company to build an application to manage music. When you start a company and you're going to build an application, lots of applications need databases. And you need to design the database for your application. And often this is very much a team effort with a lot of different people with skills. Some people worry about the end user capabilities, some people worry about the performance, etc. And so database design, what I'll show you coming here is just the beginnings of database design. But the basics are very powerful. And it's something where smart people should take time in database design. And so it's a very collaborative process. And if you ultimately look at the database design for applications, we draw these crazy pictures, right? And in these crazy pictures, we are capturing, this is basically multiple tables. Table, 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 table. And this particular database is kind of about an events, like, reserving the picnic shelter at a park, right? What times, who's going to be there, who reserved it, all these other things. And what we're starting to show is that how these tables are connected together. So each of these little arrows. So these are the, this is a table, and these are the columns in the table. And then some of the columns are special columns that represent relationships with other tables. And we're not going to go into all the detail. You can eventually go into some of the detail where you see what this little arrow means, and that means one, and this means many, et cetera, et cetera. And there's all this fancy stuff. And so we'll talk about this eventually. But this is sort of like what we're going for. We're going for a picture of how we want our application's data to be stored in the database. And this then becomes our schema, and it's the contract. So we made one table with two columns, and that was a schema and a contract. But now we're going to make multiple tables with many columns, and some columns that are specifically there to connect from one to another. So if you're working in a large application, you might walk in and see a picture like this on the wall. And they look, whoa, that's really important. That must be pretty complex. And for this application, it probably represents years of clever engineering to make sure that the application runs well. But this is basically how this, I don't know what it is, OpenMed medical record system, I just kind of borrowed the picture. This is how the data is stored in its database. And these things can be very complex. In a project I work on called Sakai, it's probably 4 times bigger than this. But if you zoom in on it, which you can't, but it's just a table and some columns and some connections. And then, oh yeah, there's a table. Well, that one's kind of complex. Here's a table, some columns, and 2 connections. So yes, it looks complex on the surface, but ultimately, we're just trying to figure out which tables we are going to make, what we're going to put in those tables, and then how we're going to connect the tables together. And the connections are the thing that make these things so powerful. We could just put all this data in one file, but then this thing would run like terribly slow. And so the trade-off of thinking through how your data is going to look is that when you're done, it's fast. A lot of times we don't worry too much about how fast your program is going to run. But when it comes to scanning data, especially if it's a lot of data, you think about that a lot. So the whole idea is to figure out the data that you need to represent and then drawing a picture and then lines between those pictures, right? And the basic rule that we're going to use is don't put the same string data in twice. So for example, if we have a column of something, don't put Chuck in twice. So that's bad. So if you have some column and you're replicating the same string data twice, that's not good. What you want to do is you want to make another table and put a Chuck over here and give a number to Chuck like 1 and then put 1, 1. So to indicate that something belongs to Chuck, which means you're modeling data at a connection between one table and another. We'll go through this in super great detail. So the basic rule is don't put the same string data in twice, use a relationship instead. And the other thing is sort of like model the real world. If you have users and tracks and Christmas tree farms and whatever, you'll have a table for the Christmas tree farms, and you'll have another table for the Christmas tree types, and you'll have another table for whatever. And so often you're starting to sort of build an application. And so the application that our little company is going to build is an application keeping track of audio. Our company has decided that people don't use albums anymore and aren't interested in buying whole CDs of music. So we're going to sell music by the track. I think this is a great idea, and I think we're all going to get rich with this little company. And this is the user interface that I invented, or I screenshotted from another vendor's. But whatever this is, this is the program we're going to build. We're going to make a track making thing. Now, just looking at this user interface, we see some problems right away. And often, if you try to just turn this into a spreadsheet, these things would become the problem. And the problem has to do with replicated data in columns. And so it's like, great, this is all cool, until you have the same artist name in the columns. That could be once or hundreds, because Black Sabbath has written hundreds and hundreds of tracks. And then even in the album column, that's a problem. And then it gets even worse when you're in the genre column. You're putting this string in a zillion times. And if you've been writing Python programs, they kind of finish really fast. And that's because the only assignments I've given you are tiny. But when you're going to do 1 million or 1 trillion things, the difference between metal and the number 2 to replicate this is actually very significant. Because this isn't just a 6 or 5 character string. This could be a very long string. And so in your data, you have to allow for very long strings. And so these are the problems right there, all this replication. Now it turns out that we have a user interface person in the room, and the user interface person, we say like, hi, we're a database expert. We took a class online and we know that you're not supposed to replicate data. And the user interface person says, oh no, this replicated data, we've done surveys, and that's exactly what the user wants to see. And you can't argue with that. If that's what the user wants to see, that's what they see. But we still have to write an efficient application. And so that's where we start going through a data modeling exercise, where we say, this is the kind of stuff we want to represent, and this is the kind of user interface we want to support. How can we build a really good data model? So it's not like you've got to change the user interface to make it good. You change the data model then to represent the stuff we want, and then construct it in a way that the user interface is exactly what the user wants. So the idea is you look at the data that your application is going to look, and we got all these columns, and you say, you know, is this column represent a thing in the real world, or is it just another attribute of a thing? So there's like a thing and then attributes of the thing, or two things. And so you got to go across all of the columns. And so that's what we're going to do. We are going to look at all the columns, and we are arguing. So right now, imagine we're in a conference room, we're sitting around a table, and we're going to draw this picture. And this picture looks like the thing. It's got little boxes and lines, right? We're going to draw a boxes and lines picture. And we have a blank screen right now. So the first question actually in these meetings is commonly where to start, because you got a lot of stuff. In our simple, it's really simple. And it turns out that it's not so critical where you start. Even if you start at the wrong place, eventually you're just going to have this web of information, and it's all connected, and it'll all work out if you do it right. But it does simplify the drawing of your picture if you start at the right place. And so the way I was taught to start at the right place was to think about the thing that is the most essential to this application. What is the one-sentence description of this application? And in this application, it's a thing that manages tracks. It's not an album managing thing. It's not an artist managing thing or a genre managing thing. It's a track managing thing. And we kind of see that in our user interface. We see that every line is a track. And so that makes it easy. The first table we're going to build is the track table. And once we build the track table, then we have to look at all the other things and say, look, which of these things are themselves tables and which of these things are just attributes of track? Okay, and so it turns out that things like numbers and like stars, just a number, that's 5. These are all 5s. Apparently, I only like stuff or hate it. and then this is the number of plays. And so you go like, oh, that's part of it, that's part of a track, that's part of a track. Well, and now we come to the three things that aren't part of tracks because they have the replicated data. That's the red flag that says, not part of a track. So somebody gets up to the board, grabs a piece of whiteboard, and they go like, that's our first table. It's a track table, and it's going to have a rating, length, and a count. I guess there should be a title in there as well for this column here. So we have a title field, title. Okay, so now we're good, right? We've got that. The question is, what's connected to that, right? Well, what is the thing that's the next thing to draw? Well, tracks could be connected to artists. They could be connected to albums. So let's just say kind of albums have many tracks. So the next thing we're going to do is we're going to make an album table. And we're going to say on our whiteboard, we're just drawing on a board right now, we're not writing code yet, that tracks belong to albums. And now it's kind of easy that what albums belong to? Well, albums belong to like groups. Now if you're a music expert, you kind of understand that we're oversimplifying things. And that's a fine argument to have when you're starting your company. But we're going to pretend the world's simple and that tracks belong to albums that belong to artists. So we're almost done with our meeting. So we got artists, albums, and tracks. We've drawn a picture. And the question is, where does genre belong to? What does genre connect to? You know, because does genre connect to an album? Does genre connect to an artist? Or does genre connect to a track? Now you may want to go to your iTunes and go to a track and change its genre. Change it to, easy listening. Now, if the track was, if the genre was connected to the artist, this is an album, sorry, it means that it would then immediately change all those to easy listening because that means that albums have an attribute of what their genre is. If it was the same for an artist, that means that all your AC/DC would be changed to easy listening. And if it was an attribute of track, only this one would be changed to easy listening. So the question is, when you go into that system and you change one thing, does it change all of these based on the album or the artist? Well, you can go pause and go ahead and do that, but I'm going to tell you. It turns out if you change that, it only changes one. So that actually tells you. And so in the meeting, we're arguing about this. I think it should be here, and I think it should be here. And then you say, well, but if you do it this way, that means that it's going to change. And then the UI person was like, no, we can't have it connect to the album because then our users would be so mad at us, blah, 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 blah. We wouldn't make a lot of money. So when it's all said and done, you've argued through. It took you a lot longer to argue this last bit. This was the hard part, to say, okay, genre belongs to track. It just does. And this is a simple, trivial example of how the data model creates the features of the application. Sort of when we started, we saw this big picture that what's in the data model determines what the application is capable of doing. And we have to get the data model right so that it can all be very efficient. So now that we've drawn this picture on the wall in our conference room, at some point we have to map this into a database structure, okay? We're going to figure out how to actually map that logical picture that we just drew into a physical picture, exactly how we're going to represent this in a database.